Hey guys, welcome to this live session by Intellipaat. So in this live session, we are going to look into artificial intelligence. So now, artificial intelligence is a very popular technology right now, and without AI, a lot of technologies won't exist. So some technologies where AI has its presence is self-driving cars, mobile assistants, and medical imaging. So in this particular live session, we're going to learn from the very basic of AI up to the most advanced parts where we'll be doing projects in AI. So before moving on with this session, please subscribe to our channel if you haven't already so that you don't miss our upcoming videos, and also leave a like to this video and all the videos you watched and enjoyed from our channel. Now before moving on with the session, let's look at the agenda. We'll start off with the introduction to artificial intelligence, where we'll understand what is AI and why do we need it. After that, we'll look into the subset of AI, which is deep learning and also neural networks. Once we learn about that, we'll move on to the tools which we can use to create AI models like TensorFlow and PyTorch. Once we cover all these theory concepts and also the tools required to create models in AI, we'll move on to the projects. So the first project we'll be doing is a facial recognition project using computer vision. After that, we'll do an AI project on HR analytics. The third and the final project we'll be looking into is a credit card fraud detection project using machine learning. So now once all of these projects are done, we'll basically do a comparative analysis on machine learning and AI. So we'll understand the differences between machine learning and artificial intelligence. So once this is done, we'll move on to learning the AI engineer career path, where we'll be understanding the skills required to become an AI engineer and also the salary of an AI engineer. So once all of this is done, finally we'll move on to interview questions. So we'll be doing interview questions on machine learning and deep learning, which are basically subsets of artificial intelligence, and that would be the end of this particular live session. So now without any further delays, let's begin with the first topic of this particular live session, which is introduction to artificial intelligence.
One important aspect comes into picture when we talk about artificial intelligence. It is the year 1956, guys. Well, pretty much in the year 1956, the term artificial intelligence was actually coined. Well, how did this actually come to happen? I mean, I know a lot of us might actually know that it was coined at the Dartmouth conference and so much more, but what exactly is this conference? Well, in 1956, for a couple of years, basically, there used to happen, there used to be meetings and a couple of meetups where a lot of scientists and researchers used to come together under one roof. And this eventually was called the Dartmouth Conference. And here, basically, what started out as a summer research project, and it lasted about 8 weeks. And at the end of it, the product of their research and the product of basically their entire project was one person who coined out the name what is artificial intelligence, and it has ever been stuck with us right back from 1956, right? So I hope you got the Lord of the Rings reference there. So it's one conference to rule them all. It's basically one ring to rule them all if you haven't got that. And coming back to the presentation, so even after 64 years of the term being coined by Mr. John McCarthy, he is regarded as the father of artificial intelligence, guys. Even after 64 years, the world is still going mad, still going gaga about artificial intelligence when you think about it. Well, especially in the last 10 years, right? I mean, everyone is on the everyone is on the trend of artificial intelligence, and it's just gonna go like this for the next couple of decades, is actually what analytics tell us, guys. So here's a quick excerpt that I read. Pretty much this is from the person called as Daphne Koller. She's a scientist at the Stanford Artificial Intelligence Lab, and she says that John McCarthy believed in artificial intelligence in terms of building an artifact that could actually replicate human level intelligence. Replicating a human is pretty much the toughest thing that even these big scientists could ever think of, and this was thought about way back in the 1950s as well. And she says that he was very happy with a lot of artificial intelligence today, because at the end of it is not replicating the human level intelligence that it was actually sought out to be. And it is said that he wanted artificial intelligence to pass something called as the Turing test. Well, if you guys know about the Turing test, just head to the comments section and talk to your fellow viewers and let them know about the Turing test. And if you cannot hold on to the curiosity, give me 2 or 3 more minutes. I'm going to tell you what the Turing test actually is, guys. So on that note, we need to check out what artificial intelligence actually is. So let me give you the breakup of the textbook definition, guys. Well, the definition goes like this: it's the theory and the development of computer systems, basically, which are able to perform tasks normally, which actually requires a human to do the task. It might be something as visual perception, speech recognition, decision making, and translation between multiple languages as well. Well, that definition will make sense if you actually go through it twice. I mean, this is the textbook term, right? So I usually keep all the sessions very simple for all the viewers, from the beginners to the advanced level, guys. So, you can have a lot of takeaway from it if we actually, go about simplifying certain things for you. So, the current goal of artificial intelligence, if I have to put it in one picture, is basically to tell you that it is just mathematics on steroids, guys. Because when you think about it, all artificial intelligence is trying to achieve is better ways and faster ways to do something that a human can do. A lot of terms like machine learning, deep learning, and come into the picture when we talk about mathematics as well. Because at the end of the day, to achieve artificial intelligence, we use so many concepts which involves a lot of mathematics and implementing this mathematics using code, guys. And at the end of the day, it's mathematics plus programming which will actually lead to us achieving cognition, guys. So what about the future? Well, again, achieving cognition has always been the goal, even of the even it's been the goal of the person who actually coined the term as well, and pretty much every one of his followers and everyone who wants to do something with artificial intelligence pretty much can tell you about how important and how amazing it would be to actually achieve cognition. Well, by cognition, I actually mean that getting a machine to replicate what a human can do exactly the way the human does, or even do it better as well, guys. So what do you guys think about it? What do you think in the future? What do you think artificial intelligence has a grip in the future? So head to the comment section and do let me know there. So then you might have heard of these terms, as I mentioned, right? Machine learning, deep learning, and so much more. Well, guys, I would love to explain all of these to you guys, but we've already put out a lot of videos on our YouTube channel, and we have amazing subject matter experts writing out blogs for us as well. So if you want to know more about these terms, machine learning, deep learning, or how they are used to achieve artificial intelligence in general, I suggest you head to our YouTube channel after this video, and then you can go about checking our blogs as well. But hey guys, make sure you stick till the end of the video, because I'll help you fast track your career to become an artificial intelligence engineer, and I'll be giving you a special coupon just for the viewers of this video, guys. So on that note, let us quickly check out the timeline of what artificial intelligence was, what it is now, guys. Let us head back to 1943. Well, it was the time of World War II, guys. It was almost ending, and pretty much this person is the reason, in my opinion, why World War II ended. I am a major history buff, and I believe personally, and many people agree with me, thousands of people agree with me when I say this, Mr. Alan Turing, who was a British mathematician, was the person who ended the world wars, because the Germans used a very nice coding system which was called as the Enigma, and they used to use that to send messages, and well, the Allied forces never got to know what these messages were, because they were all encoded and they just look like rubbish. But Mr. Alan Turing developed the first artificial intelligence machine. He went about using a lot of mathematics, a lot of formulas. It took a lot of days, months, and years to go about cracking this amazing encoding system, which was basically generated by the Germans to go about sending their messages, guys. There's also a movie on that, so if you could watch that, it would be pretty nice as well. So this person, alongside breaking the Enigma, also it was called the Turing machine, basically, and then he invented something called as a Turing test. Well, what does the Turing test do? Well, I just told you 3 slides back that I'm going to explain it, right? So here it comes. So basically, consider this scenario that you are a human, and you obviously are humans, right? So basically, you're just sitting in front of your computer and you're asking a couple of questions to random people around you. And instead of saying it as random, let us consider 2 situations. One, your questions are being seen by a computer, and the other, your questions are seen by another human. So whenever you ask these questions, if you cannot figure out the difference between the answers that the computer can give and the human can give, I mean, if the answers are equally good where you cannot tell apart between the computer answer and the human answer, that particular computer which answered for you has passed the Turing test, guys. So that computer is intelligent enough to pretty much give you answers just like a human, and it can do a damn good job at it, guys. So this particular test, this sets the bar for, an intelligent machine, let's say. Because if a computer can fool someone into thinking that they're actually talking to another person, then we can say, to a certain extent, that pretty much that computer has achieved enough cognition, because it is pretty much going about, let's not say pretend, but it's trying really hard to replicate a human, and it's doing a good job at it as well, guys. So fast track to 1956, again the term was coined there, and scientists begin to tackle the concept. They were like, okay, now the term is set, let's work on it. And one of the top scientists, his name is Mr. Marvin Minsky. So basically his view, along with McCarthy's view, got him very good funding from the then American government, United States government, who basically hoped that, with the help of artificial intelligence, it will actually give them an upper hand in the Cold War, which was ongoing back then, guys. So pretty much Mr. Marvin Minsky along with McCarthy actually got good funding from the government, and they went about doing that as well, guys. So this another important thing happened in 1956 was Mr. Marvin went about starting the artificial intelligence laboratory at MIT, guys. And this lab, right from 1956 all the way till 2019 and 10 years from now, has been punching out amazing solutions to the world's problems, and it has been the most efficient laboratory in terms of artificial intelligence that the world has ever seen. And there are very intelligent people, and very much a force in these people which drive them towards achieving artificial intelligence, is what I can tell you, guys. And then again, a quick fast track to 1981. Well, 1981, artificial intelligence actually got commercialized. So this person called Mr. Ken Olsen, he is the founder of Digital Equipment Corporation, guys. So basically here he realized that, as a business leader, we can actually, start making use of artificial intelligence and start selling artificial intelligence to the common folk as well. And then fast track to 1997. This was one of the most important key moment, in my opinion, back in the 90s regarding artificial intelligence, because this was the first time there was a chess tournament conducted between the grandmaster Gary Kasparov. He was a world champion multiple times in chess. He actually played against IBM's Deep Blue. Deep Blue is basically their then supercomputer, and then Deep Blue actually defeated the world's best chess player at that point of time, guys. And people were saying that IBM's Deep Blue could actually think like God, because it was evaluating over 200 million moves in the game of chess at once. So for every move, it could bring up 200 million combinations of how you could go about playing. How amazing is this, guys? This is still 1997, and then artificial intelligence was already on the roll, and people could say it could think like God. I mean, that is a huge statement, and every time I go about reading about Kasparov or Deep Blue, I am amazed by the fact that this actually happened. In fact, multiple tournaments happened. You can probably read about it after the video, guys. And then fast track to the 21st century. We are finally at 2002, guys. I'm sure most of you might have heard of Roomba. Well, Roomba is a company, pretty much, it's from iRobot. It's basically a carpet cleaner, and it's a vacuum cleaner, guys. So it's a robot vacuum cleaner. So, in my opinion, again, this was another big achievement, because all it took was just few layers of behavior generating systems, which basically guided this machine around your house, around your living space, and it could efficiently clean carpets and floors autonomously without your help. And this has been sold across the world as well. There is 15 million units sold, and I use pretty much Roomba every day. So it basically has a docking station where it comes out of its docking station. It cleans our living room. It goes into the bedrooms. It cleans the bedrooms, and pretty much it just comes back, knows where its docking station is, and just goes back, charges, comes back again 2 times a day. You can program all of these, and it is an amazing thing, guys. It doesn't even, sometimes it starts doing it at the middle of the night, and I'm taken aback. Basically, you can set all of that. You can set the timings of which your robot actually starts cleaning and all of that. But it's actually amazing to know there is an autonomous system that I personally use to get my housekeeping stuff done, guys. So they've sold about 15 million units of these across the world, and that number is rising as well. And then coming to the maybe not so nice part of it, in a couple of people's opinion, but in my opinion, again, another amazing use of this is in war machines, guys. So many autonomous war robots were pretty much deployed to Iraq and Afghanistan. In fact, 2000 plus robots which are capable of war, everything from helping our soldiers carry heavy loads, defusing bombs which would be a threat to the life of the soldiers, patrolling enemy area, till all the way till they could make a stable war robot which is capable of inflicting heavy damage on the opposition forces, guys. Well, this is good in terms where our forces or any country's armies, navy or military forces are not put into immediate danger. Well, if the robot pretty much is shot dead or whatever, if it's malfunctioned or something, or if it's taken a lot of damage during the war, there is no human life lost there, and that is the important thing, that is the good thing. Well, the bad part of it is if this pretty much keeps on going, then every superpower, every nation who's a superpower will want to go about hoarding these. And then, I pray to God there isn't another big war coming. But if there is, then we will, see a lot of these war robots, guys. That's the sad part of it. And I'm sort of confident it really won't come to that. But if it does, then you can see a lot of robots there, guys. Let's just pray it doesn't come to that. Well, the next important thing, in between the robots and the Tesla autopilot actually came about Google's self-driving car, guys. So I'm not sure if you guys know about Google's self-driving car, but instead of just telling you what the self-driving car is, I just thought of telling you the Tesla autopilot directly, guys. Here, basically, this was the biggest breakthrough in terms of artificial intelligence technologies, because Tesla, as a company in the United States, co-founded by Mr. Elon Musk, started providing cars to the public where the car could drive itself throughout, it could park itself, and all you had to do is basically sit in the car, and every 15 minutes or so you had to hold the steering to make sure that you're not sleeping or something. So how amazing this is this. There is a photo on your screen right now on the top right, if you can check it out. That is an actual photo from the car's dashboard, guys. So it basically, instead of having a huge speedometer or something, it has this amazing display where it shows you, it detects all the cars around it, it detects rain, it detects the shortest distance, guys. You have to read about Tesla's autopilot, and I'm sure many of you guys will find it fancy, guys. In my personal opinion, if this is brought throughout the world, the capabilities of self-driving, that would be an amazing thing, guys. We've already seen a lot of companies actually bring out parking aids and autonomous parking, and it's basically called as parking help or whatever it is. A lot of companies like BMW, Skoda, and Mercedes, and all these big guys have already had autonomous parking capabilities. But when you think about when you think about how it goes about in every country, I'm sure it's very different. But then when you again contemplate about it, if this was brought to every country, it would be amazing, right? And then coming to 2019, guys, I mean, it's one more month to the end of 2019, and one amazing thing happened this year is pretty much in the field of medicine with respect to artificial intelligence, guys. Well, because artificial intelligence, as we all know it, has been helping the world in many different ways, and it has done so in the field of medicine as well. Well, it can be used to ameliorate reading time for digital breast tomosynthesis while maintaining or improving the accuracy of the reading. Well, what it's basically trying to tell us is that artificial intelligence is basically helping us to accurately make sure we detect cancer cells early on, guys. So this, again, we already know the victims of cancer, and we already know that it is an uncurable disease, and it takes a lot of time, endurance, patience, and so much more to go through with this, guys. But then if artificial intelligence can help us to check out what cells are harmful, what cells are harmless, basically what cells are benign, and so much more, then definitely this would help, right? Well, it has actually, the research has already been done, it is being implemented in many countries, and as a part of an artificial intelligence researcher, I am extremely proud of the fact that we've brought artificial intelligence down to the field of medicine, guys. So on that note, we need to check out what's next. We've seen all these different fields, and I'm sure there are hundreds of fields that I could have put in here due to the shortage of time, and pretty much to keep it to the scope of this tutorial for all of our viewers, I had to cut it down, guys. But take a second, head to the comment section, and let me know what you think about the views of artificial intelligences, and what are the other applications that you find amazing, guys. So on that note, we need to quickly check out what are the types of artificial intelligence, guys. If we keep diving into the depth of these, then it might actually go out of the scope of this video. So let me quickly tell you what are the types of artificial intelligence. Well, we have three different types of artificial intelligence, guys. One is narrow AI, next is general AI, and then super AI, guys. With narrow AI, it's basically it is the concept which is meant to assist or take over specific tasks and do it better than a human would do. Basically, an example of a narrow AI would be pretty much your mobile phone assistants, right? It can be Siri, Alexa, Cortana, and so much more. So you just make your work easier. Instead of opening the calendar app, setting your calendar, all you do is say, "Hey Siri, set my calendar for so and so." So that again is a very good example of narrow AI, guys. Coming to general AI, it's basically taking knowledge from one domain and transferring this exact knowledge into another domain. Well, general AI will almost require the intelligence of a human. If it will not require more intelligence, but you have to match the intelligence of the machine with a human or something very, I'm sorry about that, very close to that. Well, a good example to give you about this is, when you think about it, it's usually very advanced level of chatbots. I mean, sure, Siri, Alexa, all these are amazing chatbots. And then general AI is again a lot of mathematics involved here as well. A very good example would be AlphaGo and so much more, guys. So AlphaGo is basically again another computer which beat the world champion at this game called Go. I wouldn't say it has the cognition level of a human, but pretty much, even though it sounds simple on the outside, it is actually very complex. And even the world champion said that this is the most intelligent Go player that I've ever met in my life. So that brings us to super AI, guys. Super AI is on another level, guys. This is I would say artificial intelligence, mathematics, programming, all on steroids at once. Because when you think about it, super AI consists of machines that are extremely smart compared to humans. They can outrun a human, outthink a human, outgun a human, and so much more. For either good or bad reasons, super AI is pretty much either in good terms or in bad terms, guys. I've never seen neutral sentiment about super AI, but for the scope of this video, all you need to know is that super AI is pretty much the domain which consists of machines that are extremely smart when you compare it to humans, guys. So on that note, we need to quickly talk about what is the cause for all of these intelligence, guys. So what makes artificial intelligence intelligent? Well, in my personal opinion, the art of training a machine is amazing, guys. When you think about it, you can go about showing your computer images of cats and dogs and asking it to classify it for you. I mean, from our childhood, we have been trained by either school or by family members or friends to know what a cat looks like and what a dog looks like, but your computer does not. It might have taken you 3 years to figure out the differences, or 1 year to, let's say 1 year, you took 1 year to figure out the differences. Your computer will probably take 5 seconds or 10 seconds to figure out this entire thing what took you 1 year, guys. So when you think about it, everything from a very simple cat dog classifier all the way till achieving cognition, in my personal opinion, is just art, guys. Because at the end of the day, taking a concept which does not exist and bringing it right up to the level of a human being, and in a lot of people's personal opinion, human beings are the most intelligent species out there right now. Well, unless there are aliens and all the conspiracy theories. Well, jokes apart, well, coming back, bringing a machine up to the level of a human is definitely achieving cognition, and it's being done right, guys. So we need to think about the challenges we face when we go about making artificial intelligence intelligent, guys. There are 4 important points which pose as challenges. One is knowledge, guys. Because again, when you think about it, when you have to train a machine to figure out stuff on its own and hold these and implement it later is very difficult. This brings us to the second point. Well, if you think getting your machine to hold information and to make sense of it is difficult, then think about learning, because you can learn at a rapid pace, at a slow pace, or whatever it is. But getting your machine to learn, getting your machine to understand about a new concept, contemplate about it, work with it, analyze it, store it, and use it later is something very difficult. And this brings us to the next thing, which is problem solving. Even though you got your machine to have all the knowledge and learn very easily, it needs to go about implementing all of these in a perfect way, guys. Well, it can have the knowledge of all the worldly things which goes by, but what is the use if it cannot solve a problem? Because again, all the artificial intelligence terms or whatever points towards artificial intelligence mostly is a problem, right? Anything in the field of military, medicine, or so much more, we give the developers, the researchers, the scientists a problem so that they can solve it for us easily using artificial intelligence, right? So if your machine cannot solve a problem, then it is pretty much no good, guys. And this is actually very tough to achieve as well. And next comes obviously cognition, as I've been telling you for so many times right now, because again, bringing your machine up to the human level is again a very daunting task, guys. And in the middle of this, let me give you a very quick fun fact. I'm sure most of you guys might have heard of it already. Artificial intelligence has been used in terms of litigation, litigation and law and court and so much more as well. How? Well, I'm sure you guys have heard of JP Morgan, right? They are the banking giants of the world, and they came up with an artificial intelligence model which basically was used to go through and analyze some legal documents. You wouldn't believe the numbers, and the first time I read this a couple of months ago, I was taken aback, guys, because when you think about it, it reduced the workload from 360,000 man hours to a matter of seconds. Think about it, 360,000 hours of job. This is what it takes a human to do it. But as soon as they implemented that model, it just took the model a couple of seconds to do it. And I have read that the model is very accurate as well. So when you think about it, think about the odds, 360,000 hours and a couple of seconds. So, if you didn't know this fact, then I hope you find this very entertaining, and I hope you guys feel very interested about this fact at the same time, because we already know artificial intelligence is being used in every field, but not many of us know how it was actually used in litigation, right? So I just found it very interesting to tell you guys about that. And this brings us to the dark side of artificial intelligence. Well, is there a dark side? Well, you remember Elon Musk, right? The founder of Tesla, the founder of SpaceX, the founder of SolarCity, and so much more. He's basically a billionaire entrepreneur, guys. Well, he says that, at least when there's an evil dictator, that human is going to die. But for an artificial intelligence being, there will be no death. It will live forever. And you will have an immortal dictator from which, you can never escape. So, I am sure our views on this particular topic, we can debate about it all day, all night, and we're going to have very different opinions about this. And we need to respect people with very different opinions about this, because at the end of the day, all of these, what we look at as different opinions actually come under one umbrella, and it helps develop artificial intelligence in the right way, guys. So, I hope there is a good... I am in fact, I am sure that there is a good way and a good path for the development of artificial intelligence, but you can never know at any point of time. Well, according to a lot of experts, that it might take a turn for the bad as well. Again, let's hope that it doesn't go there. And on that note, we'll quickly bust a couple of myths and facts, guys. So the myth is that superintelligence by the year 2100 will be inevitable. Well, when you think about it, it might happen right now, it might happen in a decade, in a couple of years from now, or it might never happen at all. To achieve super intelligence, again, as we've been talking, is a very, very, very challenging task, guys. And the myth is that, only people who do not know about Luddites are basically people who are not very well informed. That only these people are worried about artificial intelligence and all of its bad things for the future. Well, not exactly, because even many top artificial intelligence researchers are concerned about how it's going to go about in a good way or in a bad way as well, guys. Another myth is that artificial intelligence is turning evil, it is turning conscious, and so much more. Well, the actual worry that we need to go about doing is, artificial intelligence actually turning to be very competent with a goal that would be misaligned with our particular goal. So it might take a very staunch deviation from what we set it out to be, and it could do something on its own. So that is the actual worry when you compare to the myth. And then to bust another couple of myths, people say that robots are being the main concern, like those Terminator movies and whatnot. Well, again, here as well, misaligned intelligence is again the main concern, because we live in a world of technology. In every device, every home, I'm sure most of the world is connected through an internet connection, right? So you will not need an actual robot in case if something goes wrong as well. So that is something to think about. And then artificial intelligence cannot control humans is a myth. Well, intelligence actually enables control. So, we do this very sad thing where we trap animals in cages and create zoos around them. I mean, I'm not much of a zoo fan. I hope I do not offend anyone regarding that. So we are smarter than tigers and all of these other animals, so we can go about controlling them because we are smarter. Now think about a machine which is smarter than humans. It can go about controlling us as well, right? So that is a fact to think about again. So machine cannot have goals. Well, this is wrong, because again, let us say two planes are fighting in the air. It's called as a dog fight. So two planes are fighting, and the plane behind just launched a missile. If you have seen in a lot of movies that I'm sure you would have, this missile exactly knows where the plane is and to go hit it. This basically works on the concept of heat seeking. Well, it has detectors in the front of the missile which will find the hottest thing it can see and then just go hit it. So the hottest thing in a plane is in the plane which is in front is its engines. So this will basically chase the plane's engines and hit the engines. So that is a heat seeking missile for you. And then the next mythical worry is that super intelligence is just years away. Well, not really. It is a couple of decades away, as I've pretty much told you. But again, it might take way longer than 2 decades, 3 decades, 4 decades, and so much more to, just to make it safe for us to use as well, guys. So that is all with the dark side concepts that I had to just inform you guys in case you weren't knowing. So this brings us to the next concept, which is basically the domains in which artificial intelligence has its hold, guys. Again, number one, as I've been saying for a long time, is healthcare, guys. That is the best thing that I've seen artificial intelligence being put to, and there are so many things live as well. So it has been so subtly integrated into your lives that you would not even know it is there. When you think about it, probably you just open a health app installed on your mobile phones or your computers. You'll be talking to a chatbot instead of a human, and you wouldn't know it. Most of the time you can just set an appointment with your doctor and ask more information about your appointments and so much more by just talking to a machine instead of talking to a human on the other side, guys. And from that till helping detection and curing of cancer is again an amazing thing in my opinion. And the second thing is stock trading, guys. As an investor personally, I could sort of relate on this as well, because if stock trading again is again a very tipsy-turvy world, right? So sometimes you lose money, sometimes you make a lot of money. But if you had if you had a different approach, if you had a more intelligent being to look at graphs, to look at data, and to make better sense of it than an expert trader, then that would be an amazing thing, because you could end up making more money and losing less money at the same time, right? So this brings us to another next thing, is sales, guys. Well, this is a personal recommendation from me, because here at Intellipaat, let me tell you how we implement machine learning and artificial intelligence for our sales team, guys. So we get about 10,000 or 15,000 sales leads every single day. Imagine calling those 10-15,000 people, guys. So it would be a daunting task to go about doing it, but we have a machine learning model which is in place, which basically helps filter out these people, categorize them, and make sure it basically makes sure that they get in touch with our course advisors, and then later our course advisors basically help them get the course that they were actually looking for, guys. So this makes the entire process of going through the part of sales very interesting, very simple, and we get lot of analytics from that as well, guys. So this is us at Intellipaat using artificial intelligence to help out you learners as well, guys.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5,000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Now, let's actually get a bit deeper and understand what is intelligence. So, intelligence can be defined as one's capacity for understanding, one's capacity for self-awareness, one's capacity for learning, and one's capacity for problem solving. That is, how well is something or someone able to understand? How well is someone able to learn new things? And how well is someone able to solve problems by themselves? So, now that we know what is intelligence, let's understand what is artificial intelligence. So, when you apply the same intelligence to machines, this is known as artificial intelligence. Now, just imagine there's a machine which can understand things which are normally understood by human. There is a machine which is self-aware, and there is a machine which can solve problems by itself. Now that's just amazing, isn't it? Right. So this is the artificial intelligence which I'm talking about. So now that we also know what is intelligence, I'll ask another question. So tell me, what is it that makes humans intelligent? Well, we as humans can reason, we as humans can learn, we can perceive, we can solve problems, and we also have linguistic intelligence. That is, we can figure out what is someone else saying, and we can also understand the grammatical intricacies of different languages. So, again, my question would be, what if a machine could exhibit all of these factors normally shown by a human? Again, that's just amazing, isn't it? So this is what is known as artificial intelligence. So a machine which can show traits normally shown by a human, that is known as artificial intelligence. Alright, so now that we're clear with artificial intelligence, let's segregate AI, ML and DL. So normally most people get confused between artificial intelligence, machine learning and deep learning. So this is where I'm going to help you out in understanding the difference between these three. So we have AI at the top, and you can consider machine learning and deep learning to be subsets of AI. So again, machine learning and deep learning are just ways to achieve artificial intelligence. So I'll restate it again. Machine learning and deep learning are just ways to achieve artificial intelligence. Now, machine learning is that part of artificial intelligence which aims to teach the computers the ability to do tasks with data without any explicit programming, right? So we don't need to do any explicit programming, and the algorithms do tasks by themselves. And in ML, we mostly use numerical and statistical approaches to achieve artificial intelligence. And then we have deep learning, which is actually a subset of machine learning. So first we have AI, and then we have ML, and then we have DL. So deep learning comes in where machine learning fails. And we apply deep learning through something known as artificial neural networks, about which we'll obviously learn later. Right. So now let's understand artificial intelligence in a bigger set. So as I've already told you, artificial intelligence is the superset under which comes machine learning, under which comes deep learning. And then machine learning and deep learning are basically ways to achieve artificial intelligence. Now these are the different areas of research of artificial intelligence. So you have ML. Again, a part of ML is deep learning. Then we have natural language processing. So over here we basically understand what is spoken or written by a human. And then we have speech, where we either translate the speech to text or we translate the text to speech. The next subfield is robotics, and then we have autonomous vehicles under robotics. So Google's self-driving car is an example of this over here. So now that we've also understood the difference between artificial intelligence, machine learning and deep learning, let's see different examples of machine learning around us. So most of you would have shopped on Amazon. Now, when you go into Amazon, you see that there are some products recommended to you. Now, how do you think that would happen? So this is something known as recommendation engine. And recommendation engine is nothing but a component of machine learning. So let's say you and your friend buy similar products. So your friend buys 5 products and you buy 3 products. Now out of those, whatever 3 products you buy are same as what your friend buys. So let's say the common products are an iPhone, a back cover for the iPhone, and a Bluetooth headset. Now let's say the other 2 products bought by a friend would be a MacBook and a mouse. Now since there are 3 products which are same between you two, this is why the products which your friend has also bought, those are the products which will be recommended to you. So on the basis of the commonality between you and your friend, you will be recommended a MacBook and a mouse as well. So this is nothing but a concept of machine learning. And then we have Amazon Alexa. Amazon Alexa is a really good example of speech recognition. When you say Alexa, turn on the lights, it'll turn on the lights. When you say Alexa, book a ride for me, it'll do exactly that. When you say Alexa, order a cheese pizza, and that is exactly what Amazon Alexa will do. Now Alexa is just a machine, right? But when you say do something, order a pizza, book a cab for me, turn on the lights, how is the machine able to understand all of this? So the idea behind this is speech recognition, and that is again a component of machine learning. And then we have Netflix's movie recommendation. So let's say you watch two TV series. First TV series is Friends and the next TV series is Big Bang Theory. And since you watch these two TV series which belong to the genre comedy, that is why maybe you will be recommended How I Met Your Mother, or you can be recommended Silicon Valley or some other TV series belonging to the comedy genre. So this again is machine learning. And then we also have Google traffic prediction. Let's just say you're traveling in your car and there is huge traffic there. You desperately want to get out of the traffic. So you turn on Google Maps and Google Maps tells you the best direction from where the traffic would be the least. Now, how does Google Maps do this? This again is machine learning. Now, let's look at the subcategories of machine learning. So we have supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, you can consider that the learning is guided by a teacher. So we have a data set which actually acts as a teacher, and its role is to train the model or the machine. So once the model gets trained, it can start making a prediction or decision when new data is given to it. So let's take this example. So over here, we are training this machine by giving it samples of data. So over here, the data is nothing but different images of apple. And along with each image of apple, we are also giving it the label of the image, right? So this image goes with its label, which is apple. Again, this image goes with its label, which is apple. Again, the same with these two, right? So we are teaching this machine that whenever it sees an image something like this, it is nothing but an apple. And after time, when we give it a new data from whatever learning it has done, it will predict whether it's an apple or not. So on the basis of its learning, this machine predicts that there is a good possibility. There is actually 97% possibility that the image which has been fed to the machine is nothing but an apple. So a use case of supervised learning could be spam classifier. So spam classifier basically means that whether the email which we get it's a spam or not. And that is done on the basis of different textual parameters. So let's say a genuine email wouldn't contain too many exclamation marks. It wouldn't contain a catchy headline and so on. But on the other hand, if it's a spam email, maybe it will contain a lot of exclamation marks with maybe a lot of numbers, and it'll have statements like, hey, congrats, you've won a lottery, or hey, could you help me out? So this spam classification is basically an example of supervised learning. Then we have unsupervised learning. So in unsupervised learning, the model learns through observation and finds structures in the data. So once the model is given a data set, it automatically finds patterns and relationships in the data set by creating clusters in it. So what it cannot do is add labels to the cluster. Like it cannot say this is a group of apples or mangoes, but it will separate all the apples from mangoes. So over here we have this set of images. Now this unsupervised learning model which is applied on this, it will segregate these fruits on the basis of similar characteristics. So over here we have segregated these 4 into one cluster, these 3 into second cluster, and these 3 into the third cluster. Now even though the unsupervised learning does not have any labels, it has still segregated these three into three clusters, right? So the machine over here does not know that these are apples or these are oranges or these are bananas. Yet it has segregated these three on the basis of similarity of characteristics. So it found out that these four objects are similar to each other, and there is quite a bit of variability when it comes to these four objects and these three objects. Similarly, this machine was able to figure out that these three objects, they are quite similar to each other, but when compared with these three objects, they are very dissimilar. So this is the underlying concept of unsupervised learning. And a good example of unsupervised learning would be again Netflix movie recommendation. So over here, the movies are segregated on the basis of different genres. So over here, TV series like Friends, How I Met Your Mother, and Silicon Valley are clustered into one group because those come into the same category. Similarly, movies such as Secret Superstar and Dangal could come under the same category because they have the same lead actors. So over here, we are segregating the movies on the basis of similar characteristics, even though there are no labels in it. And it's finally time for the third machine learning type, which is reinforcement learning. So over here, there is an agent and there is an environment, and the agent interacts with the environment and finds out what is the best outcome for it. So it basically follows the concept of hit and trial method. The agent is rewarded or penalized with a point for a correct or a wrong answer. And on the basis of positive reward points gained, the model trains itself. So let's take this example. So over here, this self-driving car would be our agent and the road is the environment. And this car is interacting with this environment. So it will observe the environment and it has two choices over here. So either to go straight or turn right. Now, let's say this agent or the self-driving car decides to go straight. Then what happens is it goes and bangs straight into this barricade. So then it realizes that the action taken by it was not in its best interest, and that is why it is penalized. So since it is penalized, it realizes that the action taken by it was wrong, and that is why from the next time onwards, it will do the opposite action. So instead of going straight, it will take the right turn. And when it takes the right turn, it realizes that the road is correct and the agent is rewarded. So this is how reinforcement learning basically works. So the agent interacts with the environment, it takes an action, and if the action turns out to be incorrect, it is penalized. And if the action turns out to be correct, it is rewarded. So this cycle goes on and on till it completely learns its environment properly. And the best use case of reinforcement learning is again self-driving car. So companies such as Tesla and Google are working on these self-driving cars.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
So just to sum it off, these are the three different types of machine learning algorithms. So we have supervised, unsupervised, and reinforcement machine learning. So under supervised, we have regression and classification, and in unsupervised, we have clustering techniques, association analysis, and hidden macro model. And then the third is obviously reinforcement learning, which works on trial and error method. And if you want to do some really cool machine learning projects, you can check the sites out. Now let's look at some limitations of machine learning. So when it comes to machine learning algorithms, they would require massive stores of training data. So again, as I've told you, machine learning is totally based on the data which it has. So if you have more amount of data, only then it will be able to give correct accuracy. So let's say you take in very small amount of data, and there's a good possibility that the results which you're getting are very biased or very incorrect. And also, error diagnosis is quite difficult when it comes to machine learning. because again the amount of data is very huge, and wherever there's a mistake you'd have to go through the entire algorithm which you've written and then find out that particular mistake by yourself, which is very difficult. And also when it comes to machine learning algorithms, they're not really that creative. So these ML algorithms are built only for one specific purpose. So let's say I'll build a machine learning model which will predict whether it will rain or not today. Now, if I want to use the same model to predict the stock prices, that will not work, right? So basically one model is built only for one particular task. So this is the lack of creativity that I'm talking about when it comes to machine learning. And also there are a lot of time constraints as the model has to learn through a lot of historical data. So that was everything about machine learning. Now let's start off with deep learning. So deep learning is a subset of machine learning where it learns through data representations as opposed to task specific algorithms. So we saw that the drawback in machine learning models was that the models are specific to only one particular task. But this is not the case with deep learning models, as these deep learning models are based on the data representations, and these deep learning models are mostly built with something known as deep neural networks. So this is how a deep neural network looks like. So these deep neural networks completely learn the data which is fed to it. So this is the data. So let's say if this image of woman is fed as the data to the deep learning model, then it will completely extract all the features of this data by itself. Again, the difference between ML and deep learning over here is that the feature extraction in machine learning is manual. But when it comes to deep learning, the feature extraction is automatic. So the deep learning model automatically extracts all of the features associated with that image. And when new images are fed to it, it automatically is able to tell whether the image is same to this or not. So this over here we have a graph which tells us how does performance vary with respect to the amount of data. So what happens in machine learning is that as we keep on increasing the data, the performance increases only up to a particular threshold. After that, if we increase any more data, there is no increase in performance. So this is another problem when it comes to machine learning. But on the other hand, when it comes to deep learning, the more amount of data you give it, the better will be its performance. And that again is because deep learning is based on learning data interpretation. So the more data you give it, it will automatically learn all those features of the data by itself, and it will be keep on increasing its performance gradually. Now let's look at some applications of deep learning. So speech recognition is one application of deep learning. Now you need to understand that you cannot build speech recognition applications with machine learning. So this is where machine learning fails and deep learning comes in and helps you to build speech recognition applications. Also another application of deep learning is self-driving cars. So we see over here that the person is just sitting. He is not even touching the steering wheel and the car is driving by itself. So just an amazing application of deep learning. And then we have language translation over here. So this again is a part of deep learning. So over here we are typing something in Spanish and it is being automatically converted into English. So we also have visual translation over here. So over here this text or this board is in some random language, and this app over here which uses deep learning automatically converts this visual into English. So those were some applications of deep learning. Now let's actually understand how does deep learning work. So most deep learning methods use neural network architectures, and that is why deep learning models are often referred to as deep neural networks. So a deep neural network basically has these three models: an input layer, the hidden layers, and the output layer. And the term deep usually refers to the number of hidden layers in the neural network. So traditionally, neural networks only contain 2 to 3 hidden layers, while deep networks can have as many as 150 hidden layers. Now that's a very huge amount, isn't it? So deep learning models are trained by using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. So all of the input data is given to this input layer, and this input layer automatically extracts the features by itself. Now that data is sent to this hidden layer, which performs all sorts of processing tasks, and then the final result is given out through the output layer. So now let's also understand what exactly is a neural network. So a neural network is a computing model whose layered structure resembles the network structure of neurons in the brain with layers of connected nodes. So it can learn from data which can be trained to recognize patterns, classify data, and forecast future events. So the neural network is based on the biological neural network of our brain. So that is why it is given the name neural network. So the layers are interconnected via nodes or neurons, with each layer using the output of the previous layer as its input. So its main function is to receive a set of inputs, perform calculations, and then use the output to solve the problem. Now, as I've already said, these artificial neural networks are based on something known as a biological neural network. So, our biological neural network has dendrites, cell body, and axon. So dendrites are where the input is taken, cell body is where the processing is done, and axon is where the message is transferred to other neurons. And the same thing happens in artificial neural network as well. So first we give in the data, that data is processed, and then the final processed result is given out as the output. So over here, let's say we train the data with images of cat, and the labels would be either cat or not cat. After that, we give in a new image of a cat, and then we basically try to predict whether the model correctly classifies this as cat or not cat. And since the model has learned the data properly, it correctly classifies this image as cat. Now, there are many ways of knitting the nodes of a neural network together, and each way results in a more or less complex behavior. Possibly the simplest of all topologies is the feed-forward network. So when feed-forward neural network, signals flow in one direction without any loop in the signal paths. And typically, artificial neural networks have a layered structure. The input layer picks up the input signals and passes them on to the next layer, known as the hidden layer. And there can be more than one hidden layer in a neural network. And at last comes the output layer that delivers the result. Now, the first question to pop into your head would be, what is the inspiration behind these artificial neural networks? Well, the answer to that is the biological neural network of our brain. So let us first understand the architecture of a biological neuron. So as you can see in the slide, our biological neuron has these three main components. So we have the dendrite, the cell body, and the axon. These dendrites receive the signals, and the cell body processes these signals, and the axon finally sends out these signals to other neurons. So just like the biological neuron, the artificial neuron has a number of input channels, a processing stage, and one output that can fan out to multiple other artificial neurons. So now let's understand these artificial neurons in detail. These artificial neurons are the most fundamental units of deep neural network. It takes an input, processes it, passes it through an activation function, and returns the output if the condition is met. Or else it will process it again until you get the correct output. And such type of artificial neurons is called as a perceptron. So they are basically like a linear model which is used for binary classification. So as the figure shows, we have x1, x2, x3 and going on till xn as inputs in the input layer. Now, to which we add the weights and the bias that are randomly selected. So here we have W1, W2, W3 going on till Wn as weights. So we multiply these weights with the corresponding inputs and add all the values together, and finally we add bias to that sum. So this final sum is passed through an activation function which finally gives us the output. So let us see this in detail. So here we have 3 arrows which correspond to the 3 inputs coming into the network. Now for these 3 inputs, we have corresponding weights associated with them. So input 1 is associated with a weight of 0.7, input 2 is associated with a weight of 0.6, and input 3 is associated with a weight of 1.4. Now, these inputs are multiplied with their respective weights and their sum is taken. So if the 3 inputs are x1, x2 and x3, the sum would be x1 into 0.7 plus x2 into 0.6 plus x3 into 1.4. And to this sum, we add an offset which is called as bias. So this bias is just a constant which is used for scaling purpose. Now let us understand the concept behind these weights. So these weights basically determine the relative importance of the inputs. So let's say we have 2 inputs, humidity and wearing a blue shirt. So here we can see that wearing a blue shirt has almost no correlation with the possibility of rainfall. So that is why the weight assigned to input x2 would be low in order to bring down its importance. Now let us see why do we need activation functions. So consider this scenario where you have 2 different classes. One class is represented with triangles and the other class is represented with circles. Now let's say I ask you guys to draw a linear decision boundary which can separate these 2 classes. So is that really possible? Can we draw a linear line which can segregate these 2 classes? Well, the answer is obviously no, isn't it? So let me tell you guys how can we do this. So we'll have to add a third dimension to create a linearly separable model which is easy to deal with. So the logic is, when you're going from 2D to 3D, you're making your equation non-linear. So with the third dimension, I have introduced non-linearity in our data, which helps in creating a linearly separable model. And in real-world situations, you don't always get linear problems. So you should know how to deal with non-linear problems as well. And this is where activation functions help us to convert the linear equation to non-linear form. So these activation functions bring in non-linear functional mappings between the input and the response variable. Their main purpose is to convert an input signal of a node in an artificial neural network to an output signal. And if we do not apply an activation function, then the output signal would just be a simple linear function.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section.
Neural network. Then we have the leaky ReLU, which is just a modified version of ReLU. So the leaky ReLU, instead of just completely removing the negative part, it just lowers the magnitude. And finally, we have the softmax function, which is ideally used in the output layer for classification problems. So the softmax function basically gives a set of probability values for each class of the output. And that particular class, which would have the maximum probability, will be our output class. So that was all about activation functions. Now let us learn more about perceptrons. So like we were taught how to behave in certain conditions, perceptrons also require training. So they have a learning algorithm through which they produce the output. By training a perceptron, we try to find a line, plane or some hyperplane which can accurately separate these 2 classes by adjusting the weights and biases. So consider this image where we give the dogs and horses as input. So here after the first iteration, error value is 2 since the horse has been classified as dog and there is one dog which is placed in the horses class. And in the second iteration, the error value is reduced to 1 as it is just the dog which is classified as a horse. And finally, in the third iteration, we get the correct output as the perceptron has been trained well with no error. So all the dogs have been placed in one class and all the horses have been placed in one class. Now let's understand the perceptron training algorithm. So this perceptron over here receives multiple inputs and each input is initialized with a random weight. So after these, we multiply these weights with their corresponding inputs and then we get the sum. Now this input is passed through the activation function which would give us a non-linear output. So this process until here is known as feed forwarding. Now, if the output which we get is not optimum, we calculate the error in prediction and then go back and then update the weights and bias. So this process where we go from output to the input layer is known as backpropagation. And we keep on backpropagating until we get the desired output. So that was the perceptron training algorithm. Now let's have a look at the benefits of using artificial neural networks. So the artificial neural networks can learn organically. This means an artificial neural network's outputs aren't limited entirely by inputs and results given to them initially by an expert system. So artificial neural networks have the ability to generalize their inputs. This ability is valuable for robotics and pattern recognition systems. Artificial neural networks also help in nonlinear data processing. So nonlinear systems have the capability of finding shortcuts to reach computationally expensive solutions. These systems can also infer connections between data points rather than waiting for records in a data source to be explicitly linked. This nonlinear shortcut mechanism is fed into artificial neural networking, which makes it valuable in commercial big data analysis. Artificial neural networks also have high potential for fault tolerance. When these networks are scaled across multiple machines and multiple servers, they are able to route around missing data or servers and nodes that can't communicate. And these artificial neural networks can also self-repair themselves. So if they're asked to find out specific data that is no longer communicating, these artificial neural networks can regenerate large amounts of data by inference and help in determining the node that is not working. This trait is useful for networks that require informing their users about the current state of the network and effectively results in a self-debugging and diagnosing network. Now, to implement these artificial neural networks, we would need the help of a deep learning framework. So the first question to pop into your head would be, what are the different deep learning frameworks available? So today we'll cover just that. So let's start with TensorFlow. So TensorFlow is arguably one of the best deep learning frameworks that we have today. It is an open source software library developed by the researchers and engineers from the Google Brain team for high performance numerical computation. One well-known use case of TensorFlow is Google Translate. So Google Translate is coupled with capabilities such as natural language processing, text classification, forecasting, and tagging. So TensorFlow basically comes with two tools, TensorBoard and TensorFlow Serving. So building massive deep neural networks could be complex and confusing. This is where we can use TensorBoard to visualize our TensorFlow graph and plot quantitative metrics. And then we have TensorFlow Serving, which is a flexible, high-performance serving system and can be used for rapid deployment of new algorithms while retaining the same server architecture and APIs. So now let's look at the next deep learning framework, which is Keras. So Keras is actually a high-level API which can run on top of other deep learning libraries such as TensorFlow, Theano, or CNTK. And with the help of Keras, we can implement both convolutional neural networks as well as recurrent neural networks. And the best thing about Keras is, model building is extremely easy. It's like stacking layers on top of each other. So next, we have PyTorch, which is a scientific computing framework developed by Facebook. So we can get from the name itself that PyTorch is Pythonic in nature. That is, it can leverage all the services and functionalities offered by the Python environment and also smoothly integrates with the Python data science stack. Another great feature of PyTorch is that it offers dynamic computational graphs which can be changed during runtime. This is highly useful when we have no idea how much memory will be required for creating a neural network model. And the next deep learning framework is DL4j. So unlike deep learning frameworks which we saw till now, which were all based on Python, Deep Learning 4j is a deep learning programming library which is written for Java and the Java virtual machine. And the biggest advantage of DL4j is it includes inbuilt integration with Apache Hadoop and Spark. So it helps in getting state-of-the-art results on image recognition tasks. So it shows matchless potential for image recognition, fraud detection, text mining, parts of speech tagging, and also natural language processing. And finally, we have MXNet. So MXNet is a deep learning framework developed by Apache Software Foundation specifically for the purpose of high efficiency, productivity, and flexibility. And the beauty of MXNet is that it gives users the ability to code in a variety of programming languages, such as Python, R, Julia, and Scala. This means that you can train your deep learning models with whichever language you're comfortable in without having to learn something new from scratch. And this deep learning framework is known for its capabilities in imaging, speech recognition, forecasting, and NLP. So when you hear the term TensorFlow, the first question to pop into your head would be, what exactly is a tensor? So in TensorFlow, data is represented in the form of tensors. Simply put, a tensor is a multi-dimensional array in which data is stored. So you can consider these tensors to be the building blocks in TensorFlow. Now, these very tensors are given as the input to the neural network. So as I've said, a tensor is nothing but an n-dimensional array. So the number of dimensions used to represent the data is known as its rank. So if a tensor has just one element, in other words, if it has just magnitude and no direction, then its rank will be 0. If a tensor has magnitude and direction in one plane, then its rank will be 1. Similarly, if a tensor has magnitude and direction in two planes, then its rank will be 2. And this goes on higher up the order. Now, TensorFlow, as the name states, is a combination of two words, tensor and flow. Here, the data is stored in tensors, but the execution is done in the form of a graph. So this is not like your traditional programming where you just write a bunch of lines and everything gets executed in sequence. So first, you'd have to prepare this computational graph, and then this computational graph is executed inside something known as a session. Now, in this computational graph, all the mathematical operations are depicted inside the nodes, and all the tensors are represented on the edges. So the entire computation process is done in two stages. In the first step, the code is depicted onto the computational graph, and in the second step, a new session environment is started and the graph is executed inside this session. So that was all about the computational graph. Now let's look at the program elements in TensorFlow. So we have three program elements: constant, placeholder, and variable. So let's start with constants. So constants are program elements whose value does not change, or in other words, the value is fixed. So let's head on to Jupyter Notebook and work with these constants. Right, so my first task would be to import the TensorFlow framework. So I'll type import TensorFlow as TF. I'll click run. So let me just wait till the import is done. Right, so we have successfully imported the TensorFlow framework. Now, as I've said, let's go ahead and start working with the constants. So let me just type in constants over here. So I'll create the first constant and name this constant as con1. Now this is how we can create constants in TensorFlow. So I will use this TF and then put in a dot and then type in constant. Now inside this, I will give the value of the constant. So let's say the value is 10. So this is an integer type constant. Now similarly, I'll also create a floating type constant and I'll store this in con2. So I'll type tf dot constant and the floating value would be 3.14. Now after this, I'll create a string type constant. So again, this would be tf dot constant, and the string which I'd be giving would be this is Sparta. And finally, we have a Boolean type constant, and I'll store this in con4. So this will be tf dot constant, and let's say the value is false. Now I'll run. Now let me print all of these values. So I'll use the print function, and then I'll go ahead and print all of these values, con3, con4. Right. So we see that this first constant is a tensor of type integer. The second constant is a tensor of type float. This third constant is a tensor of type string, and this fourth constant is a tensor of type boolean. Now we see that we only have the data types of all of these tensors, but we don't have their values. This is because, as I've already told you guys, we have to create a computational graph and then execute that computational graph inside a session. But till now, we have not started our session. So let's go ahead and start a session first. So I'll type sys equals tf dot session, and I'll hit run. Now I will run all of these inside this session. So I will type sys dot run, and let me go ahead and run all of these: con1, con2, con3, and con4. So this time we have the values of all of these tensors. So the value of constant 1 is 10, the value of constant 2 is 3.14, the value of constant 3 is this is Sparta, and finally the value of constant 4 is false, right? So first we'd have to create all of the constants, then we'd have to create a session, and inside this session we'd have to run all of these constants. Now let me go ahead and perform some simple operations on all of these constants. So let me just type in operations over here. So I'll do a simple addition operation. So I'll type addition over here. And let's say the value of the first constant is 20. I'll put a plus symbol, and then I'll take in the next constant, and the value of the second constant would be 30. So I am basically adding two TensorFlow constants. The value of the first constant is 20, the value of the second constant is 30, and I'm storing that result in addition. Similarly, I will multiply these two constants now. So multiplication tf dot constant. So I'll give the value of 20. Now I'll put the asterisk symbol, and then this would be tf dot constant of 30. So this time I'm multiplying these two values, right? So I'll hit on run. So now again, if I'd have to see the resultant addition and multiplication values, I'd have to run these two inside a session. So I'll type sys dot run, and then put in these two values over here, addition and multiplication, right? So we see that 20 plus 30 gives us an addition value of 50. And similarly, when we multiply 20 with 30, we get a result of 600. Right. Now, so this was basic operation with scalars. And we already know that tensors can have higher dimensions. So let's go ahead and perform addition and multiplication with these higher dimension tensors. Right. So again, I'll just put in addition over here. And I will take in the first constant, and inside this, I will give in a list of values. So let's say I will take in 1, 2, 3, 4, and 5, and I will add this list with the next constant. And this time, the second constant has the values of 5, 4, 3, 2, and 1. Similarly, I'll also multiply. So multiplication equals tf dot constant, and this will have values, let's say the same values, 1, 2, 3, 4, and 5. Let me put a comma over here. Right. Now I'll put the asterisk symbol. Again, I'll type tf dot constant, and I will give in the list of the values 5, 4, 3, 2, and 1. Now I'll hit run. Again, I need to run these two inside a session. So sys dot run, let me put in addition over here. After that, I would also need the multiplication value. Right, so this is a result. So when we add 1 plus 5, we get 6. When we add 2 plus 4, we get 6. Similarly, when we add each of the corresponding elements with these elements inside the list, we get all of the 6's over here. Now let's take this multiplication result. So over here, when we multiply 1 with 5, we get 5. When we multiply 2 with 4, we get 8. 3 cross 3 gives us 9. 4 cross 2 gives us 8. And again, 5 cross 1 gives us a 5. So this was addition and multiplication with respect to lists. Now let me also do a simple operation on strings. So let me take in the first string and name it as str1. So this is a constant. So tf dot constant. And let's say I type over here, I love, and then I give a space. Now I will take in the second string, which would be str2. And inside this, and again, this would be a constant. So tf dot constant, and the value of this constant would be TensorFlow. Right. Now I will run this and let me execute this inside a session. So ses dot run of str1 plus str2. So the result which you get is I love TensorFlow, right? So the first string is I love, and then there's a space, and the second string is TensorFlow. So when I add these two strings, the resultant is I love TensorFlow. Right, so that was all about constants. And then we have placeholders. So when it comes to placeholders, we don't have to provide an initial value and can specify it during the runtime. So this allows us to build our computational graph without needing the data. And this is how we can create placeholders. So tf.placeholder is the syntax. And inside that, we just give the data type of the variable, which we will substitute later on during execution. So let's head back to Jupyter and work with these placeholders. So let me just type in placeholder over here. So let me create my first placeholder. So I'll name that as A and tf dot placeholder. And this would be of integer type. So tf dot int 32. Now I will create another variable which would be b, and the value of b would be actually a cross 2. So let me run this. Now I will run these two inside a session. So ses dot run, and I want to see the result of b. So I'll put in b over here. Now since we know that a placeholder takes in a value during runtime, so this is when I'll feed the value to this placeholder A over here. Now to do that, I would have to create something known as a feed dictionary. So feed dict equals, let me create a dictionary over here. So it would be A, and the value which I'll be giving to A would be, let's say, 5. Now let me run this and let's see what do we get. Right. So during the execution time, I have assigned a value of 5 to A. And when we multiply this 5 with 2 over here, we get the value of B, which is 10. Right? So all of this is happening during runtime because with the help of a placeholder, we can assign it a value during execution. Now, similarly, let me go ahead and give a list of values over here. So instead of 5, let me give the list of values 1, 2, 3, 4, and 5. Now I'll run this. So over here, 1 cross 2 gives us 2, 2 cross 2 gives us 4, 3 cross 2 is 6, 4 cross 2 is 8, and 5 cross 2 is 10. So you get an array of values during runtime. Now similarly, let me also create a placeholder for strings. So I'll type string placeholder over here. So now let me create this variable and name this as string name, and this would be your placeholder. So tf dot placeholder, and I am taking in a string. So tf dot string. Right. Now let me create another string over here. So the name of this string would be my name, and let's say the value of the string is I am. Alright. Now let me run this. And I'll execute this inside a session. Ses dot run, and I want the result of my name when I add it with respect to string name. Now let me also create a placeholder for strings. So I'll just type string placeholder, and let me create the first placeholder. So I'll name that as str1 name, and since this is a placeholder, tf dot placeholder, and I will be giving in a string during execution time. Now I'll also create another string value over here and name that to be my name, and the value of this string is I am, and then I'll give a space. Right, so now I'll hit run and let me execute this inside a session. Now let me also create a placeholder for strings. So this will be string placeholder. Right, so let me create this placeholder. I'll name this as str name, and since this is a placeholder, I need to use tf.placeholder, and I will be assigning a string to this during execution time. Now I will also create another string which would be my name, and this would be equal to I am, and there's a space, and I will be adding this with str name. So let me hit run. Right, now I'll execute this inside a session. So for that, I'll type sys dot run, and I want the result of my name. So I'll just put in my name over here, and then I'll provide the feed dictionary. Feed dict equal to, let me put in the dictionary over here, and I will assign the values of str name over here. Right. So the values of str name would be Sam, Bob, and Charlie. Now let me hit run and let's see what do we get. Right. So what we are basically doing is we are adding this with the placeholder value over here, and we are giving the values during the execution time. So I am Sam, I am Bob, and I am Charlie. Now these three values are coming from this feed dictionary during the runtime. Right. So this is all about placeholders. And finally, we have variables. So a variable is just a program element which allows us to add new trainable parameters to the graph. And this is the syntax to create a variable. tf.variable, and then we give the value, or we initialize the value, and then we specify the data type of that variable. Right, so let's head back to Jupyter now. I'll just type in variables over here. Right, so let me create my first variable, and the name of that variable would be var1, and we can create a variable like this, tf.variable. So guys, you need to keep in mind that this V over here is actually capital. Right. So now after this, I would have to assign a value to it. So let's say I assign this variable a value of 20, and this is of integer type. So tf.int32. I'll run this. Now another thing to be kept in mind is whenever we are declaring values in TensorFlow, they have to be initialized. So this is how we can initialize all of the variables. So we have something known as global variable initializer. And when we invoke this function, all of the variables which we have declared would be initialized. I'll hit run. So now let me execute this inside a session. So sys.run of init, and I have initialized this variable over here. Now let me also go ahead and run that variable, sys.run var1. Right, so we have the result of var1, which is 20. Now since this is a variable, the value of a variable can be actually updated. So let me go ahead and update the value of this. So I will name this as updated var1, and the function would be tf.assign. And inside this, the first parameter would be the variable which I'd want to update. And after that, I need to give the value to which I'd want to update this. So I want to make this value of 20 to 25. Right, now I will run this. So now this is actually a variable. We can actually update the values. So let me go ahead and do that. So the name of the updated variable would be, let's say, updated var1, and the function for that would be tf.assign. And this takes in two parameters. The first parameter would be the variable which we are supposed to update, and the second parameter would be the value to which we are updating it. So I want to make this 20 to 25. I'll hit run right now. Let me run this inside a session. Sys dot run, and I need to pass in the variable which would be updated var1. Let me make it small v over here. I'll run this. Right. So initially the value of var1 was 20, but we have updated it and made its value to be 25. Now let's also go ahead and create a small linear model. So let me just type in linear model over here, and this is how our linear model would look like. Wx plus b, where w and b would be variables and x would be a placeholder. Right, so let me start off by creating w. So w is a variable, so w would be equal to tf dot variable, and I am initializing it with a value of, let's say, 10, and this is of integer type. So this would be tf.int32. Now,
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
similarly, I will also assign the value for b. So b is also a variable and its initial value would be 5, and this is also of integer type. And finally, we have x, which is a placeholder. So x is equal to tf dot placeholder. And since placeholder does not actually take an initial value, it just takes a data type. So the data type is again tf dot int32. So I'll run this, and now what I'll do is I will multiply w with x and add b to it. So the equation would be w cross x plus b, and I will store it in a variable and name that variable to be linear model. Right, so this is w cross x plus b. I'll run this. Now again, if I have to execute this, I have to run this inside a session. And since also I have created two new variables, I'd have to initialize them first. So init1 equals tf dot global variables initializer. I'll hit run. So now I will create a session. So sys dot run, and I will execute init1 first. So I have successfully initialized these two variables w and x. Now I can go ahead and run this linear model. Sys dot run. Now I would want the result of linear model. So linear model, and then I will use the feed dictionary. Now inside this feed dictionary, I would have to assign a value to this placeholder x. So x equal to, let's say I give a list of values over here, and the list of values would be 1, 2, 3, 4, and 5. Now I'll run this and let's see what do we get. Right. So if the value of x is 1, we get 15. So this basically means that 10 into 1 plus 5, which is 15. Now after that, if the value of x is 2, so this would mean 10 into 2 plus 5, which is 25. Similarly, if x is 3, that would mean 10 into 3, which is 30, plus 5 is 35, right? And same is the case for 4 and 5.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
So let's go back in 1980s. There was this crazy guy called Geoffrey Hilton. He proposed that we could mimic somehow the mind, how a human mind works, and we can mimic the way it works, so that we can also try to make a thing out of it, so that whatever our mind is doing artificially, we can also do that thing. So he proposed a paper, and everybody said that, Hilton, listen, you are doing something wrong. This is not what is right. And everybody, didn't like uh, the way things were going on. But after 20 years, almost in like late 90s, around 1999, he again came up with this paper. He brought in his paper, but this time with a proof, and he won a contest that is called ImageNet in 2004. This time he came back, and everybody had to listen. So we were at 2004 when he won the ImageNet. I have two people who I've already told that, ImageNet is ImageNet is actually in a competition. It is held by uh, joint vision of Stanford plus Princeton University. These guys come up, and they downloaded a corpus of images. Now they have a very large collection of images, around 1 million images, around covering 1,000 categories. They have. You can just click on explore, and you can see this tree around here. So what you have to do is that you have to make a model out of it so that you can classify the images. So people used to make, hand coded classifiers, and they were working. They were working, but at some stage, they had to fail, because like now, let's say that fish, you are trying to detect a fish, but fish cannot every ways be in the same manner in which you are building the hard coded thing, right? Or let's say that you are trying to detect a cat, and then you say, okay, top right if it is a eye, top left it is a eye, and then it's a squishing mouth, then it's a cat, right? But now the cat face will not always be available to you in that particular fashion, right? It might be a top view, a side view, a bottom view, any view might come up, and at that time people used to fail. But in 2014, 2004, when Geoffrey Hilton came with his paper, the competition he won was with 94% accuracy, and that was never achieved, and it surpassed the human accuracy also. So that was where, when people started listening to him and he came out, then he proposed slowly that, okay, that this is what I think, that artificial neural network is nothing, but that we are trying to mimic what is happening in our own mind, right? So if I say that, what is the theory, what Joffrey said about neural network is that he said that artificial neural network is a computational model that is inspired by the way biological neural networks in our brain human information possesses, right? So I mean, most of you know this thing, that that our nervous system is made up of axons and okay, I'll show you the photo, that it is made up of axons and brains. A human nervous system is most basic diagram, and everybody of you might have seen this. So how this works is that there is a exact replicate copy of this. If I copy this, and you can attach it back here again. So these are the axon terminals that are connected to dendrites again, and this is how it flows. So let's imagine that your fingertips where you can have your dendrites, and these are like small particles again of your pure neuron connected to your brain. So this is how there are like millions of these connected, and they're connected. If I take this, okay, one more feature of Jupyter Notebook that you already know, that you can add a markdown language. So what I do is I do escape M, and then I'll write HTML inside it. So I write img src is equal to, this is how you can write your, in this you can add that this is, right? Let's now look at it one by one, slowly. Okay, so these are called dendrites. These dendrites are the one who are like septicles. These are the one who are responsible for catching all the information and sending it forward to the nucleus. Now nucleus processes this thing, and it sends to this axons, and again throws it out to the axon terminals. Now imagine again that this is this copy, this is again replicated here, back here. So you can imagine that these dendrites are connected to these axons, right? And then they're flowing. Now imagine, let's say that you touched a very small, a very hot glass, right? The moment you touch the hot glass, the dendrites at your fingertips, they sense that something is very hot there. So they send this information to your brain, okay, that this is hot. Now imagine this dendrite is processing the information, sending it to terminal to dendrite, then dendrite to terminal. It goes on until it goes to your brain. Now the brain says that this is very hot. you should remove your hand. Okay, now this process is again flowing back to the dendrite, the original dendrite here. Let's say that this is the original dendrite here. Okay, and your brain will say that this is really hot, you should remove the fingertips from the glass. And now when I'm saying that this information is going on, believe me, from your fingertip to your brain there are like millions of these dendrites who are connecting and flowing this information. Now again a process of reversal information flow is going on, and this time your brain is sending a signal that remove your hand from the glass, and this is again going back to the fingertip, and then you release your hand from the glass. But in real life, when you touch the glass and when you remove it, how much time do you take to remove this? It's just some nanoseconds, right? I mean, less than. Your reflexes are very strong, you just remove the hand out. But imagine what is happening when you do this. Your brain is not, your hand is not taking the decision of removing that. You might think that, okay, my hand is taking the decision to remove that. No, the hand is like a slave of brain. So every body part of ours is like a slave of a brain, right? Whatever we are doing, it is sent by the brain. The information is sent by the brain, and then it's doing. This is how your body works, right? So it's a slave of your brain, and the brain sends the information, remove or attack, whatever it is, then it reacts. But it's really fast, right? Similarly to this way only, Joffrey said that, okay, this neural network, this is how even I will also build a neural network. Now I'll show you how a basic neuron looks like. Here it is. This is the image. You write it. Basic neural. It's not a network, it's just a neuron. But this is an artificial neuron. So Joffrey said that, okay, this is how I propose. Let's do the following. Let's say that your hand is not doing anything. Your dendrites or your nervous system is not, this basic neuron is not doing anything. Imagine that it's doing nothing. But it is reciprocating the information. But how it is reciprocating the information? By activating itself. So when you touch a hot glass or something, it activates itself, and then only it's transmitting the thing, right? Now imagine if this would have not activated, it would have sent nothing, right? So this is also playing a very crucial role. See, brain is sitting somewhere like a million neurons far, right? He doesn't know what is happening to your hand until and unless this neuron is sending the information. So what information will the brain process if it doesn't have the information? So these guys are very much responsible for sending the information, and they send the information only when they're activated. So this dendroid will become, this nucleus will become activated, then only it will send the further information. And see, there is also a basic kind of a information processing is going on. It doesn't mean that these dendrites are just sending blank signals. See, I'll tell you more depth inside. See, these dendrites, they collect the information. These dendrites, they collect the information and they send it to the nucleus. Now, nucleus thinks that should I process this and send it forward? Yes or no, depending on that, nucleus send it further. Right. Now, how is nucleus sending is nucleus has a particular threshold value. After processing it, it says, okay, if I am activated by that processed value, it will send it further. If not, it will keep it to itself. So this is also how a basic artificial neuron, when I say artificial, it means that the one that we are building right now in deep learning, right? This is also built. Now what is happening is that imagine this round thing that you're seeing is the nucleus. This thing is a nucleus. But this is a nucleus, right? And these are the dendrites to it. This one, this X1 and X2. This is the way of thinking how we are intimating, and this is the tail, axon tail, and it is again connected to again a neural network. So it's a chain of multiple neurons going on. Now, if we go mathematically, what is happening inside this? It is nothing but a linear combination of all the inputs with a bias. I just like went to the very human biological way and I just sent a sentence. It's doing nothing. What it's doing is that it collects the input. Let's say that you have two inputs. Let's say that you have two inputs, x1 and x2. These are your two inputs. Now to every input, you will give some weightage to it. Let's say our weightage is here. This weightage is called W1 for x1 and W2 for x2. Correct? Now what I said, it is trying to build a linear regression, right? So what it does, it multiplies the weight of the corresponding input to itself. So W1 x1 plus W2 x2 plus it adds a bias to it. Now you will ask what is a bias. I'll say imagine that there is another input called x naught. There is another input called x naught, and the value of x naught is equal to 1. The value of x naught is equal to 1, and there is this weight associated to it that is called w naught, right? So this bias is added to it, and then you add this. That's it. You plus all these values, multiply plus all these values, and you give this output to something called y. This is all a neuron does. Make sense? Any questions? Please ask. It's very important that you build the intuition that what is happening here. So this is the most basic. It's the smallest part of a neural network that you can pick. And the smallest part of a neural network is doing this. That it takes all the inputs that are coming to itself, give them some weightage, multiply the weightage to the corresponding input, and then sum all these, and then add a small bias to it also. That's it. Over. How is this weightage and bias being introduced? That who is okay, x1 and x0, x2 and x1, I can say okay, someone is giving to us the input that what is the temperature of the glass. Let's say it is coming from the outside environment. X1 and x2 is coming outside, but who is giving this w1 and w2? So okay, so the answer is that in a artificial neural network environment, at the very first instance, they are randomly allocated to it. So see, you all guys have learned ML, right? So how does ML work? ML says that I know the output, and depending on the output, I have to give some weightage to these inputs so that they can give me the output. Now you know that the output will be y. You know that the output is going to be y, right? Now you want to make some equation where y is equal to x1 plus x2. Okay, and now this is not the correct answer, right? X1 and x2 will never give you y1. So what you do, you add some w1 here, some random w1, and then here random w2. What it will do, it will not give you the answer. W1 and W2 will not give you the answer. You will do some corrections again in W1, W2, and ultimately it will give you Y. So this is what is happening. At the very first instance, you will take W1 and W2 as random. First is that does the process is reverse? Yes, it also reverses itself. The model will not only go from x1 x2 to y, but it can also come back from y to x1 x2. And second, let's say that he's asking Shivam, does it process recursively? Recursively, just imagine that there are like thousands of, now I'll draw it again to show you. This is just a very basic one, right? Now imagine what is going on here is that this is the small that you saw, right? X1 x2, and it is giving some y. Now here it is again, there is a x1 x2, and then this is giving me y. Now this y and y1 will become an input for some other cell, and then it is giving here. So are you imagining how will it look like? This becomes this, and this will become again an input for some other. So these are like connected. These are like throwing information from one to another, one to another, one to another, right? But this is how it works. This is how a small network looks like. And this is if I write down the theory, it says that the basic unit of computation in neural network is a neuron, or often called as a node, right? And came write it very right. This is called a node, or you can say it a unit also. So it receives input from some other node, from an external sources or external source, that I was saying right also, right? The x1 and x2 might be an input from another neuron, or it might be given to you directly from the external environment, right? Computes the object. Each input has an associated weight to it, which is assigned on the basis of its relative importance to other. The node applies a function f to the weighted sum of this input, right?
So we'll be having the students' data. So whatever the marks, based upon their marks, so we have to decide the grade. So we have to adjust whether the student is passed out or failed. So we will be adjusting the marks based upon the grade.
This is a very hard-coded problem, I think. But let me take an example that you're working on a machine learning problem where you are trying to find out the loan defaults, right? That in bank you have multiple people who take the loan. Now the bank wants to know how will this person repay the loan or not, right? Now you already have a historical data with you. The bank will give the data to you. Okay, let's say that this is the data with you. So in that data, you already know that if this is the feature of a person, this is the credit history of the person. Based on that, they will also give you that, okay, he paid, he didn't paid, he paid, didn't paid, right? And based on that, you adjust your model, right? So there also you have a x and y with you. You will have your x and y with you at that particular instance also. Okay. So everybody gets this f this function thing, right? That's how this function is working. This function f is called the affine. So the f function that you see, this is called the affine thing, and it's doing nothing, right? You saw that this is it's doing a linear thing here, just multiplying the weights the corresponding x1 x2, and you might now consider x1 x2 as the importance feature. So the more important x1 is, the more higher the value of w1 will be, right? The more lower the value of w2 is, it means it doesn't make much sense to y. So everything that we will now talk will be with respect to y. So the x2 is not making much sense to y, so the value of w2 will be very less. Let's say y is dependent on x1, so this value of w1 will go more higher, right? And then your bias you already have, this is a static thing, right? Because the x naught associated to it is equal to 1, right? Let's now go back at what further happens here. Now you get the y out of here, right? Now this y thing is a little, you have got the answer, and this might be greater than 1 or less than 1 also, right? So there is no measure of this answer. It might happen that w1 w2 is very small. Let's say w1 w2 are very small, then the value of y might be almost equal to 0, right? Or let's say that w1 value is very high, like very high, so the value of y might also get very high, right? So now this might bring some bias, this might bring some ambiguity to our model. This y might be sometimes, next to infinite, it might be equal to infinite, or it might also be equal to 0, right? Depending on the variables. And we don't want that. We want our y to be in some particular range, right? We want our y to be in some bonded weights, right? Then comes next guys whose names are activation functions. Activation functions. Now we got to know that how this y is made, right? How this y is ultimately achieved. Now to adjust the value or squeeze the value of y, we need some other thing, right? We need something that can control the value of y, and these are called activation functions. Now what activation functions does is that they will take the value of y and they will squeeze the value of y in some certain range. What they will do, they will squeeze the value of y in some certain range. So we have multiple, let's say we have a step function, we have a 10h function.
Shivam, Sanjay said, can you please come again about this activation function? Not getting you properly.
So let's come back what this activation function is. So you understand that the value of y, how it is calculated, right? It is not totally dependent on w1 and w2. If the value of w1 and w2 is very less, I mean 0.0000, or let's say 10 to the power minus 23, then the y is going to be very less, right? Next to 0. Or let's say that the value of w1 and w2 is like 10 to the power positive 48 plus 48. So this might be very high. The value of y might be very high. There might be no standard to control this value of y, right? Mathematically, there is no, this value can go from negative infinite to positive infinite, right? And this is not a very good range to get about a particular output, right? So what we do is we introduce something that is called activation functions. Now what this activation function will do is activation function will make sure that your output that you have got y should be in some particular range. What it should be? It should be in some particular range. Now how do you decide that who is going to be in what range, and how is that range called? See, the activation function, if I ask you mathematically, the mathematical purpose of introducing an activation function is to squeeze the value of y between some variable called 0 to 1, right? Majority times. So the purpose of activation function is to bound the y in some range, right? And this range might be minus 1, say 1, 0 to 1, or sometimes 0 to infinite. It might be different things, right? I was at this thing that mathematically the value is to be squeezed between 0 to 1. But if I talk to you about statistically why I am doing this is, now imagine till here, till this particular range, your model is a linear model. Everybody agrees with me, right? This is a linear model. Nothing non-linear have been done till now, right? All the things that we have done till this step in this circle, everything is linear. There is no non-linear thing, right? Now, linear things are a little bad at classifying things if there are more than three classes, right? If I ask you, if let's say there are three classes, one is like crosses, right? One is circles, right? And one is some triangles. Now, can you make a single line and can divide these three data? No, right? If it would have been two classes, you might have, drawn a single line and you might have divided the data into like two classes, right? But if it is a three class data, how will you divide this? You have to ultimately make a triangle kind of a shape or this kind of a shape, right? Then only you can divide this thing, right? So I'll show you a photo also. Let's say, let me give you an example, then I'll show you how this works. Okay, can any one of you, let me hide it here. Now this is this thing in front of you. Everybody can see your data. There is this red dots and there is a blue triangle in the screen, right? Everybody can see this. Now, can you make a linear model that can separate these two things? This can only do in a two dimension, right? But if I say you that, okay, see a magic, anybody wants to try this thing? How will you do? No? Okay. What I'll do is, I'll remove this now. So what I did was, I introduced a third dimension. And now I could easily separate by introducing a hyperplane here. And then I can say, okay, something that is above this hyperplane is red, something that is below this hyperplane is blue. Makes sense to everyone, right? So this is why we do activation function, to make sure that we want to classify things more better, to make things more clear. We do an activation function. So mathematically, why we are doing activation function? Because we want to squeeze the value of y somewhere. But if I talk statistically, what we are doing, we are introducing non-linearity in a linear model, because linear models are very much not capable of classifying things in when the number of classes increases. So now we saw that as soon as we increase the linearity, if we increase the dimension in the data, if we introduce non-linearity in the data, what it is doing? It increases the chances of making a linear separable model, right?
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Right? So if I say in three times, first mathematically squeezing the y. Second, if I say graphical thing, why we are doing this? Because we want to introduce a new dimension. And statistically saying why we are doing this? Because we want to introduce non-linearity inside it. Now you might be asking what these functions do. It's a very good question. I have activation functions graphs. See, this is how a sigmoid looks like, a tanh looks like, a ReLU looks like. And see, everybody is bounding. So see, sigmoid is bounding between 0 to 1. Tanh is bounding between -1 say 1. ReLU is bounding from 0 to infinite. So it lets go everything that is going above. Yes, we have step function also. Step function says that you can go, if something can be only have two things, either 0 or 1. If something is negative, it goes 0. If something is positive, it goes 1. It's a step function, sigmoid, tanh, ReLU. So there are multiple things. These are doing the same thing that we want to do for a activation function. ReLU, you can understand that if something is negative, it says it's a 0. And if something is positive, it lets go whatever the value of this is, right? I write the variables in here. This is what brings in. Sigmoid is this, tanh is this, and ReLU is this, right? What is the maximum of 0 to 1? That value it will take, right? This is what activation functions is. Let's say that you have this thing called y1 and y2, right? and now the value of y1 and y2 is very large, right? So this y3 will become ultimately also very large, and this y4 will become also very large, and we know this is not the exact thing. We always expect our output to be in the form of 0 to 1 if it is a classification problem, and if it is regression problem, then it will always be in some range from 0 to 1, right? You all agree with me, right? In machine learning also, whenever you did a classification problem, you one hot encoded the problem. So you never said that the output is going to be a C80 cat or DOG dog, right? You always said that, okay, if 0 comes, this is cat, 1 comes, then it's a dog, right? You did the same thing, right? The machine learning also, or if it was a regression problem, then you always regress a value from 0 to 1 with a multiplicative factor, right? So this is what is happening here also. The y3 and y4 ka value can never go up beyond a limit. To control that limit, we have to squeeze the value. And see, when I'm saying squeezing the value, that is in mathematical format. But if you see in statistically, what we are doing is that we have to introduce non-linearity into the data, right? Because linear data are not linear equations are not good in separating non-linear data, right? Right? This becomes separable. You see, now it is very much separable just by a simple hyperplane. Okay, so coming back to a feed forward neural network. So see, this was the input x1, this was input x2, and now what a feed forward neural network expects is that a hidden node should be connected to all the inputs. What does it expect? It should be connected to all the inputs that are in the previous layer. So this is, let's say this is called layer, input layer. Wherever your hidden neurons, this is called hidden layer. And your outputs are here. This is called a output layer. Now when you are building this feed forward neural network, your responsibility is just one, that whichever neuron you're standing, let's say we are standing on this particular neuron, let's say this neuron, this neuron. Now the only thing that this, okay, this is not a neuron exactly, oh sorry, let's say we are standing on this neuron. Now the responsibility is just this, that if you go to the previous layer is the input layer, all the neurons in this layer should be connected to this hidden node, right? Similarly, output 2 also expects the same. You go to the previous layer, so this is the output layer. What is the previous layer? Hidden layer. So all the neurons in the hidden layer should be connected to the output node 2. Make sense? Or if I make it more easily, let's say that whichever neuron you are standing, just go to the previous layer, and all the neurons in that previous layer should be connected to this particular neuron, right?
What is this layer signifying here?
Correct. Very good question. So what you are doing is you have stacked all your neurons one by one in some format, right? So all your input neurons. So see, whatever you made in this above statement here, in this above thing here. So this x1 and x2, this is this x1, x2. This might be x3, x4, x5, x10, right? So these x1 and x2s are what? Inputs, right? So what you do is you collect all these and you just put it inside a layer here. This becomes a hidden layer. Now you will not only have one neuron, you will have multiple neurons, right? So what is happening is that what you have done is, rather than having just one neuron, what you have done is you have made multi-neuron system. So this is a feed forward multi-neuron model here. So what you are seeing in the previous photo, that is the image that I showed you, that was just a multi-input single neuron, but now you have multiple neurons. So what you do is you stack these neurons in this layer, then you can have, so this is just an example. What you can do is you can have an image like this also, multi-layer. Okay, so now if you see Tarun here, so what is happening is these are your inputs x1, x2, x3, x4, right? This is your input layer. This is your hidden layer 1, where all your affines and activations are happening, right? This is your layer 2. Again, all the affines and your activations are happening. And this is your output layer. Hidden layer HL2. This is HL1. and this is input layer, plus some bias B will give some output called Y. And here you will be having a very small activation function also residing here, right? Similarly for this N2 also, this N2 is connected to all the inputs, right? This N2 is connected to all the inputs. This N2 is connected now, it is connected to this, to this, to this, and this. Now N2 will also do some affine and then bring some activation, small activation function here, and it will also give some output called Y2. Similarly, Y3 will also be here. Now this Y1, Y2, Y3 will become input for these neurons. Let's say we call this neuron as N4. Now this N4 is connected to this, this, and this. Similarly, again affine, and let's say it gives the output called O1. Now O1 is here. Similarly, O2 is here. Now this O1, O2 will also become input for this. Let's say we call it O1 right here, right? This is O1. Y4. Let me remove this. Sorry. We were here that there is this some output called Y4, and there is some output called Y5, right? Now what is happening? Y4 and Y5 will become output for this O neuron, and they will give some output O1 and O2 similarly here, and then you will have outputs, right? This is how a multi-layer neural network works.
How will we know that how many layers?
Correct. This is one of the very good questions that first of all, how many layers do you want? This is the layers that you have, L1 and L2. Now you might have another question that okay, in one layer how many neurons can I fit? So there are currently 4. I can fit 5, 6, 10 also, right? I can fit 10 neurons also. So who is going to tell me that how many neurons and how many layers? This is what data science you are going to do here. I mean, everything is built for you. This neuron thing and this all thing this is already built for you. The only thing that you have to do is that you have to come up with the optimal number of neurons and optimal number of layers for each neural network. And now who is going to decide this? Very good question. This is you who is going to decide this. And how? Okay. So first answer is that hit and try, that everybody will tell you, and I'm also telling you that the first approach is hit and try. Let's say that you are doing a very new problem. I mean, you don't have any idea, you are just doing. So one thing is that you'll go with the hit and trial model. Second is that as soon as you become a little bit expert, now you start learning, okay, this is how my model is reacting to this particular neural network layer. Then you see the model capacity. Okay, so let's say that now see, when this let's say this is called neuron 1. When this neuron 1 is connected to x1, x2, x3, there is a weight called w1, w2 on this layer, and w3 here, right? So but when this n2 is connected, this is not w1, w2, w3, there is w4, w5, w6. So when this x1 is connected to this n2 here on this line, there is another weight, that is w4. So imagine how many weights are there for 3 inputs, 3 neurons. There will be 9 weights, right? Now there are 9 weights. Now imagine here again that you have 3 inputs and 2 outputs, 3 to 6, then you have 6. So 9 plus 6. Then again here 2 to the 4. So you will have 2 plus 4. So 9 plus 6 plus 4 is 19. So 19 weights are there, and then you will have 3 biases here, right? So 19 plus 3 is what? 22. So for the small neural network, you have 22 values that you have to predict, right? Because y1, w1, w2 we have taken as random, right? And biases are also random. So you have to adjust them in a very optimal way so that you can get the output as y. So now imagine that you have 22 things that you have to train here. 22 things that you have to predict, not predict, but you have to optimize, right? And now let's say that you have a data only for like 10 rows. Now does this justify that you will have 22 things to adjust in the 10 rows of data? So this is called capacity building. So what you have to do is that you have to check your model if your model is even capable, if the data is even capable to adjust these values, right? Let's say that you are just doing a simple addition, like if you give two numbers, your model has to give some output, right? Now let's say that you have 1,000 examples for it, but now you're building a, like, say, 1,000 layer and 1,000 neuron, per layer 1,000 neurons, and then you have 1,000 layers. Now does the model require this much of data? No. The data will be lost in some third or fourth layer only, right? And see what I just said in just last 2 3 sentences, this will come slowly with the experience in you also. So what you'll do, so whenever a new problem comes to me, I first of all read the research paper through it. See, because we are not researchers. Let me be frank with you. We are not researchers who are going to make things. We are deep learning engineers here, right? We have to implement the engineer and we have to solve a business problem through it, right? So what you do is, first of all, you read some papers out of it, right? Then you get the intuition of how do you build a neural network around it. Then I do some hit and trial error. Okay, this is how you build, and this some changes, and then slowly you understand. Okay, when I change this thing is affected more. Then you reduce and more. Then you have some prior knowledge also, like that I told you. If capacity, that what is the capacity of the model? Let's say that you have a very large data, but you are just building one layer. Then the data is underfitted, right? Or let's say that you have very less data, but you have made a very big neural network for this. And this is called overfitting, right? You have a very over number of neurons for your model to be predictable, right? So slowly you will you will have intuitions. And this is, I will tell you, with your when you will be doing your first problem in a neural network, you will understand slowly. See, you might be thinking that, I'm not taking to you practical, right? I am not telling you about any real world example, but this theory is really important. I might directly jump to the code also, but that will make no sense to you after 2 or 3 weeks, right? Because code anybody can write, until unless you don't know. Okay, what will happen is the next after 2 or 3 months, when you will be making your own neural network, you will fail that. Okay, which activation function to use? Then this thing will occur. Okay, so see, this is what he is talking about to all the people. This is what he's talking about. Let's say that you want to add more layers. So currently there is only 2 hidden layers. You want to add more, add more, add more, right? If you want to increase per layer, you want to increase the neuron, you might go like this also. Okay, you might, like, I'll reduce it to, like, let's say 6. This I'll reduce it to 4. This and 2, and this is 1, right? This is how your neural network will look like. These are the two inputs. Now every input is connected to the every neuron in the first hidden layer, right? Then second, then third, and fourth similarly. And this is how the data is flowing inside it. You can see now slowly, when we put every x into each neuron, does every neuron give same y? Very good question. But no. See, Kim, if we come here, it would have been the same if they would have same w, right? So if x1 is connected to n1 here at this layer, it has w11, right? But when x1 is connected to n2 here, it has something called w12, right? So there are different weights. So it is coming from x1, but because it is connected to different neurons, different input neurons, they will have different weights also. Understandable? So to other people, what Kame is asking is that, okay, that you are doing affine. I understand that you are doing affine, but let's say that, let's go back to affine equation. Because the value of x1 and x2 is constant, the output will always be constant, right? But no, because y1 is made up of this equation, and this equation is also driven by w1 and w2, and the w1 and w2 values are different, the value of y will also be different in each case, right? Makes sense, right? And when you are asking about a real world problem, this is how a neuron will work. Okay, I have this also, don't worry.
So you mentioned overfitting and underfitting neurons,
Yes,
so how do we come to know that based on the Y or
again a very good question. So I took these two words called underfitting and overfitting. This is how it actually works. This is a intuitive GIF. Okay. So what Suresh is asking is that I took two words in overfitting and underfitting, and how do we address this problem? So what we do is that we divide our data into two parts, and I think you must have also done this in ML also, right? Training data and validation data, right? Not two, just three parts, right? Training, validation, and testing, right? So what you do is whenever you are training your model, you just make a slice, another slice of a data, and this is called validation data. And you will never show this data to the model, right? So no, you are never going to train your model on this particular data. So what you're doing is you will never show this data to the model, so model will never come to know about it. So it will never learn about it also. Now once your model is made, what you will do is you will test it on this data. What you will do, you will test this on this data, and then the model will say, okay, this is how it looks like. Okay, this is what the predictions are, and then you'll see the predictions, and then you'll compare the predictions. Okay, this is not what I wanted, so the model is underfitting or overfitting. Now how will you do underfitting and overfitting? You'll do a confusion matrix, and then you'll see that if the model is just giving out you only one classes, let's say that your data had 10 classes, and if the model is just pushing towards one class, then this is overfitting. Your model is overfitted at a very lot level. Okay, then we have another question from Game. He says that it means now this dog image, when we expand this image mathematically, this will come out to be three things. One is called x1, x2, and x3, right? Now what we have to do is this x1, x2, x3 is done towards from our end. Now this x1, x2, x3 is connected to this neuron 1. Okay. Now x1 is connected to n1. This is called w11. But when it is connected to n2, it will have some another random weight called w12. W12. Make sense? So number of neurons you can increase as much as you want. As much. You can have n3, n4, n5, n6, n7. Doesn't matter. But you have to make sure that this w11 is not the same weight for all n1, n2, n3. Right? Cool. Thank you. Thank you. So inside the matrix, you can see there are multiple values. The value ranges from 0 to 255. 255 is for like utter black and 0 is for white. Right? The value ranges from 0 to 255. You can see the more black it is, the more the value it has. Right? So what is happening is that these are the multiple inputs that you will have inside your images. Multiple inputs, and all these inputs will go in here. So in this particular example, you are seeing 3, but this time you will have more. So these all the zeros in first, all the values in second, third, fourth, fifth row till the 28th row. You will have all the numbers inside this input layer stacked one by one. So ultimately you will have 28 cross 28 is equal to 784. So you will have 784 inputs normally for this small image. And this is you guys were all asking about me how this will work in real world. So real world, let's say that you have an image of 500 cross 500. So that becomes around like 25,000,000. That means 2.5 million inputs you will have for single image, right? And let's say that you have 10,000 images, so this becomes multiplied by 10,000, right? So these are the number of inputs that will go inside one by one by one by one by one. So one image will go one time, two image will go two, second time, third time, and then based on this, the output is the model is going to do some calculations in the hidden layer, and then it's going to predict the output, and it will give you some output at y. Okay, so now we'll turn up pages and we'll move to multi-layer perceptron. But now we might have multi-layer perceptron architecture. Now a multi-layer perceptron architecture simply means that you might have multiple hidden layers. Okay, so apart from having a input layer and output layer, you might have hidden layers in between of them also. Whereas a single perceptron was only a linear function, a multi-layer perceptron will have multiple linear and non-linear functions, a combination of them, right?
Okay guys, a quick info, if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
So I think you already saw this, but I have an image of multi-layer perceptron also. Let me show you. Okay, so this is how a multi-layer perceptron looks like. If I just minimize my screen a little bit so you can see this now. Again, just to memorize things up, this is x1. This is what your input, x1, x2. These are your two inputs, right? Now you have a single hidden layer right now here. You have this one neuron here. Now you already know that what is the calculation going on inside. There is the affine function. Affine function, what it does, it takes input from all the behind layer neurons, right? So if I say it takes input from all the behind layer neurons, and if this is a hidden layer h1, then it means that it will take inputs from all the neurons inside this input layer, right? So this is x1, then this is connected, this is x2, this is also connected. Now whenever a neuron is connected to another neuron, it is connected through some weightage corresponding to it, right? Let's say this is w1, this is w2, right? And then you might also have a x naught. Now the x naught is always equal to 1. So you might say this is just a bias as b. Now this b is like constant to this neuron also and to this also, right? I change this and it must have come to this. Okay, so now this is x1 and x2. For this, when they are connected to this neuron, the one that is downwards, and this neuron, they are connected again to some weightage, but this weightage might or might not be equal to the w1 that is the one that is described here. The one described here, this is never going to be equal to this one, right? So these are different weights associated with different. So you might, to make it more simplified, you might think that whenever there is a string connecting two neurons, it is connected through a weightage, and this weightage is different for each one, right? This weightage is different for each one. You might also see the equation here down here. W naught in plus 1 plus W1 x1 W2 x2. Now you know that W naught is equal to 1, so we have replaced W naught is equal to 1. Sorry, x naught is equal to 1, so we have replaced x naught with 1, and W naught in itself you can say W naught, or what people like to say is it's called as notation called B, and this is called the bias of the neural network. Okay, bias, and these W's are called the weightages, right? And then you do again a summation out here, and this time you do the final output, and then you give the output right here, right? You also remember that after every neuron there is also activation function which is sitting here, here, and here. They are also present on the outer section also. This and this, they're present here also. So they, and then you read that there are different types of activation functions. Activation functions from step function to sigmoid, then to uh, softmax. We have different. I'll slowly go through each of them, and then you'll understand that how they interact, and how you might be also changing them according to your needs, right? So now once we are done with this perceptron layer, now okay. So this is called a feed forward neural network. Just one thing, feed forward neural network. Once you come from here, this neuron, you go till here, then there some calculations goes on. Then you come to here, which is taking connections from this and this neuron, and then you give the output, right? Now let's say the output comes out to be some y1, whereas the actual output was, let's say, y, right? Now there is the error associated to it. So you say that you have an error, and what is the error? Y minus y1. This is the error, right? Y was the actual answer that should come, right? But you are saying the answer is y1. Then y minus y1 is actually the error. What it is? It is actually the error. This is actually the error, y minus y1. Now your model, you say to your model that model, you have done some kind of mistakes. Now if you go back inside your session, if you go back to your session, you might see some errors inside it, and that error might be equal to y minus y1. So go and do the changes. Now if you see our function that we have done till now, the result through which we have come till now here at this point y1, it is all how much dynamic things you have taken, I mean non-static things you have taken. See, x1 is always going to be static, right? This no one is going to change this x1 and x2, because these are given by the data itself, right? So the data can never change itself. It is you who has to change, right? And then what is the thing that we have taken assumed? These are the values of W1 and W2. W1, W2, and W naught. These are the similarly these W's here. I mean, all the W's that are here, all the W's that are here, these values are something that you have assumed, right? So now what the model says, the model says that the value that you have assumed, W1 and W1, W0, W till Wn, these values might have some kind of a correction because the current values of W are present, are giving some error, that is y minus y1. So to reduce this error, you go back and check your values of W and switch the values of W to such an extent so that they minimize this error, right? Whatever I said just now is statistically, right? Okay. Now this thing is called backpropagation. Now backpropagation, if I take the copy of the, so I'll tell you my particular example. So I was working on this library that is called DOLD5. Here what we are trying to do is that we are trying to restore colors into images that don't have color. So I mean, if you talk about images that are like from that are before 1924. So we have some German artifacts. Those are before 1924, and those are totally black and white images to us, right? So what we have to do is that we have to fill images inside it. Now, filling images inside it is, I'll tell you, it's a complex process, but there is a form of images that comes out. That is called the LAB images. So if someone of you who has interest in photography uh, or if you understand what images are, then you might have heard this term called LAB. LAB images to convert. Now the range of LAB images is from minus 128 to 128. So here my task. So if generally if you see the activation function, if you remember from the previous class, all our activation function from ranging something from 0 to 1 or minus 1 to plus 1, right? Now I wanted something that has to go from minus 128 till plus 128, right? Then how will these things two go? So accordingly you can change your activation function and you make your own function out of it, right? Make sense?
Yeah, I forgot you in last lecture you said whenever you're trying to bound your values in a certain point, then you use
Correct,
different activation function. I just reminded.
correct, totally correct. So so this is all about the feed forward. Now feed forward, if I just say in one line, feed forward is going from input to output. Now if you want to come back from output to input to make corrections, that is called back propagation.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
This is one of the most not used, but this is one of the most obvious things in backpropagation. This is in AI, and why this is famous, because this is the main backbone for AI. This is how AI learns itself, right? So people say that AI is learning from itself. No, it's not learning from itself. It's learning from the errors. Whatever error it is making, it goes back and it checks. So see, a human tendency of error checking is what? Let's say that you are doing some calculation and you do some error. What do? You go back again to the calculations and you check, okay, I did this mistake, and then you correct it, right? This is also the way how machine is also understanding. So what machine does, machine does some calculation, it calculates that there is some error, then based on the assumptions that it took, or based on the assumptions it took, it thinks, okay, these are the things I assumed and this is now the error. So what it does, it goes back and say, okay, I will change my assumptions, I'll tweak my assumptions, and then I'll see what is the error again. This is a iterative process. So again, let's say that in backpropagation, what will it do? It will try to change the values of W1 and W2, right? It will try to change these values of W1 and W2, and then it will say again go in the forward direction, and it will again see, okay, again there will be some error, but this time the error will be less as corresponding to the previous error, right? Now again it will go back, then come forward, again go back, forward, go forward, invert, forward, backward, forward, backward. This will happen multiple times, and at one point the error will saturate. The error will look like this. So error graph will look almost like this. Here error is on the y-axis, right? And this is whatever you say, time on the number of epochs. Steps means that how many times you have gone forward, backward, forward, backward. So you can easily see here that the error was very high at this particular point, but then it slowly decreased. It decreased till here, but now it's almost saturating. So it's like almost saturating. And at one instance, it will be like parallel to the x-axis. It will become parallel to the x-axis. This is how it looks. So what happens is, I've already told you that all the edges that you are hit, that you see here, that all these lines that you see here, these are called edges. All the connecting things are called edges. Now for every corresponding edge you have a weightage, right? For every corresponding edge you have a weightage, and these weightages are by default randomly assigned to you, right? Now they are randomly assigned at the very first point. When the problem start at that particular instance, these are like randomly assigned to you. Now for every input in the training data, the ANN is activated and its output is observed. This is what I told you also, right? That once we'll do all the calculations, we'll do the first feed forward neural network. We'll check what the output is, and then the output is compared with the desired output that we already know. And the already know, this is also, you might have heard this term again and again. This is called ground truth, right? So see, deep learning may, you might have heard, this is not equal to what traditional technologies. In traditional programming, you have been given the input and people ask you output. But here it's not like that. Here they will give you the input also and the output also. And then you have to define some way to convert this input into output, right? This is how machine learning works, right? Because they give you input also and then they give you output also. So like say, let's first, on the first example, if someone tells you that you have to do some image classification problem, then this is not like they'll give you at the very first instance, this is the image, now tell me what it is. No, they'll give you a training data set where they will give you the output also. With the image, they will also tell you that, okay, 9 is written here, 5 is written here, 7 is written here, right? So you have the ground truths with you also. Now what you'll do, you'll compare your result with the ground output, and then the error is propagated back to the previous layer. If you read the line propagated previous layer, the error is noted and the weights are adjusted accordingly. This process is repeated till the output error is a predetermined threshold value, or where you think that it is being saturated. Right? This is what I also told you. Now, if I tell you that how it goes, okay, let's see one by one. Mathematically, I'll show you one by one also. Now see, it's pure maths, okay? Just a little attention and then we'll be here. Let's say this thing is called, okay, or otherwise what I can do is I'll just pick up the smaller problem and then I'll show you also how it is done. Okay, now if you see that how is this y1 calculated, then let's say that we had an input called input called I1, and let's say I2, write down, and let's say that we only have this one. Okay, let's make it more simple, right? I will take just this image. That will make you understand how things work, right? Let's copy this and write it down. Okay, this is the example, right? So now we have input as x1 and x2, right? And we have an output called y. Let's say that the actual or the desired output be ya, right? This is what we require from them. This is how we have, and the value of y is equal to w1 into x1 plus w2 into x2, right? Everybody agrees to this, right? That how is this calculated, right? Now the okay, and let's then define error. Error is equal to y minus ya. right? Or whatever you want to say, ya minus y doesn't make much problem to us, right? This is how this is working. So now if I say E is equal to y minus ya, then I can say E is equal to, instead of y I can write w1 into x1 plus w2 into x2 minus ya, right? Now if you open up this, doesn't make much sense, but let me write it down. W1 into x1 plus w2 into x2 minus ya, right? Now, sorry, sorry. Okay, now the error is this, right? Now, what do you want to do? Now the final equation of error is in front of you, right? If I write it down, the final equation is in front of you. You can now you have the final equation in front of you. Now you have to see that how to minimize this equation, right? How will you minimize this equation? This is the equation of error in front of you. Now what you can do is, now you might be thinking that okay, this error equation is just a simple linear equation, I can solve it linearly. Now imagine that instead of x1 x2 you have 1000 xn, right? Now this equation is not a 2D equation. Now this is a 1000 dimension equation. Now you cannot just simply do things and just check it around, right? You cannot just do it like that. You cannot just plot a graph and you can look into that, right? This is a little more complex than we thought of it, right? If I show you how the graph might look like, right? The graph will look like this. Just don't read these things, okay? So what I can do is I say, okay, this is your error equation, or let's say error I can also say j of, okay, when you plot this thing here, now what you can see is, see, x1 is what, x1 is a constant, right? x2 is a constant and y is a constant. You all agree, right, that x1, I will put a star and say x1 comma x2 and ya are constants, right? You cannot change them, these are constants, right? They make no effect to E. The one that might change E is W1 or W2. Okay, for a fact, none of you told me, but we missed a bias also here. Bias B. We missed this bias B here, right? Say this B, but this B is, I mean, it's not going to make some effect to us, but still, just for the courtesy, let's put this, right? So now we can see that, okay, what is happening is that E is only dependent on W's, right? The error is only dependent on W1 and W2 and B. None of the other people are changing this E. So what we'll do is we'll try to plot this error with respect to the weight, and we'll see this is how the graph looks like. And what do we want to do with the error? If error is y minus ya, what is our aim? Our aim is to make ya is equal to ya as equal to y, right? This is what our aim is, right? If ya is equal to, then we are saying that the error should be equal to 0, right? Error should be equal to 0 or tending towards 0, right? But if I say mathematically 0 is, if I say statistically, this error is never going to be 0, right? This is never ever tending to 0. So what our main focus is? Our main focus is that if E is here, our main motto is to minimize the current error. Whatever the error is, we have to minimize this error. Now the value of this error can be found here, right? You can simply see the graph and say, okay, this is the value of E. Just take the value of W's and plot them, right? But as I told you, now these errors are not just two inputs. We have like 1000 inputs, so we might have 1000 W1s and then one B also. So we cannot just plot it. So it will become a 1001 dimensional graph. You cannot just plot it. So now we have to think mathematically that how can we minimize the error E. Now minimizing the error E, but we also have the like the equation of E also. We have the equation. Don't think that we have the graph, just think that we have a equation of E also, right? This is above, right? And equation of E is somewhat like this. If I copy this from here, this is somewhat like this, right? This is somewhat like this. This is what the equation of E is, and this is how we have to minimize. Now in mathematics we have learned in inferential mathematics, we have learned that if you want to minimize any curve, if you want to minimize any polynomial curve of the order greater than 2, what is the process? If you want to find out, if you want to know that where is, take the first derivative, that's you have to take. So see what the first derivative tells you. The first derivative tells you that wherever there is a change in the slope of the graph. If I talk about what we learned in our higher education about differentiation, was the differentiation tells you that point coordinate where the graph changes its slope from positive to negative or negative to positive. So if you take the first derivative, it will tell you this place. See, it was in negative slope, then it came in positive slope. Now again here, when it was in positive slope, then it came into negative slope. Again positive, negative, positive, negative, positive, negative, positive, negative. So it will tell you all the places where it has uh, changed the slope from positive to negative or negative to positive. Vice versa, it's possible, right? So this was how we talk about inferential mathematics. But if you go in descriptive mathematics, it says that what is a derivative of a function? A derivative of a function when you have a tangent that is parallel to the x-axis, right? When it is parallel to the x-axis. So how where will be the tangent parallel to x-axis? Whenever there is a slope that is equal to 0. So if the slope was from positive to going to negative or negative to positive. So both the mathematical percepts tells you that there is a change in the slope in that, right? So similarly, we can know that where are the positions, where are the places where we can get a change in the slope. Now, as Omar very he suggested that we will get all the points where it is maximum and minimum also, and we just want the point where it is minimum. I mean these points, we are interested in the one that are by dotted by green, either this, either this, either this, right? But now again there's a problem is that these are very higher error. This one that I'm just marked as E1, this is a very higher level of error, right? We don't want a higher level of error, we want a lower level. This one we want the E3, we want E3 to be our error. So what we do, we take double differentiation. We first take differentiation, then we take double differentiation. Now double differentiation, then Omar, can you tell me what is the condition if it is less than equal to or equal to less than 2? Okay, I'll tell. Now, with the first derivative, you can know that where is the slope of change. But if you want to know that what it is, if it is a maxima or if it is a minima, how do you know it? You know by doing a double differentiation of that thing and then checking its dimension. So if the double derivative of any of your function is greater than 0, if the double derivation of a function is greater than 0, then it is a minima, right? And if the double derivation of any of your function is less than 0, then that is maxima. These are the conditions. Then you will check accordingly and you will go for minima. Now again the problem is that okay, now you will reject these points, you will reject all. Okay, so you might discard this, you might discard this, you might discard this, you might also discard this, right? So you will remove all these blue points. Now you will only have the green points with you, right? Now you want this E3 to be there, right? Now we don't have any mechanism through which we know that we have reached global minima or not. This is the dilemma in deep learning. And so slowly what we do is now understand this mechanism. This is called this whole thing that I'm showing you right now is called gradient descent or GD, right? You might have also heard this as SGD, stochastic gradient descent. When you do a gradient descent in batches, it is called stochastic gradient descent. So what I'll do is I'll take the first derivative of DE, DE. Now you know that E is equal to this. Let's write it down. So now you have seen this one thing that the E is dependent on either W1 or W2. So what you'll do is you'll take the derivative with respect to one time with respect to dW1. So what will happen? It will say x1 and then everything is equal to 0, right? Because these are all constants. Am I correct or wrong? What I'm doing is I'm trying to take a derivative with respect to W1. What will happen? X1, correct. X1 into 1, totally correct. Plus W2 is again a constant, plus constant plus constant. Makes no sense, right? It's there. And if you want dE by dW2, then what will happen? It will give you X2, right? X2 into 1. Don't worry again to, okay, it's in chat. Just a second. Okay. So now you might ask that, okay, now we understand that this is the new value of W1 and W2, right? So now what will happen? This older value of W1 and W2 will be replaced by the new one, and then you again go forward, and then you again get the error, again come back, change the value, again go forward, backward, forward, backward. But there is one thing that you might ask me, that what is this A here? This A is called alpha. Sorry, this is not A, this is actually alpha, and this is also called as learning rate, or you might see people calling as LR. So let's say the previous value of W1 and W2 will give you some error that would be here at this point, the one that I draw very small here, right? The next one will be here, then here, then here. So it might vary that how gradually you are moving your W. Let's say that you are making very small change in W, very small change in W. So your error, let's okay. So now let's say you have taken some initial value of W such that W1 such that the error is here, right, at this point, at this particular point. Now you make a very small change in your W1 and make it to W1 dash. So what will happen? The error will shift very slowly also, right? Your error is also going to shift very, very slowly because you have made a very small change in W1. Or otherwise, let's assume that you might, there your W1 originally was here and you made a very big change in W. So your error might be here at this point, new error might be here, or it might also happen that it might come here also, right? It might change that how gradually you're moving your W. So there is this terminology that says that you should very slowly move your W so that you don't miss your minima. Assume Again, let's assume that you slowly moved your hair till here. So you have come till here. Your W1 is here now. And now you suddenly increase, you did a change in W1 so large that you came here. You came at this point. Now this is bad because you missed the global minima in here, right? So what people say that you should very slowly move the value of W, very slowly. You should do all the changes very slowly, and your dE by dW, your dE by dW should be controlled by some another external factor, and that factor is called alpha. Now, because if you go down the screen, if you see, I have multiplied this dE by dW term with a thing called alpha. Now this alpha is with you. This is a constant and this is in your hands. You can change it anytime that you want, right? So what you will do is, I'll move back up here. So what you will do is that you will select the value of alpha such that it is moving very slowly, right? But now there's a disadvantage also, because if you move very slowly, then let's say you are here, then you will come here at this point, then here, then here, then here. So you might reach your global minima at a very larger time. It will take a lot of time to you. So you have to take a very critical value of alpha such that it moves very slowly.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
And alpha, keeping the value of alpha, yes, you can say this is one of the parameters of hyperparameter tuning. Hyperparameter tuning, HPT. Yes, this is one of the small features that you are tuning. So the value of alpha you should keep is 0.001. But again, if someone says you this, well, like I just said you that you should keep your alpha, no, I'm totally wrong. It depends on your data that how slowly you see that your model is moving. This is just the initial value that you should take. So if you will see all of your major frameworks like Keras or like TensorFlow, you will see that they have put a value of 0.001 also by default.
Okay guys, a quick info, if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
Feminist was the data set where everything was written, in 1, 2, 3, 4 was written on images, and we need to predict out what is written on the image, right? I told you there are two things now. One is the image, and second is what is actually written on it. That is called labels, right? So we got the data set, and then we started doing it on Keras. But today we will do it on TensorFlow also. Why on TensorFlow? Because I want to give you a basic idea how code in TensorFlow is also written, and how Keras is helping you in how much lowering the work. So otherwise, you won't get to know that how much things Keras is doing in on itself, right? I'll do the first basic. And if you think this is not visible to you, I can switch to this also. NumPy as np and import. What else can we do? Matplotlib. Okay, I'll do these three imports. I'll check the version of TensorFlow what that we are using. So I'm currently using 1.8.0. If you are using anything else, don't worry. Ours code might at some place differ, right? Don't worry. But if your code varies, right? So how do I get the data? I get the data from tensorflow.examples.tutorials.mnist. So actually TensorFlow has already downloaded, not downloaded, but they have put this inside their in their syntax. So if you go inside these tutorials, you will get a lot of. I'll show you also. Let me show you how many examples do we have. I have also never seen these, but okay. So currently they have only MNist here. They're adding slowly other things also. Okay. So we have MNist here. Then we do the input data also. Input data. Let's say we do this. Anybody remembers the syntax that is called a read datasets? Read datasets expects from you is that it requests you the input data dot reads is first is the train dir. Where do you want to keep the data, right? You can see all these things written here, right? Train data, fake data is equal to false. Yes, we don't want to fake data. One hot. Everybody remembers one hot encoding, right? That we did last time also. If you have any doubts, please ask. Let me know. The current default D type of the data is float 32. That's good for us. Reshape equal to true. Validation is equal to 5000. That's correct. Seed is equal to none, and source URL it is written here. So the URL is actually here from where it is going to download. So you don't have to tell it the download for it, right? We will just say where do we want to keep the data. So I'll keep the data in. I'll keep the data in MNist underscore data, right? This will create a folder there, MNist underscore data, and I want the one hot encoding to be on. So sorry guys, I don't have space to write because of this true. Okay, so what has happened here is that now by default, if I see and go in my data section here, so I might have a MNist dataset in my data folder, right? I'll show you. I have the data folder and see here is this MNist data, and all the four files are here. Which four files? If you remember, we did this also. MNist right, these four files that we saw, yes, that also. If I'm not wrong, we have done this I have shown you this website, I've shown you what data set it is, right? Correct? Correct me if I'm wrong. Okay. So now what we have done is we have downloaded the data and it is in the one hot encoded data sets. Right. Now I did one mistake here. I should have first of all said import warnings and warnings dot filter warnings and ignore. Why I am doing this? Because I don't want to see this all warnings here. You can see this is just warning. So I don't want the warning to be displayed every time. Just don't want it. So now you will see no warnings. Correct? Now let's see what is inside MNIST. If we check the type of this, so it says it's a dataset type of a thing. Let's see what things it can help us. Okay, so it has actually three things: test, train, and validation. Let's go inside what is this test train, and you can see that there is dot index and dot count. It means it's actually a tuple. It's actually inherited from a tuple thing, right? Let's go inside train. Train may, if we see, there are images and labels, right? Let's go to images and then let's see what is the first image. First is this image. This image looks like something like this. Let's do one thing. Let's print this. Let's plot this image, right? How do you plot this image? plt.im show, right? But im show will take two things. What? At first you need to make sure that your image is a 2-channel or 3-channel image. But if you see what is the shape of your current image, currently it is 784. 784 is not a valid image, right? Our image should have a width and a length, height and width simultaneously, right? So there is no. So what you have to do is that you have to do a reshape of this also. We know 784 is a square of 28 cross 28 and we know these are the images of 28 cross 28. Now you get 28 cross 28. We'll do a 1 also. Why? Because I want to show that this is a 1-channel image. Now if I do a plot, what we can do more is that we can make it gray so that you can see the actual color. This is how it looks like, right? So the first image looks like this. This first image looks like this. What I can do is I can print the label also for this corresponding image. I'll say print MNIST dot train dot label, but I have to make sure that I'm giving it the same number. So if I've given 0, then I'll give 0. Because this is one hot encoded, now the data is in one hot encodation, and you can see 0, 1, 2, 3, 4, 5, 6, 7, right? So you can just say control Z. I can make a function out of it, and I can say plot underscore image, and we can accept a number from the, let's say we want to print 59900th image. This is actually a 0, 1, 2, 3, 4, 5, right? I'll take a pause here. If you have any questions, queries, please ask. So what MNIST is giving you? MNIST is giving you 3 types of data. If you see here, if you pay a small attention, it says 3 things: test, train, and validation, right? So now what you did was you went into train and then you said how many things are there? There are actually 2 things. There is images and there is labels also. So labels and images, imagine there are a very long list, a long array, where for every corresponding image there is a number written there. So what I'm doing is that I'm asking MNIST that inside your train data set, if we have images, give me a image called num. Num is actually a function here, right? So num is actually containing 599. So what is the 599th image? Just try to plot it. Now because if you see the shape of MNIST train images, it is actually, what we are going to do is now we are going to make TensorFlow variables. So to store all these images, weights and biases, we are going to make placeholders, variables, and constants. If you remember these definitions, so what we are going to do, we are first going to make a tf.placeholder. This placeholder will keep all the images, and we'll also have a y that will be that will a y that will contain all the labels, right? For every image there is a label. So what will the model do? Model will try to learn all the features from the image and try to map it to 1 2 3 4 5 6 7 8 9, right? So what we are going to do, we are going to say tf.placeholder. So first is actually the d type. D type is df.float 32, correct? Then it asks for the second thing is that is shape. Shape is equal to none. No. We don't give shape is equal to 28 cross 28. We give it the full image. We are not going to do the unfolding of the image. We'll let it remain flattened only, right? Now we are going to make the weights. How do we make the weights? Weights is equal to tf dot variable, right? By default we are going to initialize them with zeros, correct? How many zeros? 784, the number of inputs, and the next column output will be 100 only, right? So see, what is happening here is that we are creating a variable called w. So our neural network will look somewhat like this, but sorry, we don't have so many. So let's say this is the input, but we have only 10 outputs. This is the input layer. Input layer has 784 columns that we already know, and I think okay, and this is the output, right? So what is happening here is that you have 784 inputs of an image inside your input layer, and then you have 10 outputs. Now how many weights will be there inside? Let's say that this has to connect to every 10 of the outputs. 3, then 4, then 5, then 6, then 7, then 8, then 9, and then 10. So this is just one input. Then you have 783 other also, right? That means number of weights we will have inside our thing, right? And I did a mistake, sorry. I should have written it 10, I have written it 100, sorry. Right, these are number of the weights. Bias is 10 only. Why 10? See, because you will connect this 784, let's say these are 784 and these are just 10, right? 1 2 3. Where are the biases connected? On the this end. Now once you're done with this w, it's not here, I lost it. Okay, so see, what is this is your inputs, right? These are your inputs, and let me change my pen. This is your output. Now how many outputs do you have? Only 10, right? Currently I am drawing just 5. Now how are these connected? These are connected somewhat like this. So weights are connected to every node, right? Everything is connected to everything, right? So you can what you can do is, how many weights will be there? Input into number of output, right? Input into number of output is equal to the number of weights. But how is the bias connected? A bias is connected somewhat like this. Let me give you an example here. A bias is connected to every output neuron like this: b1, then b2, then b3, b4. Or you just imagine that bias is nothing but bias is actually a input only, but that input value is 1. So let's imagine this is x0 here, and you have input called from x1 till x784, right? These are inputs. Now just imagine one thing, only one thing, that if you have outputs here and these outputs want to connect to this x0, how many lines will you have? If you want to connect this x0 to every output, how many lines will you have? 10. So the bias will be, so what we are currently doing is we are just making it for one layer, right? So if you are making it for multi-layer, then you have to do it for every layer, from here till here, then for here. So you have to do it for every layer. How did biases came up? So bias, imagine bias is nothing but actually an input called x0 whose value is just 1. Now let's say that we have declared these three things, x, w, and b. These are the three things that we want to declare. We also want to make a y also, correct? See, how I am going to declare y is very important. I will say tf.nn dot softmax.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
So it has no option. So what it will do, it will go with the maximum probability and it will say, okay, because the weights are more, you are allowed to go, right? Whereas what is softmax function? Summation of e to the power minus z above e to the power minus z. So what this actually is doing is, it is taking all the probabilities of all the things and then it is making sure that the probabilities ka sum is equal to what? 1. So let's say that we are doing a MNIST problem, right? Where what are the different outputs that we can have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we can have 10 outputs, right? So what will the affine do? Affine for every output. If I show you, just give me a second. So whenever your output is there, just imagine these are the 10 outputs, right? And you gave a image of 5, right? What you did, we gave a image of 5. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. These are 10 outputs, right? And let's say this is the fifth one. Sorry, let's say you gave the fourth image, right? You gave the image called 4, right? You gave this image that was looking like this. Now what is happening? Now the neural network has done all the calculations and it thinks it's the fourth image, right? So what it will do, it will give probability. It will give probability for every class. It might be high or low, but the model will, at every output, model will give some probability that this is this probability. I think probability of having a 1 is this, probability of having a 2 is this, 3 is this, 4 is like 98%, right? And it will give probability for all. Now what you will do, you'll pick the maximum one. Now who is giving these probabilities actually? Softmax. Softmax is distributing. So Oman is saying that, so it is just converting data into probability distribution. Yes, totally correct. Totally correct. It is converting the data into data probability prediction. So softmax is converting all the numbers into probability distribution, whereas the sum of all these probabilities, all the probabilities that it is giving you out for all the outputs, the sum of all this should be equal to 100 or 1. I mean, if you're taking in terms of percentage, it should be 100, and if you're taking in terms of probability, it should be 1. Yes, I was asking one thing, that is this photo saying the same thing that I've written in this highlighted cell also? Yes. So we have converted this operation that is showing in this image into this one line, right? Softmax ka code, I mean, you can see the function. The function is if you see the softmax ka function, it's e to the power minus z upon summation of e to the power minus z. If you want, I can send you all the sheets with all these formulas and all, right? So we asked, first we did the affine, we did a matrix multiplication of x and w, then we added bias into it, and then we did a softmax of the whole thing, right? We have done this thing, right? This is the one that we are going to calculate. This is the y that is being calculated, but we already have the y that is with us also, right? That is called y actual. We also have the y actual with us, so we have to create that y actual also. That is called dot placeholder. We'll create a placeholder for that. Placeholder should be of 432, and the shape should be, can anybody tell me what will be the shape? That will be 10 only, right? Why it will be 10? Because our image will have only one thing, right? If this is the image, the output will be 4, right? Why I am giving 10 here? Because we did a one hot encoding. You remember on the above, we did this one hot encoding here at this point. Now what does one hot encoding does? One hot encoding says that your data is actually not in the form of 1, 2, 3, 4. Now it has converted into zeros and ones, and you can see it here very much correctly at this instance. Whenever you are writing 5, you are writing in this format. So now what is going to happen, that for every image the answer will be in 10 length, right? That's why I'm giving this. Now what I'm going to do, I'm going to do the cross entropy. What is this cross entropy? I'm telling the neural network that you have to go back and do all these things also. So what I'm doing, I'm saying him to do a reduce mean. I'll tell you what I'm doing, don't worry. Reduce mean of tf dot reduce sum of what? Y minus ya minus tf dot log of y. I've done the sum here, and then reduce mean of this, comma reduction indices is equal to -1. Not -1, it should be 1. I know this is a bit tricky, but can any one of you want to try this thing? What is actually happening here? Okay, I'll tell you. What is happening here is, at this particular step, what we are trying to do, we are trying to calculate the errors for back propagation. What we are going to go, we are trying to calculate the errors. And you remember error was actually what? In the last class we discussed this also. What was error? Error was nothing but y actual minus y predicted, right? This is what I've written here also. This is y actual minus log of y predicted, right? Now what I'm doing, because y actual and y predicted will be, let's say this is the output for all the cells. So it will have some y actual. Let's say it is the image of 4, right? So 4 image pe y actual will be 1 here, right? And other than that it will be 0, 0, 0, 0, 1, and then 0, 0, 0. And let's say it's giving some probability 0 0.01, 0 0.02, 0 0.1, let's say, and at here it will give 98. So what you have to do, you have to minus all these things, right? And then add up. I'm doing the same. I did a minus ya minus log of tf log y, and then I did a sum of it, right? Reduce sum of it, and I've reduced it to the indexes, first index, right? And then I took out the mean of it, because it is the cross entropy is the mean actually. You divide by the number of observation. That is called the cross entropy. So you have the cross entropy with you now. I'll take a pause here. Have a look at the screen.
This reduction indices one, this I couldn't understand.
Okay, so see what is actually happening is that these why we wanted to go with the numpy also, but okay. So imagine you understand these are outputs, right? These are output neurons, right? And let's say the image is of number 4, right? So one hot encoding will say this is y actual. What it will say y actual? It will say ya upon 0, 0, 0, and it will here say y1 z1, right? And then 0, 0, 0 for all. And what will your y predicted say? Y predictive will give values for everything, right? It will give something. Let's say it gives 0 here, then 0.1 here, 0.1 here, then 0.2 here, right? And then let's say it gives here 0.9. Let's say it gives 0.9 here, so it will be 0.02. Let's say it gives here 0.9 and something. So what you have to do is you have to minus these things first. This is what we did also, right? We did a minus here, and then we got the answer. Let's say answer is here, and then we get the sum of this. But this is only for one image, right? We want to do it for all the images. So what is happening? I'm saying it to the model, that model do it on the first index. Now if you see properly, what is the first index in every shape? None here. And what is this none? This none is the number of images that are going to come inside this. See here, none. Now what we have to do is that we have to minimize this thing only, right? Cross entropy is actually our error, and we have to actually what do? We have to minimize this. Now, how will we minimize this? This is called a training step. So what we're going to ask to gradient descent, we'll say gradient descent, bro, we have this thing called cross entropy. Please reduce this please reduce this cross entropy for us. Minimize what? Cross entropy for us. Correct? Okay to all? Now whatever we are going to do, what happens in TensorFlow? What is the golden rule of TensorFlow? It says that whenever you want to run something, you have to run it inside a session, bro. Ses is equal to, today we are going to use a new kind of a session. Let's say it's interactive session, right? It's actually a session only, but you can handle it very carefully, right? So it's actually made for what you call, for all your Jupyter notebooks only. So you can do a interactive session rather than doing tf.session. You can do interactive session, right?
Okay guys, a quick info, if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
I'll run it. Now all your variables are declared inside the session and they are ready, right? Now, but this doesn't do. So what I'm going to do, I'm going to start a batch of I'm going to start a range of 500, let's say. At first, let me make it 50 only. So I will run a 50 steps, 50 forward and 50 backward steps for our training, right? And I will say batch. So what I'm doing, I'm asking the data to be given in batches. And how will I get this? I will say mnist dot train dot next batch. It will automatically give me batches inside it, right? Then I have to increase this also, because how many training samples do we have? Let me check, just 1 second. Mnist dot train dot images dot shape, we have 55,000, right? So I have to make it 550. Did you get the calculation what I'm doing actually here? So what I'm asking MNist is that MNist, please don't give me all the images at once. Give me 100 images, and that I will take it in every step, right? And if I am going to take 100 images, then how many times do I have to run the loop? 550 times, because I have 55,000 images. Making sense to everyone, right? Because we have 55,000 images and I'm taking only 100 images at a time. So I have to take 550 times I have to run this thing to complete all the images, right? So what is happening now? It will give me batch X and batch Y. Batch X will contain all the images and batch Y will contain the correspondingly labels of the thing, right? I'll do nothing. I'll just say ses.run and I will run the train step, nothing. And I will do a feed dict. Now I have to feed the dictionary also, right? Because I have taken two placeholders. One is this YA and another one is this X, right? So I have to feed these X and Y also. I know the X is nothing but X is what? Batch X. BATCH, batch X. And I know my Y underscore actual is what? Batch, BATCH, sorry. Batch Y, right? Now if I run this, it will run the session for me. Enter. So now what is happening is the session is going to ask what is train step. So train step will say that you have to do a gradient descent optimization minimization for cross entropy. It is going to ask who is cross entropy. Cross entropy will say that I'm a reduced mean of a reduced sum of YA and Y. So it will go back and it will ask, okay, YA, you are a placeholder, I get it, but who is Y actually? So he'll say, okay, Y is actually a calculation of X, W and B. It will ask what is X. X is again a placeholder. You get the value from your feed dict. But who are W and B? It will say W and B are here. So first of all, why do we take batches? Okay, the concept of batches came because we don't have as much as RAM we can afford, right? because we have a limited RAM resource, right? Let's say we have 1 million images. Now, can you just put 1 million images in the forward and neural network? No, never. You have to give them like 1,000, 10,000 images one at a time, right? Because our RAMs are limited, right? We still don't have processing power that can take all the images. Now your question comes, how do we decide this batch number, right? Let's say that we take a very large batch number, right? So what is happening, that all the images are going try to go inside the network, but again what will happen, that because all the images are going together, it will go fast. Definitely it will go fast, but again the RAM will exhaust at one limit, right? Let's say that we reduce the image only to one image at a time. Now give me now I'll ask you this one simple question. Okay, you decide and tell me. So let's say that I ask you to classify let's say two animals, and you have never seen those animals, right? These are some African animals that you have never seen, right? And I am showing you only one image, and I say let's say the animals name are animal A and animal B, right? And let's say I only give you one image at a time, right? And then I say you that, Sanket, this is animal A. Now give and the next time I show you the image, I ask you that what is the probability of animal B. You will say to me that, bro, I have never seen animal B, right? You will say this to me, right? That's why we cannot minimize the number of batches also. So we have to make a certain ratio of the batch number such that the model is also getting generalizedly trained. Are you getting my point? What I'm trying to say? This is pure theory. That if you're giving a very less number of batches, then it's difficult for the model to run. But if you are giving a very large number, then you're forcing the model to learn multiple features in just one go, right? That's why you have to decide this number very precisely based on how many features in your images do you have, how difficult your image is to categorize, or let's say that if you are training on two images, that what is the difference? Is the difference very significant? It can be caught very easily, or is it very difficult to catch, right? That's how you define this batch number resizing thing. So see, why majorly do we resizing is because, see, if you're giving a HD image to a model, it doesn't make sense to it, right?
Yeah, actually, I'm not saying about resizing. Resizing also is also one of the factor, because if I resize the image to a very small size, means suppose a 1000 by 1000 pixel image, if I reduce it by to 20 by 20 pixel image, then the processing speed for that entire data will be fast enough, right? But it will minimize the features in that. So if I reduce to that to some 500 pixel to 500 pixel, then it will take some more processing time. But when I take 20 by 20 image size, then I can give a large number of what I can say batch size. But if
Batch
I
size, correct.
yeah,
I get the idea
but
what you are trying to say. So just to RAM to accommodate, so this is a very good mathematical calculation that you are doing, that if you reduce the resize the image to a smaller content, then you can give a very large batch number. But you have a very high definition image, then you have to make sure that your batch size is very limited. But you have to make sure, Sanket, here, that you have to see that you should not even reduce your image to a very small extent that even model cannot take out. So because if you go and see the algorithm, that how does the cv2 dot resize work, or how does the image resizing algorithm work, the features are somewhat lost. But you have to now make sure that at which extent do you want to resize your image, right? Second is,
yeah, absolutely true.
so see, why I'm saying this is because, see, at the end of the day, when you are resizing your image, so the next time when you are doing the prediction from this model also, that time also you have to reduce this image size.
Yes.
So I'll say it again. So if, let's say that you reduce the 1000 cross 1000 image into 200 cross 200 image, and then you made your
Hmm.
model. Now what you have to do is, then while you are predicting the images, at that time also you have to make sure that your images are reduced to 200, and then only you can do the prediction also.
Yes. So, is there any some mathematical formula, or means some kind of calculation? So, can one decide to means approximate batch size or like that?
So okay, yeah, correct. So see, I'll tell you. First is that it totally depends on the data that you are working. So I'll tell you two different use cases. One is that you're working on this thing called on a classification of nut and bolts. So nuts are cylindrical in size and bolts are hexagonal in shape, right? This is one thing that you are doing. And second is that you are working on the very minute wiring section, wiring classification. So you have a model of
Mhm.
multiple wires going inside. So have you seen that image that when multiple LAN wires are going inside server farms, right? That image
Yeah,
is given to you,
you can
right?
say of PCB,
Correct, correct,
a
correct. Or
PCB.
PCB
Yeah,
also. Correct, 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 correct. PCB motherboard connection you can also take, right? So now you're
yeah.
working on this minute thing, right? So now
Mhm.
you have to make sure that how is the model going to differentiate, right? So it depends on the data, right? So if bolt and nuts are there, they're quite differentiable at the very first instance, right? And if you're
Mhm.
working on wires, they're very minute, and it's even difficult for humans to differentiate. And how can the model differentiate, right? So the first thing is data. That your data is the first thing on which you can decide this number. Second is that people have made generic models like VGGNet, ResNet, and ImageNet. So what I generally do is that I take inspiration from these papers from these models, right? So because you see we don't have much time to experiment with this because our client is standing there, right? Second, this is the second thing, right? So what I do is I take inspiration from other models, right? Third is that I do this elbow thing, elbow algorithm. What does elbow algorithm says? It says that if you it is a generic equation for every brute force thing. So what you do is you draw a graph here. On the y-axis you have the error of your model, right? And on the x-axis you have the batch size. So what you do,
Mhm.
you start your batch size with, let's say, 1, and you go with 10, 20, 50, first 10, and then 50, 100, 200, and then you go with the maximum amount also, right? See a graph somewhat like this at this section. It is almost like a elbow, our hand elbow, somewhat like that. And this is your optimized batch size that you should take.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
This is the optimized batch size that you should always take. So first thing is your data. Your data will tell you that how much you have to resize it. So I'll tell you how do I decide this. That I told you that I take inspiration from other models. So I have seen that VGG works on the 2 to 4 dimension. So they resize the image to 2 to cross 2 to 4 cross 2 to 4. So what you can do is that you can resize your image to 2 to 4. And I have seen bigger models like the new model that I was working yesterday. It took an image of 500. So I have never seen a model with more than 500 cross 500 image. Again, it depends on your data. Again, it depends on the data. See, batch size is just one number, right? Now you have to decide multiple things like batch size, then how many layers, then in one layer how many neurons. So there are multiple hit and trial that you'll do. And believe me, I asked the same question almost 5 years ago to my mentor also this, and he was also giving me something that you will decide with this experience. And the more models you will make now, you'll get the more ideas. Slowly, whenever you will be dealing with data, you will get the idea. Okay, this is quite difficult. Difficult for the model to train. So I have to leave the model to a very specific area. So you'll reduce it to very specific area, and you'll crop it in a very good manner, right? And then you will give a generalized batch size, right? So right now what here we are doing is that we are giving it a random batch size, right? So model on itself is taking random images from itself, right, from the data pool. But sometimes, let's say that I'll tell you, I was working on this example of watermark detection. So what I was doing, I had to build a classifier model whether there is a watermark present or not. So let's imagine that you are a real estate client, right? Let's say you are housing.com, right? And now people are uploading photos on magicbrick.com also, right? So what they're doing is that they're uploading images from magicbrick.com to your portal also, housing.com also. And this is a violation of rules, right? Because magicbrick.com has its own priority images, right? They have their watermark on those images. But now people, what agents are doing to save time, they are uploading the same magicbrick images to your portal also. And now magicbrick will sue you. Why? Because you are using his images, their watermarked images. So you have to restrain the users from using those images. How will do it? So you have to build a classifier for this only. That you have to tell that this does this image contain a watermark, yes or no. So see, this is a very I worked on this problem almost 2 years back. So what was this problem? This had the same problem. So imagine this is a image, right? And similar to this image, same copy of this image but with a watermark at a very small level. Now watermarks, you know that watermark are not colored in nature. They are transparent in nature, right? And they work on the alpha channel. So what is this? That they don't even have some color on them also. So what you can do, you cannot even convert your image into a single channel image also, right? So you are asking this question, what is the resize? I'll give you one more problem. Other than resize, you have one more problem. Rather than converting your problem into a single channel image, you have to keep it now into 4 channel image, right? And if I reduce this image size, what was happening? The logo was the watermark was getting squeezed out, so I could not resize the image also. So that's why I had to take a model with the constant image also. So it depends on the problem on which we are working, right? Second, I'll tell you, I was working on this PCB wiring also. I was working here, and this was not actually a PC wiring, it was actually a car wiring system, right? So there was this engine was also in the photo, there was multiple things inside the photo, and there it has a very small slot in which images were going inside, right? Now if you give the model this whole engine and all these things, all those noise also, the model is not going to understand anything. So what I had to do, I had to crop this section first of all. This small section I had to crop this small section, and then I had to give it to model. Sankit, I know I couldn't give you a correct answer, but did I make sense to you? Because see, you can read multiple blogs. I mean, you'll read multiple blogs and multiple books. You will not get a correct answer anywhere. Even if now, once what we have done here until this 33 step is that we have taken a batch of 100 images and we have trained the model. Now let's see that how do we get ACC is equal to TF dot equals. What is TF dot argmax? Argmax what of what? Of let's say YA comma 1 comma TF dot argmax of Y comma Y comma 1. So ACC will come out to be ACC will come out to be what? Where is the ACC correct predictions? ACC dot run. So why is this not eligible to us? Just a second. Okay, sorry, I have to cast it also. Sorry, my mistake. I should say this as TF dot reduce mean, TF dot reduce mean of TF dot cast, ACC with a correction of TF dot float 32. Correct. And take it into the ACC. This is not actually ACC, this is actually correct predictions. Sorry for this thing. We have to run sys dot run. If I run ACC, what things I have to give? I have to give a feed dict of what I have given only YA, right? So y is equal to I have to give mnist. Okay, I have to give x also. Sorry, x is equal to mnist dot test dot images, right? And y is equal to mnist dot Why is it not working? Not labels. Right. And did I have removed the section? I have to put a question mark also. Okay. What is this? Says placeholder shape 10 GPU device placeholder 2 data type. This okay. Sorry. See what I did. I was giving test here and I give train here. I have to give test. Okay. Again. Sorry for my mistake. So it comes out to be 0.098. Already running good. I mean, it's not good. The probability should be 0.098, but we didn't have done much of the thing. Only it is just one perceptron, and it can give this accuracy right here, right? This is just to show you that how things will work here and how you can do what I was saying. How will you do multiple things out of it, right? What you can do, you can get your I think weights also. Simply you have to do sys.run and you have to get out your W here, right? WN you can get your weights also here. So these are all the weights and weights should be 784 into 10. These are your weights. You have your weights here. Similarly, you can have your biases also here. Biases you can have .sys.run. Now what can you do? You can do B. B.run should be equal to 10 only. Yeah, 10 only. You can do C here also. Right? This is just to give you an intuition that how will you do a change. Sys dot close. Very important. Just do this. CNNs. Now CNNs are actually a new kind of not a new, but they are one of the most fascinating kind of architecture that you will ever learn in deep learning, especially in images. So till now what we have done is we have just seen that okay, we are connecting some neurons to other neurons and other neurons to other neurons, and this is something the information is getting passed. And if you remember the maths behind this, that we are just doing a affine, then we do some activation function. It means that we are bringing some non-linearity in the data, and then we are passing it through some activation function, and then we are finally giving it to the next layer. And then this chain is going on. Things are coming in, going out, coming in, going out, coming in, going out, right? But how is this network helping the model to learn the key features, right? We learn this new and very interesting uh, 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 neural network architecture that is called CNN, or commonly known as the convolution neural network. So convolution neural network, what will it will do is it is somewhat like how do you say? Let's say if this is the original image, then to find out the features inside it, what you are going to do is you are going to take a smaller cube or square. Sorry, not cube. You will take a small green square, and then you'll apply this. You'll put this green here on the top, so it will somewhat cover like this, right? Then you will move this green spot to your right, right? Then one step down, so it will come like this. Again right, then one step down, then again right, then one step down, again right, and then one step down. Eventually this small image, or what we call it as filter, will like run over this whole image, and it will learn the important features and the aspects of the image. Right now, how does this done? I'll show you a very intuitive example here. Wait for a second. I have this wonderful thing running for us, and this is called CNN. Yes, CNN. Let me make a new Jupyter notebook. See, this is somewhat what is happening inside your. So this green image that you are seeing right now, this is the big image, and the orange image that is moving is called a filter. So what you are doing is you are moving the filter on the image one by one. You are moving the filter by one. Now, when I say when you are moving this filter on the original image, what I mean is that you are doing a element-wise multiplication on this image, and then you are summing up all the things. So if I stop this thing here, okay, it doesn't stop. If I put it here, cool. I got this thing here. Just a sec. Just give me a second. Cool. I have this picture already with me. Control C. Okay, so ING equal to. Okay, see this image right now. Right, you can see this image right now in front of your screens. Okay, I'll push it here. Okay, so this green thing, this green image, and whatever this big thing is written here, these big numbers 1 1 0 1 1 1 0 0 1 1 1 0 0 1 1 1. All these big numbers are what? These are, let's say, the pixel coordinates of the big image or the original image, right? And then imagine this orange filter where small red color me you can see these things, these numbers 1 0 0 1 0 1 0 and 1 0 0 1 1 0 1. These small numbers are the filter. These are the numbers for the filter that is going to move over the image, right? Now when this thing is moving over this thing, it is doing a element wise, or you can say a scalar multiplication. Element wise one by one multiplication means that this one is multiplied by one called 1 multiplied by 0 is 0, 1 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 1, then 1 plus 0 is 0, 0 plus 1, 0 plus 1, and then 1 is to 1, right? And then you have one more. So all these numbers, first for this one, second for this one, third for this one, and fourth for this one. Sorry, this one. So these four, this number becomes 4 and you write here 4. Similarly, what you will do is you will shift the now this filter to a little bit of your right. Then you'll have the second one. If you move it to a little low, then it becomes your, see, low and down, it becomes 2 3 4, then 4 2 3 4. This is how your convoluted features are calculated. So now do you get the idea how this thing is coming? If you see this GIF a little more, once take your time, imagine how this thing is working. It goes on the right hand side one by one is shifting, goes down, again one shifting, goes down, and this is how your final image is made. This pink image is your final image that is made. Again, I'll ask you, please take a small time to digest this thing. This is a little not tricky to understand, but a little one should pay more attention to this, how this thing is working and how is the thing going on. Because now I'll tell you what is happening when you are doing this thing. So what is happening is right now here is that if you, so okay, just tell me this thing, that let's say if you are standing in front of something, right? And then, so how do you identify, how are your images identifying you as a body? I'll tell you. So there are pixel value that are changing at the border of your body, right? So let's say that you took let's say you're standing in front of a white wall, a pure white wall, and then you're standing. How are you differentiated from a wall? Because if you open up the matrix of that image, if you open up the numpy array of the image, you'll see that your body will contain a higher pixel values and the white wall will contain 0 pixel values, right? Now whenever your body to wall is there, whenever the boundary of your body is there, right, at that particular instance your pixel values will be changing, right? Because your pixel value would be somewhat like 230 235, and then suddenly the image of white will be 0, right? So whenever you will be running this filter over your image and then doing this multiplication, what will happen that it will largen up the broaden up the areas. It will broaden up those border areas for you. I know it's not easy to understand, but don't worry, I'll show you things. I am putting his blog in your chat also, so that you can open up anytime and then see. But this is his blog actually. So if you come down here, what is happening here is this is what the image looks like, right? We have already discussed this thing that 255 is sheer black and white is almost like zero, right? Now what is happening is, let's say this green was your image, this green thing was your image, and this orange one was your matrix, right? For your filter, right? What you're going to do is you're going to put this 3x3 image over this 5x5 image and then do a multiplication. Multiplication say you will be getting a convoluted feature. Right now, if you understand this thing, okay. So first of all, you know this thing is called a filter. Sometimes we call it as a kernel also. This orange thing as a kernel or a filter also. Now see, imagine what you're doing is that you are, let's say this image was not made up of 0 and 1 only, but it was made up of 0 to 255. Now what would be happening is that the larger values, the values that are two. So imagine there are two numbers in front of you. One is called, let's say, 5 and another one is 230. Now, if you multiply both the numbers with, let's say, 10, which one will become more larger? There are two numbers, 5 and another one is 230. 230 is the person you who are standing. This is your body pixel, right? But the white background will contain values from 0 to like 10 only, right? Because this is the white wall, a pure white wall. So let's say even if we say that there are some tints and something, so the color density will be, or color pixel, let's say it's 5, and let's say you're multiplying the same with 10, so your 5 into 10 will be 50, but your 230 when multiplied by 10 will be 230 sorry, 2300. So what is going to happen is that we are going to do a matrix multiplication and then sum up all the things, and these are gathered here, right? All the things are gathered here in this area. Now you might say that what has happened if you have gathered larger values, and then there might be some lower values also, because if you are running this thing on a white border also, let's say if everything is 5 multiplied by 10, everything is 50, right? Doesn't make sense. 50 ko you add up all, it will become the same value, right? Now I'll tell you how things change here. When you run this, let's say this was your original image, this deer was your original image. If I zoom in a little bit to show you, this was the image. If you see clearly on my screen, this was the, let's say, image, right? And when you do a filter of this identity filter, it will return you something like this. If you return this filter, it will return you something like this. If you return edge filter, this is something like this. If you return -1 -1 -1, this is called blur, sharpen blur, edge blur. Then you have box blur, Gaussian blur. So this will happen if you multiply your image with this filter and you run this filter on your image with stride equal to 1. So your original image from here, this thing, this particular thing, this thing will change to these things depending on which filter, through which filter you are multiplying it. Make sense? Now let's say if you're analyzing this thing, this image, what has happened here is that you can easily see that the animal's border are now created or sharpened here, right? You can more easily visualize the borders of the animal, right? Rather than with this original image at here, where the borders were not much not, they were not much in the same group. Now you can easily do a spread out with just one convolution, and this is just one. We'll like replicate it like multiple times to get more value out of it. Make sense? Now you understand why we are doing this, running a filter over the image. Now this depends that what are the values that you're using inside your filter. Your filter might do a blur of the image also, and it might do a sharpening of your image also. And this edge detection is the something that we want to do right now, that we are very much interested to know that what is the edge of that animal, so that we can differentiate if it's a cat or a dog, right? And this is the perfect example how things are working for us. Correct? Everybody gets the idea? Cool. Now, once you have done this filter and you have got a very edgy image, now what you want to do is still on this edgy image, you want to capture the maximum values. So now imagine that what you have done is you have multiplied a larger number with a more larger number, right? So your smaller number will become smaller and the larger number will become more larger. And then also you are saying that you want to have the maximum values only. This step is called as the second step in our CNN network, and this is called max pooling. This is called as max pooling. The first thing was running a filter over your images, right? That you have already run successfully and you got everything out of your image. Next, what you're going to do is you're going to do this thing. Okay, again, sorry, one more thing to show you. Let's see. With different filters, you have different feature maps available to you. Let me zoom in so that you can see it more efficiently. Can you see it now? So what we are doing is we are trying to run a filter over this, and through different filters, you can see different images are coming out. Different outputs are coming out, right?
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Make sense? So what we are going to do is next what we are okay. Now in this, one more thing I want to tell you is that you should have asked me this question, that in this particular GIF that we are seeing here, we are moving the orange filter with one step only. Like see, one step it's going ahead, right? You might argue this to me that okay, this is also arbitrary, right? We can move it to two steps also. And my answer would be yes. You can move it two steps, you can move it three steps, and if it's a very large image, you can move it like more steps, right? So it depends on the architecture of your image and the architecture of the filter that you are choosing, right? Now, when I say how many steps do you want to move, this is called a strides. What it is called? It is called strides. So in our case, right now, the GIF that you're seeing, the stride is equal to 1. When I say stride is equal to 1, it means that you will be moving your image, the kernel, with one step ahead. From left to right, your kernel will be moving one step. And similarly for going down also. So it's if you see, if you quietly observe that your kernel is shifting downwards with just one row only. It might have shifted to two rows also, right? But because you have set as strides as 1 comma 1, 1 comma 1 means that you will be shifting column to 1 and to row also you will be shifting 1. Make sense to everyone? So till now what we have done is we have taken some arbitrary matrix called as the kernel matrix, right? Then we took some arbitrary values inside it also, some random values. Then we have taken this thing called strides. We have by default we are giving it at 1 comma 1. It means one row to the left and sorry right and one to the down, right? So we're cherishing all these things as of now. And then we have got out something that is called convoluted feature, right? Now one thing is for sure that your output is going to shrink from the original image, right? So originally, if you see in your example, your image was around 5 cross 5, and now it has come into just 3 cross 3. Let's move to the next stage where we have done this convolution. Now our next step would be,
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
to get more more edgy features out of it. So what we're going to do is after we have got this feature map here on the after once we have got this feature map on the left hand side, what we're trying to do is we'll again find out more maximum numbers out of it. So what I'll do somewhat. So let's say on the left hand side that you're seeing is the convoluted filter. I mean, this is the thing that they have returned you after you have done your feature mapping, right? Or your mapping is done. You ran the filter over your image and this is done. And this is the output that you see on the left hand side. Now again what you will do is you will say that I will take a 2 by 2 ka square, right? I will take a 2 by 2 ka square and I'll pick up the maximum values that are present inside the image. So what is going to happen is currently your answer is in the shape of 4 cross 4, right? And then 4 cross 4, and let's say that you are making a 2 cross 2 circle, and then you have to find the maximum value. So in the first 2 cross 2 you find 6, in the 7 you have 8, in the third you have 3, and in the fourth you have 4. Make sense? Even this max pooling thing has this size that is called 2, that you can see right now it's 2 cross 2, and it has strides equal to 2. Why? Because you don't want to get the maximum number again and again. So let's say if you are taking this, once you have taken these values, you should move to the next thing, right? So let's say this was your first filter of 2 cross 2, and now you have strides of 2. It means it will shift to 2 rows and 2 columns. So this will be your next row column. Next question will be who's the maximum? You'll say 8. So you can see all the values are transferred from 6, then 8, then 3, and then 4. Everybody gets the idea. So see, the max pool thing is nothing but let's say if we go up again, till here where you just got this new answer from your after you have run your filter over your image, this is called convoluted feature, right? Now this convoluted feature is actually nothing but a edgy photograph of your original photo, right? So it contains more edges, more clear edges, and more things, but they're still not much clear to you, right? So then what do you want to say to the model is that model give me more heavier amount of images, give me the maximum number of pixels in a particular area. So you say okay. So what you're going to do is the final thing that you have here right now in the pink 434 243 234. This thing is called a convoluted feature. Now you'll go down. Now once you have got this image, your second step is to take the image and run again a 2 cross 2 filter over it, right? And then with the strides of 2, it means the next step is not one step but two steps, right? So your first square will be 1156, right? This one, right? This one is the first square. How much is your total maximum number in this? 1156 is 6, right? So you give 6 here. Then your second, because it's the stride is 2, so your next square will become somewhat like this 2478, right? Maximum thing is 8. 8 will come here. You have next thing as 3 2 2 1 2. Then your 3 is equal to 1. Sorry, 3 is not equal to 1, but 3 comes here, right? Then your fourth square, then this is a fourth square 1034, which is the maximum value. 4. 4 is shifted here. These are the two main examples that you should understand at the first stage. One is the convolution. Convolution means that you are running some random value of filter over your original image, doing element multiplication, and then adding those things, and then having a convoluted filter. And over that convoluted filter, you should have run a pooling kind of object. So you can have a max pooling where you're picking up the maximum values. You can have an average pooling where you're doing the average of the particular pool, or you can have the sum pooling where you're trying to do the sum of that pooling thing, right? But now between these are the two major steps in convolution CNN terminology, right? But in between these two steps, there is a lot of thing that happens, right? So let's zoom out of this and then let's try to cover them one by one what we have missed till now. So see, whenever you're running this thing that you're seeing on your screen, this filter, whenever you're running, you will never run a single filter on your image. This is what CNN is. You will run multiple filters with multiple different values, and that thing is known as the depth of the CNN. So whenever you will say that from keras.layers import CNN, right, or conv2d. So actually the name in the Keras library for this particular layer is called conv2d. CONV for convolution, CONV, and then 2D. So it means that you are using convolution neural network for 2D images, right? So what you will do is, at that instance, it will ask you that how many filters do you want to run on your image? How many random filters do you want to run? That is called the depth of the filter, right? Now imagine this photo here that you're seeing here this is a image of a boat that is standing somewhere near the deck, and you can see water and some grass. Now what it is that right now you have a depth of 3. It means 3 different filters will run on this image and they will produce 3 different convoluted images. Did I make sense here? Imagine that this thing is called as the depth of the convolution. Now depth of the convolution means that right now till this before this example we were running only one convolution, right? We were running only one filter over the image and we were getting only one output of that image, right? Now what the model is saying that we will not run one, but we will run multiple. So in this example that you're seeing in front of your images, right, in your screens right now, where this you have a boat inside, where you have a boat near the surface of the earth, you are running 3 different filters, and for running 3 different filters you will get 3 different convoluted features, right? So you cannot control the value that what is going inside the what is the value of those filters, but yes, you have to definitely tell the model that I want to take these many number of filters, because this will increase the depth of your model, right? So you will say, let's say I want to take 25 different depth of the model, or I want to take 1,000 depth, for the first image. I want to have 1,000 different convolution filters, because eventually their size is decreasing. If you see closely, if you remember the GIF, the height and width of the image is going to decrease, right? But 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 the depth is going to increase. So earlier, let's say if the image was of 1D, sorry, of with one channel, now it is going to convert it into 3-channel image, because you have run three filters on it. Let's say you ran 500 filters. So for one image, you will have 500 different outputs, right? So see, why we are increasing the depth is because, see, ultimately the model needs to get some or the other final decision thing. See, ultimately the decision is taken by the last layer, right? And you remember that you have to ultimately mold your model to take to the dense layer. And you remember the dense layer are nothing but a single column rows, right? So when I say dense 1024, it means that this is a one column, but 1024 different 1024 different rows are there standing. So you can imagine 1024 blocks one over the above, right? So you have to somehow converge your model to have, so you're converging your 2D image, which has height and depth, and you want to convert it into a depth only thing, right? So let's say that your image was somewhat here like 50 cross 50 image. So what you're eventually doing is, whenever you run a convolution filter, you're reducing its size to, let's say, 35 cross 35. But when that image is converted into 35 cross 35, you're increasing the depth of it, because you're not running single convolution filter, because you're running, let's say, 10. So if the original size was 50 cross 50, now it was converted into 35 into 35 into 10, right? When you will run more, it will convert it into, let's say, 15 into 15 into 100, right? And then eventually you will be having only 1 cross 1 cross 100. What is
Shivam,
happening
Sanjay.
is, rather than running one convolution filter and having only one answer to the model, what we are doing is we are running 10 and hundreds of filters, so that eventually we are like, in the end, we are clubbing them all, so that we can. So if you have done ML, you must have heard of this thing called ensembling of all the models, right? So let's say that you don't want to trust only one model, but you build 3 different models and then you club all these models. This is what is happening here also. We are not running only one filter, but we are running 100 different filters, and then at the end we are clubbing all their results, right? Let me just scroll it up. So when I say filter or feature, I mean this thing, this small yellow thing. that is not known to us. This is the random matrix that we know. Other images might have different convolution because this image was very symmetrically designed. That's why you were able to do this with the -1 and 8 combination, right? But let's say your image is a little tricky one where the polar bear is standing in front of a white image only. So everything is white. At that particular instance, your convolution filter will be something else, right? And now coming to a second question, that are the random convolution that we are choosing, is that correct or not? Who will tell this thing, right? So what will happen is that when you are doing a convolution, you will have some output, then again you do some convolution, then your output, and at the end, the model will try to predict out something, either cat or dog, right? But then your y actual is standing in front of you also, because in the training data set you give the y labels also. So your training label is also there. Whenever it will predict out something, let's say it predicts out the probability 0.60 for the cat, but it is actually a cat only. So your model will say, bro, you are doing good. You are doing good, that you are saying this is 0.64, but no, you're not saying it totally correct. This is actually 100% cat. So what you do is you go back, right? Go back and increase your probability. Try to increase your probability by 0.4% so that our error is minimized. Currently, we are having an error of zero point 0.4. So go and reduce this error by 0.4. Now the back propagation guy will go and he will say, okay, wait. Now convolution filter you and you and you three are combining, creating an error for us. So we are changing your results to this level so that you decrease the error. So eventually, whenever you're doing a feed forward and backward propagation, feed forward, backward, feed forward, backward, feed forward, backward, you're ultimately converging your model to minimize the error and maximize your accuracy, right? So at that particular instance, you at the end, when your model is converged to let's say saturated with no more error decreasing or no more accuracy increasing, at that particular instance, whatever convolution values you have, those are the perfect convolutions. And if you run them on your image, you'll see, okay, this is the perfect edgy thing, and then it is trying to classify. Okay, now coming back to the problem where we were, that if you are doing, let's say you have done you have just ran a filter over your image and your image is converted from this simple image to this more enhanced edgy image, right? Now, if you go more thing out, so first thing that you were doing was that was called depth. Now, what is depth? Depth means just that if you are running different types of convolution filters on our images, then you'll get different results, right? So if I'm saying I'm running a depth of 64, I mean I have 64 different features which I ran over my image and they gave me the output, right? Second thing is strides. Yes, strides, we already know strides is what? Strides is the step size. That how many jumps do you want your filter to move? So in the GIF, we were seeing that our model was shifting with one space, right? One space to the right, it was shifting. So that time it was stride equal to 1, but if you do stride 2, it means it is going to jump. It is going to take 2 steps, right? Oh, then we have one of the important thing that is called padding. Now you might, if we go up again, if not, let's not go up again, but if you see this thing right here, okay, this is the dynamic one, this is it, right? Let's say if you are here and let's say that this is the first step, right? It has completed. Now let's say that you have a stride of 2. Where will be the next uh, stride position will be? Stride position will be almost somewhat here. This and this, right? So you will have an exact combination of how many. So can any one of you tell me right now that what will be the output shape? So if you are running a 5x5, if you have a 5x5 image, and if you are running a 3x3 filter with a stride 1x1, you have an output of 3x3, right? But now let's say if you have an image of 5x5, you're running a filter of 3x3 with strides of 2x2. what will be the output?
2 by 2 matrix.
Very good. It will be a 2 by 2 matrix. Take your time, just do the imagination. Just move the filter in your mind, you'll get all the answers automatically. Right? And if you want to create a formula out of it, it will be the original image size minus the convoluted image shape plus the strides. So 5 minus 3 plus 1 is 3. But if you have 5 minus 3 plus 2, it becomes 2. Everybody did the moved in their minds? Close your eyes and then if you move this, you'll get the answer as 2 cross 2. I'll do it for you right now. So the original orange one where it is the first one. Then second I have made is the second one. The third one will be somewhere here. Third one will be here. And then the fourth one will be here. So strides you can. So this is what is called as the strides thing. You already know it. Okay, yeah. So we were talking about sorry. We are talking about the padding part. Okay. Now let's take an example that you again have a 5 cross 5 image, 3 cross 3 filter, but you have a stride of 3 cross 3. What will happen right now? First is here. I can draw it for you. First will be this. The third one will be, the second one will be here. But at this particular instance, you have only 2 columns. Where is this third column? Right? So what you do is you fill it with zeros here. This is called zero padding. When you don't have enough number of columns to fill your things, what you do? You fill it with zeros, zeros, so that now you can have a 3 cross 3 padding. Similarly, if you go down, you will have this problem here also. You won't have an extra row. So what you will do is again you will go this, you'll fill 0 in this. 0, 0 and 0. This thing is called padding. What is called? This is called zero padding. Right? Let's move to the next thing. This is called zero padding, right? Now, once you have done all this, you have run the feature with multiple depth and you have some padding or you have some strides, right? Then you'll get some output out of it, right? Similarly, like you got something here, like 4, 3, 4, 2, 4, 3, and 2, 3, 4, right? This pink answer you'll get, right? You'll get an image. Now, if I say that please run it through a ReLU. Now, if you remember ReLU, what was ReLU? ReLU used to give you the answer as it is if the number is greater than 0, right? But if the number is less than 0, it will convert everything to 0. So what we are trying to say is that if there is a positive number, let it go and fly. We don't care. But if something is negative, we are going to convert it to 0. So what will happen is if you give a image, see if this was if you can see clearly, let me zoom in. If you clearly see from here, you can see it right now. If you clearly see from here on the left hand side, this was the output from the feature, one of the output from the feature, and then you ran this ReLU thing. This is what has happened. Only non-negative values are there. All the negative values are gone. You can read there also, it was written black is equal to negative, white is equal to positive values. So all the whites are there. Blacks are all gone. Right? Now once you have done the you have done the ReLU, then you have this thing called pooling that we were just talking about. Pooling is nothing but it is used for reducing the dimensions but retaining the most important features. And this is what we were talking about, that the pooling can be of different types: max, average, and sum. Read it here. These 3 lines. One of the best, I think this is the articles. He's a friend, that's why I'm bragging this, that this is the best article, but this is one of the best. Right, and especially for new people who just started learning about deep learning, this is one of the best because it is not using any kind of a jargon word. Otherwise people they use like non-spatial locational background of the image will not, and then you won't have any idea what is going on, right? So what is happening is, this is a 4x4 image. You take a 2x2 matrix over it. You do a max pooling. 6 is maximum, take 6. 8 is maximum, take 8. Here maximum is 3. Here maximum is 4. Take all these. So what you've done is, you take your original picture. You do some feature of you ran some filter. You got the convoluted filter. Then you ran some ReLU, and then on the ReLU you ran a max pooling. So eventually, what will happen? Let's see if you ran the image on a max pooling. This is what will happen. I know this is making no sense to you, not to me also, but somehow this is making sense for the model now. Model is able to understand. Okay, this is dog, this is cat. Now I understand. But if you will see this thing for a very large image, right? You will understand these things also. Let's say if you have an image of 1000 x 1000 and then you're running this thing, you will definitely capture these things. That what it is doing is, ultimately all these buildings are now reduced to a very lower level. This much big, this big image has been now reduced to this small image, right? And now if this would have been a high quality image, you could have easily seen that all these tall buildings are now reduced to a smaller level in the things, and we are reducing the dimensionality, right? This is all what we do in convolution. At the end, we get this convolution and we get somewhat architecture like this. Now just pay attention for the last moment, right?
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Extreme left was your original image, right? Then you ran some filters on it. Let's say you ran 3 filters. So the size is 3 filters are here. Now out of one image, you can get 3 images, right? 3 different outputs for 3 different filters. Now on these filters, you ran a pooling. Now pooling say you reduce the size of your image, right? Again, on this answer that you got from the pooling, you ran a convolution. Again a convolution. Now let's say you already had 3 images. Now you ran 3 again. So 3 for each image will give you 9 images, right? So you'll have 9 images. Then again you ran a max pool. Then again you'll do pooling. So eventually what will happen is, your image size, if it was 50 cross 50, this will end up to, let's say, 7 cross 7, or let's say 1 cross 1. But its depth will increase. Its depth will increase to a very large level. And this will ultimately convert it into a dense neural network. And this is what our idea is also. Right. Let's import the first thing first. Import Kiras, our best friend. Then we have NumPy, a second best friend, as env. Import matplotlib.pyplot as plt. Okay, I can remember these only as of now. Okay, so how many of you face problem in downloading the cat dog dataset? Eventually, everyone should have this problem. And I told you the solution also. If you are you have to download cat.dataset, then make sure that you are activating your Kaggle profile through your phone number also. Then only you will have this download button activated, right? If not, it won't work. Let's go to keras.preprocessing.image, and then we have image data generator. Then you have from keras. Okay, let's do the layer 1 and afterwards. And let's make the data generator. Data generator is, today let's make 2 data generators, not one for validation and one for but I don't have the images for both the two. Okay, let's split it accordingly. Okay, We'll do this. Okay, image data generator, what does it take? It takes multiple things. How many things do you want to give? Let's say rotation range. Rotation range should be what, 40. I'm sorry, I have to see this thing with shift range. How much? 0.2. Then we have height shift 0.2. Right, we can, what else do we have? Height, width, and then okay, we can do a flip also. Let's do this as of now only. So our data generator is ready. Data gen is ready. You can see all the things by going here. It can tell you whatever things you have taken, it will do. I forgot to tell you one thing, that if you remember in the previous sections when we were doing MNest, what we were doing was we were taking the whole image and then we were dividing it by 255. Why? Because we needed to normalize the image, right? Now when you are using image data generator, you can do the same with just one thing. You just say rescale, and I think we forgot this thing in last session, so I'm telling you, 1.255 dot. So now what will happen, all your images will be through your will be multiplied through divided by 255, right? Again, your data generator is activated. See, data generator, by saying it's a generator, so it will not give you all the values at once. It will give you the results in batches. And I think we discussed this last class also, where we read this, that generates batches of tensor images data with real-time augmentation. The data will be looped over in batches, right? Arguments, feature wise is boolean. You can go through all this. Next we are going to do is that we have made this generator here. Now what we can do is we can directly start with our modeling part, right? Would anyone like to help me in preparing the model? From Kiras dot model import sequential, right? From Kiras dot layers import conf 2D. Today we are going to do conf 2D, then max pool 2D, then we will use flatten, then we will use dense. What else should we use? That's it, right? And from Keras dot activation, let's import activations. What kind of activation do we need? Relu and softmax. Softmax, right? Then Keras dot losses. Maybe we'll use categorical cross entropy, right? And from Keras dot optimizer, import HGD and RMS prop. Let's activate all these things. I think we are almost done. We have taken layers, we have taken activations, then we have taken losses, optimizers, nothing else, right? Let's make the model. And before we make the model, let me shift this, drag this here and close this thing out. We get more space, right? Now let's make the model. Model is equal to sequential type of a model, right? Sequential type of model. Now let's pay a little bit attention that how do we make a model out here, right? Let me give some space and then okay. First of all, what I'll do is I will add a conv layer. I am not going to convert this image into a 1D image by doing a flattening. This time I am going to give the image as con 2D as it is. Now you remember that when we were running the convolution in practical, we had this 2D image. We were not doing it flattening. We were not doing it row major or column major flattening, right? We took the image as it is, right? So you are going to take this image model.add convolution 2D. We're not going to do the flattening part. Now let's see that what does this conv 2D takes place. Now conv 2D first takes place filters. Okay, let's see what filters is. Then we have kernel size. Then we have strides. If you don't give strides, strides are by default 1 cross 1. Then you have padding, then you have data format, then you have dilation. Before now, after that, all these are like default values. They already have some values. The only two things that it expects from you is one is the filters and another one is the kernel size. Now filters is nothing but it's the number of different types of filters that you want, random filters that you want to run on your image, right? And second is the kernel size. Now when you're making this filter, what should be the size of the particular filter that you're going to run on the image, right? So you're asking this the same. You'll be telling the 2D Keras that these are the number of filters that I will use. Let's say I use 64 filters and this should be the size. Let's see more deeper into this. Sorry. Okay, now one more important thing, when you're using this layer as the first layer in the model, provide the keyword input shape. So you have to make sure that you're providing the input shape, right? And your input shape is equal to 28, 28, 28. 3 means that for 28, 28, 28 RGB pictures, right? And you have to make sure that your data format is equal to channel equal to last. It means that whenever you're specifying your dimension as 28 cross 28 cross 3, here 3 means that these are the number of channels. But if you are giving 3 comma 28 comma 28, make sure that you change your data format as channel first. So this used to happen a lot when there was this framework called Theano. So Theano has this had this problem, not problem, but it has its own functionality, that it used to take the images in the format of. So Theano had this own format of having the channel first. Then TensorFlow came in, it said no, I want the channel at the last. So there was this conflict a lot. So now you have to specify, because Keras used to support both TensorFlow and Theano backend. So it has this thing called data format where you can specify that you will be providing your channel first or channel last, right? But Theano ended in 2017. So 2017, yes. So you don't have to worry much about data format. Data format should be channel last only. I think all the major DLP frameworks are taking it in the last now. Okay, coming back to the filters. Now this filter, you are expected to enter a integer here. Now integer, it means that the dimensionality of the outer space, that is the number of the output filter in the convolution. It means, let's say if you give it numbers 32, it means there are 32 different filters, random filters that will run on the image and they will produce the convoluted image. Second is the kernel size, an integer or tuple list of integer 2 specifying the height and width of the 2D convoluted window. Can be single integer to specify the same value for all spatial dimensions. So it means, let's say if you give it this thing kernel size is equal to 3, this means that you're trying to have a 3 cross 3 filter. Or if you're giving 3 cross 4, it means you want 3 rows and 4 columns as your kernel size, right? Strides is, again, you already know, so strides can be integer or tuple, same as above. If you don't specify, by default it is 1 cross 1, right? Then you have padding. I think we talked about padding also. Padding is either valid or same, right? It is saying that same is slightly inconsistent across backends with stride is equal to 1 as described here. So you should always take it as a valid one, works better. Then you have data format. These are all like numbers that are already predefined. You don't have to look much about it. But let's start with the convolution 2D that we have to make, right? Let's say that we want 32 images of 3 cross 3, right? Next, you have to give it as an input shape. Input shape, let's say that we are going to give 150 cross 150 cross 3. We have still not decided how our shapes of the input will look like, but we have decided that we'll go with 150 cross 150 cross 3. Now once you have specified this convolution, you have to specify a activation function also, right? Either you can specify here only in this con thing, you can just go and say activation is equal to, or you can specify by again saying here model dot add, and then you can have a activation is equal to, okay, we have not gone here from, so you can add an activation layer here also. I generally don't like this. I just add it here only. Activation, we love ReLU. We'll go with ReLU only. ReLU is the most important thing. Okay. Now, does someone remember after convolution and then doing an activation, what was the next step that we used to do? No? Okay. We used to have a max pool. Max pool again. Let's go. Max pool. What was max pool doing? Max pool was doing nothing, but it was bifurcating your image into parts that you specify and then picking up the maximum value out of it. Right? So it's saying that your image, let's say the pool size is 2 cross 2. It means that the image will start from the kernel size of 2 cross 2, and then out of the 4 values, it is going to take the one which is the maximum number. Right? But let's say we want to change this. How to change this? You say pool size. Pool size is equal to, let's say we take it 2 cross 2 only. Now this thing that we have written till these these 2 lines, which contain 3 specific um operations. This thing is called as the chunk. Single chunk of convolution. These 3 steps. Which one is the one? One is conv, then you have activation, and then you have pooling. These 3 things together are called as the chunk of. Now what you can do is you can just copy paste these things and then you can have more chunks. But this time you have to make sure that you're not using this input size, because input size should always be inside your first thing only. I'll increase this number to 64 here, or let's keep it 32 only. Again, I will copy this thing. Let's make 3 chunks because our data is not that much complex. Let's have 32, 34, 64, and then come here, and then you have model.compile. Right, compile me. You have loss is equal to categorical cross entropy. Let's bind it in double quotes. Then you have optimizers. Let's use SGD only. This is the one that converges the fastest. Then you have matrix. Let's use accuracy. Right. And then we'll do model.fit. But as of now, we don't have any input outputs. Let's just make the model sit here only. Right. Nothing much to do. So what we did actually here is we did nothing much. We just made 3 convolution filters. One is this 32. When we started this off, 32, we said 32 numbers of different so imagine this one image will now become 32 images, but the size will drop due to max pooling, right? Again, these 32 images will now become into 32, but their size will decrease. Again, their height width will decrease. Now these 62 will become almost like what will they become? They'll become 64, so they become more, and their height width will again decrease a lot. One thing that I forgot to tell you is that this is not the end, right? Our end will be somewhere when the output will be only 2 units, right? This is not the output, right? We have to do a flatten here. Remember? Because ultimately, see, our answer will be in 2 words, right? Either 0 or 1 in 2 letters, right? So the output layer will only have 2 neurons, correct? Model.add once is flattening. Flattening. We have done the flattening, then we might use a dense layer. Dense layer, let's say we take 1024. Then let's add activation. Let me add it here only in this thing. Activation is equal to ReLU. Then let's decrease this by, let's say 512. Again have activation of ReLU, and then in the end let's have the final well will have how many? Only 2, dense and 2, and this time the activation will be softmax. So this will almost become like this, if you remember. So our model should almost look like this.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
Does this look like the same? So first convolution, then pooling, then second convolution, then pooling, then imagine we have a third convolution also, then we have a fully connected dense layer, and then we are reducing the number of dense layers from 1024, then 5112, and then immediately 2. So this example has more, but this is somewhat like what we have an inspiration code, right? So I think we already have this data generator here. Let's add just one data generator. Now what we have to do is that we have to make a train generator. Train gen is equal to data gen dot flow from directory, right? Flow from directory, where is our data? Our data is just behind this. Then we have cat dog cat. Yes, dog cat small. We have more generator small. You all know what should be the format of this folder. The format of this folder should be, let me show you. These questions are coming to your mind, that how did I come to this number called 32, right? First of all, and then how did I take this kernel as 3 cross 3, right? So one is the experience, that slowly when you will be practicing more and more and more, what will happen is, now by seeing the image, by seeing your data, what is the dimension of your data, then seeing the complexity of the image, you will come to this number, how these numbers are coming. Secondly, let's say that, see, I am not a researcher, so what I generally do is I read papers. Now if you read the paper of VGG, let's say if you read the one of the best models that are available for VGG, you will see that these models, my code is totally inspired from it only. So if you go here and then you see, this is one of the VGG was written by Oxford people, where they made this. So if you see, this is how they have made the VGG model. Sequential modeling, then adding convolution 6433, and believe me, they have done more than thousands of iteration, and then they have come to these numbers, right? So I am doing nothing, I am just also following these people, and slowly, see, not only following these people, but when you will start your when you will start your modeling thing, when you will slowly start learning about these things, when you will be exploring, then you'll understand how these numbers vary. So let's say why I am taking 32 or 64. First of all, 32 and 64, why? Because there should be that the number can be any number, but we generally prefer them to be in the order of 2 to the power. Because if you will see the maths behind this thing, if you see the maths behind the convolution, you'll get to know that, okay, all your calculations are done with the numbers in 2 to the power 4, 2 to the power n, whatever where n can be stand from 1 to whatever the number is. And second thing is that to avoid any kind of a miscalculation, because sometimes, let's say, your measurements are not working finely, it might be padded with zeros or ones, like we generally saw in the padding, right? The padding can be a valid padding, or it can be a smooth padding. So depending, and not having not having much wrong data inside our model, we generally try to have this thing in 2 to the power, right? Second is, these are the numbers of different types of numbers that we are having. Let's say your image is a normal image with not much information, and let's say you have 1,000 filters right here. First of all, your RAM will exhaust at a very high speed. Second, that you won't be able to extract much information. So let's take an example of let's say that there is some task that needs to be done by some people, right? And the task is only for 3 people. Now if you deploy 15 people out of there, the total contribution will be equal to what you have given, but individual contribution will be very less. So that will also happen if you increase the number, let's say the 64 to 1500 something, then the total contribution will still be the same, but the individual contribution will get to really low number, right? You're getting what I'm trying to say here. Things, you might also ask that I might reduce this number also. Let's say instead of 64, I might have taken 32 only. Now if you would have taken 32, those 32, now imagine the same situation. The people, there's a job that needs to be done by 64 people. Now if you're employing only 32, Now the total contribution will now also be affected, right? The total answer that you want out of your job will also be not be equal to what you desired, right? So there should be a balance in this number, and believe me, deep learning models are not like that you sit one day, I mean, just write the code and then you press enter and the answer is there. It's a process of reiteration. It's a process like somewhat like this. You start, it's like a circle, right? You have your deep learning model here and then you do multiple iterations. You have a deep learning model here and then you do the iterations again and again. You're changing your parameters. You have your parameters p here, and then ultimately you have a boolean here. Do you say that your accuracy, your error rate decreased or not? If yes, then you go out. If no, then you again go to the circle, change your parameter, again go up, right? Are you getting what I'm trying to say? Make sense? You will again go up, go to the DL paper, DL code, change your code. Now again you'll check your error. If it is correct, you will go out. Otherwise, again go in. Change parameters, again go. So it's an iterative process, and iterations depend on the data, its quality, and the most important thing is differentiation. See, we are doing a very simple problem here, cat and dog, and it's quite easy to differentiate between these things, right? That you create a model that will give differentiate between you for like cats and dogs, right? But if complex are there, then so this VGG model is one of the most complex models because it is catering 1,000 categories, 1,000 general categories, ranging from little birds till like aeroplanes, bikes, motorcycles, human, Homo sapiens, and apple, fruit, everything. So almost like 1,000 categories that are covering, and this model is like one of the best models, one of the best I'm saying, because it's a very lightweight model and it is giving a very greater accuracy. Now there are models where you have 100 layers of models. Those are also giving you accuracy, but those are not optimized models. Those are like very heavy models like ResNet 101. So we have this VGG, and this is best in its nature. Okay, so jumping back to the thing, so we have data generator. We have to create a data generator out of data gen. We have given the folder. You all know how the folder looks like, right? LDIR is equal to, if I show you what is inside data generator small, then this is nothing but the two folders, category wise folders, right? These are
One
category wise
question.
folders. Okay, so let's move back here again. So we have a data generator here already. We will say that please go to this directory data generator small and then flow these images from this directory, right? I'm also telling it that you should have a target size of 150. So whatever the size of the image is, resize that image. Again, listen to me. I'm saying resize the image. Do not crop the image. This is not cropping, right? Say if your image was 1056 cross something, this is not getting cropped. This is resizing the image, right? So you are saying that you want to convert your image into this, then you have to give the batch size at how many images that you want to read, right? Let's say I want to read 32 images per batch. Now you remember we have 400 images for all the classes, for all the two classes. Now I am saying 32 batch size. 32 batch size means that if I divide 400 with 32, it will give me around 12, 12.5, or let's say 13. So this is always sealing. If you remember, this is called sealing, np.sealed. So this will always be a 13 buckets we will have. So our epoch will show a count from 0 to 13, right? Make sense to everyone? Batch size 32, and then what do we have? We have data generator, then we have color mode, it's already RGB, then we have classes is equal to none. We need to keep it none. Then class mode is categorical. Yes, we wanted categorical only. We have batch size of 32, it's by default. Shuffle equal to true. Yes, seed equal to none. We don't want seeding. We save directory. No, we don't want to save. Nothing. We don't want to save. We want to just start the thing. So it says that it found 401 images belonging to two classes, and that was correct. We had only two classes. Right, after we have got our train gen ready, we should use the model dot fit, right? But no, here we will not. Okay, sorry. Is it now visible? Cool. So fit will not work here. We will use fit transform. Model dot fit generator. Sorry, not transform, generator. Model dot fit generator. You have to give it what? A train gen that you have just made. Next, you have a step per epoch. Step per epoch is none by default, but this is what you think, right? Steps per epoch is what? That how many buckets will come here. So you get the idea, right? What was the number that we just calculated? That was 13. I'll tell you again how it came 13. So you have 401 images in total, right? And you are saying that you will have a batch size of 32. Batch size of 32 means that in each bucket you will have 32 images. Then how many buckets will you have? 12.53. Now bucket can be an integer only. So what you will do is you will do np.ceiling. It means you want the upper bound. Upper bound will be what? 13. So you will have 13 things. Or what you can do is, that is the most brilliant thing that all you always do is +1. That gives you the idea, right? So what we are going to do is we can write here that steps per epoch will be, so one epoch is what? When all your images are gone from the model forward and backward once. That is one epoch. Now you have 400 images. You are only taking 32 once at a time. So your model will be taking 13 times each bucket of 32 images, and then it will cover 400. So your steps per epoch will be what? 32. Make sense?
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Then you have epochs. Let's say 10 epochs only right now. I don't have much RAM in this, but okay. And then you can say verbose equal to 1. Verbose equal to 1 means that you want the output to be printed. Yes, we want. You can have 0 or 1 dependingly. And they have 2 also, if I remember. Yes, verbose is equal to 0, 1, 2. 0 is like totally silent. You don't want anything. 1 is with the progress bar, and 2 is with the one line per epoch. Right. Right. How, when you are running a very large model, how do you see the losses and the accuracy of this? Right. Similarly, you can have validation data. If you have validation data, you give your validation data where it is. Right. Validation steps. How many steps do you want? And then you can further give this thing. We don't have much. We will say we will remove this thing. We will run this again, and again. And our model is started, and my CPU has started heating up. I forgot to do one thing here, that you have to take this thing in some output history. Now we will start this. Sorry. See, I told you this number is going to be 13, right? Is everybody getting the idea? So we are saying that we want 10 epochs. That is a different story. But in each epoch, how many times it is going to run? 13 times. 13 times forward, backward, forward, backward, forward, backward, 13 times. And each forward, backward is taking how many images? 32 images. Now you can see your model is giving 54% accuracy. Losses are decreasing 0.69. Oh, 70 increased. 69 decreasing again. Okay, this was a very bad line. The accuracy decreased. Okay, the model is recovering slowly, slowly, slowly. Oh yes, increasing. Just 2 more steps and our modeling will be done. This is how we do. Now let me check one thing, because I think I did something, because this is not what the accuracy I was expecting. The accuracy should be like, okay, so we have a data set also small one. If I give it the big one, let's try it, then it should work better. Okay, let me run this again. Let me restart the kernel only. Epochs are also less, so you might try to increase the epochs also. And I might need to do one more thing. I might need to increase the batch size. Now, can any one of you tell me how is the batch size affecting the model? One is that, okay, it is using the RAM, right? Because 128 images are now going inside the model. But what else it is doing? Now I have changed my batch size from 32 to 128. What will this change? So let's say I give you this example. Let's say that there are two animals that are not known to you, right? I am giving you the images that this one is animal A and this one is animal B, right? Now, if I show you only one image at a time and then I ask you that tell me who this thing is, or another case is when I'm giving you 100 images and then I'm saying 50 are this, 50 are this, and then you see all those, okay, 50 animal A, 50 animal B, and then in which state you will be able to give, when I give you next image, in which state you will be you can give me better answer. Okay, I'll come again. There are two scenarios. There are two unknown animals, right? And now you are the person and I'm asking you that you have to predict which animal it is, right? But before
Okay.
predicting, I will tell you this, that which animal is which animal is which, by showing you a different picture to you. I have two boxes, right? First box may I open, and one case is that I only show you one image of each animal. One image of animal A and one image of animal B. And then I ask you that predict this third image, right? And another case scenario is where I show you 100 images first, 50 of animal A and 50 of animal B. And then I give you some image to tell me that which animal it is. Which case is better? Which case is better to you? The later one, right? Where I show you more examples. This is
Correct.
also what is happening with the model also. Try to understand that, okay, let's say if you are taking a batch size of 32 and a batch size of 128. Now, when the images are going inside, what is actually happening? These are convoluted, then sent to dense, then after dense, they are going to like reducing their dense, and ultimately they are giving some probability, right? Now, based on the probabilities, the model is saying that this is your error. And then based on their error, they are again coming back and then they are doing some differentiation, correct? Now imagine that you are showing your image only, let's say 8 images. Now the model is trying to change the model is trying to change the deviations, your gradients, by seeing only 8 images. And let's say if only cats images are shown to you, then the model can get biased, right? And let's say now in the other case, we are giving more images. Now by seeing more images, it tries to be more generic in nature, right? Make sense? How things are differentiated? How is this thing like only giving 8 images and then across giving 120 images? And then based on those images, is someone, if it is bringing some change in itself, how it is going to change, right?
Yeah, basically accuracy is increased.
Yeah, accuracy will increase, correct. One thing is that accuracy will increase, but I am just worried about one thing, that okay, our accuracy is low. I understand this thing, that is this that should be low because we have like very less data. Okay, so I have some questions now. It says it's always better to have a big batch size. Yes, to make your model generic, I think your model should have a good batch size. But again, batch size is again not in your hand, because let's say you're having a less computational heavy machine. then your model won't take this much of images in one go, right? So you have to decide very wisely how much images can you handle in it, right? So it's a trade-off. You cannot even have a very less number, and then you cannot have a very large number also. Until that, let me review the model again. Trophy SGD. SGD is one of the fastest one uh, to converge. Let's say if we use RMS prop with no delta. Let's see how it gives a number. Definitely, HD pictures are like more wider, sharpen. But again, this is a problem also and a good thing also. Let's say you have a HD image, it will have more information. I agree, but more information will come with a more computational heavy resource, right? So now HD image you have to like resize it to a normal level, right? So HD image will make no sense. But let's say you're not resizing, let's say you're keeping it as constant as it is, then you have to deal with the RAM resources. How easily your RAM is going to get exhausted. So you have to deal with that also. Let's say
Yeah,
we are done.
yes.
No, I don't think SGD is the best converger. It is converging best for us. SGD will converge best, but I want to show you one more thing here is that we have two classes right now, right? We could have done one more thing. We could have asked it here that we have no, not here. Sorry. We could have come here and say that this is only one, and rather than saying that this is cross entropy, we could have said Keras dot losses dot binary cross entropy, right? How I'm showing you that what is the difference between categorical and binomial. So what I'm saying is why I took one only, because now my answer will be in 0 and 1. And why 0 and 1? Because if it's not a cat, it is a dog actually, right? So it's actually so how I've converted two categorical problem into a binary problem. Binary problem is what? 0 or 1, right? Let's say 1 is dog, then 0 will eventually become not dog, and not dog in our case is cat. And this is one thing that you should always understand. Let's say that if your model is trying to predict three things, one is cat, dog, and elephant, let's say, and let's say you give a image of giraffe here, right? You have trained your model on cat, dog, and elephant, and now you're giving it an image of giraffe. What will it predict? 0 0 0. Okay, one answer is 0 0 0, that it will say 0 for each probability, right? So one thing that you should always remember is that the sum of the probability for the three classes will be equal to, at the softmax we always use a softmax in the last layer. And what is the responsibility of softmax? That it will give you the how many probabilities? It will give you the probabilities that much classes that you have. So if you have three classes, it will give you three probabilities, and the sum of all the probabilities will be equal to 1. So 0 0 0 might, I mean, it will not be the answer. The answer will be that the model will say that, see, I know, I know that the answer is not right, but because I'm not trained on this, and the elephant is not matching, it's not matching even to your dog, not cat. But softmax, what it will try to do, even if it is giving very less accuracy for each, it will, based on the percentile, it will give you the probability which will sum up to 1. So Ankit was saying very correct that it might not give high probability for cat and dog, but it might give some probability for elephant and dog also, right? And it might not cross 60 or above for each of any one of the category. So it might be like 30, 20 for cat, 30 for dog, and 30 for elephant. I mean the sum will be 1. It will try to do somewhat like this. Making sense?
Yes.
So always remember, your model will always predict from only what you are trying to tell it, right? And I will like to start with callbacks because I have this sheet on 6th Jan where we did this history thing out here. History thing, we did all this plotting and all. So I think we should go with callbacks. That what are callbacks? Okay, now callbacks is a very important thing, and it's a very uh, thing in. So we were talking about these callbacks, right? What are callbacks and how do they help? Okay, so a callback is actually a function that you can execute after every epoch is run. So let's say that your line is somewhat here, epoch here, and then you come here. Your accuracy, final accuracy is printed, your validation accuracy is printed, and then whatever you want to do, you can do at this stage is called a callback. Again, this will be executed when your second epoch is completed with all the 4 batches. Then again at the third end after this, and similarly. So after each iteration of an epoch, if you want to run something, you get this thing inside your inside your callbacks. Now, how do you get callbacks? Very easy. You just say from keras.callbacks import callback. See, callbacks is nothing but callback is that, let's say that after every epoch, once a epoch is run, and if you want to perform some operation after every epoch, you can call that function inside a callback. That's simple. So there are multiple things that you want to do after every epoch. Let's say you want to store the results, or let's say you're writing your own custom loss, or let's say you are writing your own custom let's say optimizer, right? Or let's say you are decreasing your learning rate based on some particular parameters. So then you can write. I can show you. I wrote this code somewhat long time ago, and this contains a very good callback thing. Let me show you callbacks. Here I'm using model checkpoint and learning rate scheduler, right? So I'm using two things. One is called tensor, one is called model checkpointing, another one is called learning rate scheduler. Now what this model checkpointing is doing, this model checkpointing is saving the weights after every epoch. That will it take the last step accuracy and loss. Let's say the last step accuracy is very large and you want the second last model. So what you can do is you can take the weight of the second last step epoch, right? And then you have the learning rate scheduler. So the question was that, let's say that the accuracy is not actually in the last step, is not good in the last step, it is good in the second last step. So what you can do is you can take the second last step ka weight, right? So model checkpointing will save each and every weight after each epoch. Second thing is what? That is learning rate scheduler. Now sometimes you want to decrease or increase your learning rate based on the prediction accuracy, or let's say I am using this based on the V monitor that I'm using. I can show you that also. So you have to write your own custom function. So here, see, I have written my step decay function. What I'm doing here is that I am decreasing the learning rate based on the number of epochs it has done, right? So what I'm doing is, if the epoch has dropped to 3, so let's say after every 3 epochs, I'm trying to drop my learning rate to 0.5. So for what generally what I think the callback that you're confusing is with the web one, where we use it after a async process, or you use it after a readout of a thing where you want to call back your afterward thing. That is a somewhat different thing that we are turning from here. So if you see the callback documentation, it says the apps. This is a base class. It's a list of keras.callback.callback instances, list of callback to be applied during training. That is it. Simple thing. So what it is it that after every epoch, if you want to run any kind of a function, any kind of a method, then you can specify them here in the callbacks. Then they will be executed and they will be recorded in the tf.event files. Again, after the second epoch is completed, you run the callback. After third, you run the callback. After fourth, you run the callback function. So we were here at this thing that let's say that you define your own custom step decay function. After you have done with the step decay, how do you call it? You make it your loss history, and when you are doing a dot fit, you call your callback here. So we'll do the same thing out here. What we'll do, we have this thing called tensor board. So if you see, I have imported this thing called, this one is not needed. From keras.callbacks import tensor board. So what I've taken is tensor board is, I'll show you what tensor board is, but let's first implement it at what tensor board is. Before you are doing your training, you have to do a tensor board is equal to tensor board. If it is in capital, it's a class ko you have to instantiate. You have, let's say, log dir is equal to, let's say here only, or let's say that you want to make it as a logs. Okay, so what it will do, it will create a folder called logs in my current directory, and then it will store all the information there, right? What it will do, it will store all the information there only. And let's say I don't want to go in the logs folder, I just want to stay in my dot folder only. Stay wherever my Jupyter notebook is, just create the file there only, right? But you can specify wherever you want to go. Now once you have done this, this will start this thing, tensor board, and then while you are in your fit generator, you will call the callbacks. Let it complete callbacks, and then it will be a list. List me, you give your TB, right? And let me increase this to 15 for now, right? And let's start the model.fit again. Now while we are doing this thing, what will happen is, let me show you. If you go in the files, you see here there is this thing that has started building up, tf.event files. After this first epoch, you will see a new file here, last modified. Okay, now you will see it up here after first epoch.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Okay, yes, you can see here, if I do a last modified above, okay, it's not coming, then you have to go down and let me show you. See if you can read this thing called here on the downside. I'm just marking it with the blue marker. This is called events.out.tf event file. So what it is generating is, the TensorFlow is generating its event file and they are stored here. Now how can you open a tensor board? Very simple. Open up your console. You go there in the console, click on the console. Okay, this is Windows, this will take a little bit time. Enter, and you have to just say tensor board. Tensor board is by default installed when you are installing TensorFlow also. So tensor board tensor board hyphen log dir is equal to, or I can show you the help first. Okay, let me run it in a simple environment. Just a second. This is your Intellipaat working directory. We are in notebook 3. We are opening the CMD. So see what I ran, I just simply said tensor board, and this will start the tensor board inside that directory, right? Now once, first thing first, I should show you the help hyphen help, that what are the different parameters that you can give. There is one parameter that is called log dir that you have to definitely give, that where your logs are kept, right? Where your logs are kept inside which directory. Okay, this is taking a small time. So now they have changed it to helpful. Okay, so these are the different flags that you can give. You can give a tag if you're running multiple. You can give port number, which port do you want to run. But the most important one is this hyphen log dir. This one is the one that is the most important that you have to give. There are multiple things that you can do with TensorBoard, but the most important is when you open TensorBoard and where you are. So I'm saying dot means wherever you are present, the log files are present there only. Let's go to our browser again, and in the browser, let's open up our.
Okay guys, a quick info, if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
So here what you can see is the beautiful TensorBoard. It's loading. It has multiple tabs, and if we see, our model is running on the 11th epoch. So you will have all the information till 10th epoch in this thing. So you can see the dashboard is here, and these are the loss and the accuracy function. These are the same numbers that you have here. So you have something that is greater than 7.1.0. And if we go back to our model and if we see what is the accuracy on the first epoch, that is 50.3. Sorry, this is the loss, 71.6. Sorry, it's correct. So it's showing you the accuracy on the top and losses at the below. So your loss was greater than 7.10. If you go on the mouse, if you put it somewhere, it will show you each and everything, right? You can smoothen it up more to see the exact accuracy number. If you're running larger numbers and you want to smoothen it up, then you can smoothen it up with here, right? And this is for loss. Whatever different kind of if you would have validation accuracy or validation load, they would have also been plotted here. These are the two things that you can definitely see here. So you don't have to actually view this this thing here. So what you can do is that you can quickly come up here and you can say, okay, my step number 6 is the best. This is performing the best. I will take its weight, right? Same here also for the 6th step, you had the lowest loss and the highest accuracy. So you'll say, I'll take this one, right? Now the most important thing is visualizing your model. So if you click on this graph button, you will see your model here, how it looks like. This is how your model is actually. So if you can zoom in, you can zoom in and see how these things are. First you had this convolution one, right? Then you had a max pooling, then con, then max pooling, then con, then max pooling. Then you had a flattened layer, then you had a dense layer, then again a dense layer, and then you had a matrix to identify what kind of a matrix what kind of accuracy it is, and then you had the loss here. If you click on this loss here, you will be taken to the loss section. On the right, you can see that this is giving you all the things out here. You can also shift your model here, and then you can see this is how your zoomed in variable is. So if you click on each thing, then you can have this. Let's say I click on this dense layer, then you have this thing on dense subnode 13th node. This is the 13th node. The input is coming from dense 4. That is absolutely right, because dense 4 is there, and then you have dense 5. And then the output is going in dense 6 for the matrix multiplication with 512 variables. And that is absolutely right, because in the first we had 1024, then we had 512. And then the output will be in the form of 7 tensors. Absolutely correct. If you go this thing and if you just do a model.history, it will model.summary, it will be the same, right? These dimensions are the same that you see here. Then you have control dependencies. If you want to have more information on the graph, then you should definitely show this to client. These are like showing here. You can go anytime, you can go there. So why there are like two? Actually, there is only one, but we are showing this as two because it's my mistake. I did this one thing. What I did was I actually ran this twice. I should have restarted the kernel and then I have done. It would have been only one, but I'm running. I am stupid. I should have not done this. That's why it's showing two. Otherwise, it would have been only a one. And here you have all the things. You can click on each and every sub node to see what is happening inside, in and out. It has multiple things. You can even see images inside it. So right now we are not given, but if you would have given, you can see your things out there also. I'm so sorry. You have multiple things in here. You can download this graph also by clicking on this fit to screen, and then you could have download this also. Session, you can see multiple devices also. Let's say I have only one device. You could have multiple devices, and then also you could have taken trace inputs. So you want to see where your inputs are going till now. Let's say if I click on this, it will show me how is my input working for this particular section. Choose legends, whatever you want to have, right? It's a very, very useful thing. You will come to know more about this when you're training, very large layered networks, when you're training good level of networks there. In our relative number means what is the difference between the previous and the past one. So it's like a step function that you're doing. Then you have the step is the exact one that the recording for each epoch, and relative is that you're trying to get the number from the previous one, how it is changing from the previous one. You have this wall one also. Wall is for time, so according to time. So again, I'm saying these are for like very big models that are running for like 5 days, 6 days, so you can convert them into time also, wall time. Then you have like 950 with accuracy was here, 955 with accuracy was here. Then, but the only thing extra that you have to do, two things that extra that you have to do to bring tensor board was that first of all that you have to tell the model that model please after every epoch you have to save this things for me inside this file call through this callbacks ko you have given a list me you have given tv is actually what, it's an instance of tensor board. And tensor board, how did you declare it? You declared it from keras.callbacks.tensor board. Now once you are done with this tensor board, how did you open the tensor board? Tensor board you opened in the command prompt, you went to the folder where you are running this thing, and then you just write tensor board -logdir. Let me write the command here also so that you get the idea. Tensor board tensor board -logdir, and then wherever your dir is actually, so r was dot wherever it was. If you would have been in logs, then you would have given logs, and then you would have changed it here also, right? And then you start. By default the port number is 6006. This is the number where you use, this is the port number. If it is used, it will increment by 7, it will increment by 1, so it will become 6007. You can specify it also while you are starting the tensor board by giving the parameter called hyphen port, right? So I was saying that if you want to run your tensor board on some different port number, then you can give the port number when you are giving this command on the command prompt. So you can specify here like hyphen port is equal to 700, let's say 6009, or let's say 7009. So you can give it here. Tensor board has to do nothing with Jupyter Notebook. Even if you are running it on a blank .py file, or if you're running it PyCharm, you're running it Spider, it doesn't make much. But the only thing that I always push pressurize is that you should do data science in Jupyter Notebook, because the answer is available to you instantly. Some of my friends are like very against it. They use Spider. So it's a personal choice. You might use Spider, you might use what, but you can run Jupyter Tensor board wherever you want. Tensor board in itself is a very separate entity. So if you remember, we ran it through a command prompt. I ran something in the command prompt, and then it gave me this thing here, right? So if I show you the command prompt, see, this is the command prompt. I ran this whole command here, this thing till here, right? Tensor board -logdir, and then it gave me that tensor board 1.8.0 is running at this address at port 6006. Press Ctrl C to quit. I just copied this thing from here, went back to my Chrome, and I just copy pasted this, and I run this. So this has to do nothing with your ID, whichever you want to use.
So, suppose you are a computer vision engineer and a client has approached you with a problem statement in which you have to detect the faces from a set of images that they will be providing, and you have taken up this project, and these are the following steps that you have to follow while building up this project. So, these are the images that they have provided to you. These are some of the images that have taken from their dataset, and here we'll be working on Python with OpenCV. In this project, we will be using the Har cascade classifier for detecting the faces from multiple images. So, firstly, you have to perform the downloading part for the har cascade system. So here I have written download har cascade frontal face default.xml and this raw GitHub code. These are the raw datas for the har cascade. You have to just simply save as, and you can save it as desktop, and you have the har cascade classifier. So now next we will be just importing the CV2 and glob. So now we will be practicing it in the Jupyter notebook. So firstly you have to import the CV2 library and glob. So I want to tell you that glob is the function which returns us the array of those file name which we will write in the next line. Like we just have to perform face detection on those images which have .jpg extension. So for that I will be writing gimage equals to glob dot glob. So here I am calling the object glob and with the function glob, and here inside the function I will be writing the star dot jpg. So it will take up all the images that have extension .jpg. So after that we will detect, after getting the glob images, now we will create cascade classifier so that we can, so as it helps us in getting the face detection. It contains all the features of the images like nose, ears, face, object. These are some of the features of the image. So here we will be writing detect equals to cv2 dot cascade classifier. Then inside the braces we will be writing which classifier. We have downloaded the har cascade frontal face default classifier, so we will be mentioning the same name, har cascade. Okay, har cascade frontal face default.xml. So now after creating the har cascade frontal face default XML file, then what we will do, we will now traverse the glob images so that we can detect the faces. So for traversing we will be creating a for loop for traverse, or you can also write t image for traversing the image, t image in g image, the glob image. Okay, so now it will take one image at a time. Now in the for loop we will read the image, a particular image. So for just reading the image we will write like I have taken image equals to cv2 dot im read, and what is this reading? The t image. Okay, so after reading the particular image from the G image, now we will convert the images. These are the colored images. The image that it has read, it is the colored images. So in this phase detection, we will first have to convert the colored image into the grayscale image. So it is easier for the classifier to handle the image and detect the faces from it. So for converting the image from converting the colored image to grayscale image, we will write gray image. I have written this gray image equals to cv2 dot cvt color color, and in the braces it will have this image that you have to convert it into grayscale. This image comma the we will write cv2 dot color and underscore bgr to gray. Okay, so after converting it into grayscale, now we will detect the faces from the images. So for detecting the faces, I will be writing the face equals to detect. I am calling this object here and with the function detect multi-scale, and it has 3 parameters. So the first one is in which image you want to detect the face. So we will be writing this gray image here, and the next parameter is the scale factor. So we will be more So we have to see the value of the scale factor, as the scale factor is that value which decreases the volume of the whole grayscale image by 5% until the face is detected. So it basically what does, it decreases the value of the image so that it can find the face from the image. So I am writing 1.25. The smaller the value is, the greater will be the accuracy. So I am writing 1.25, and the next parameter is the minimum neighbor. So we don't have to bother this value. Now after that, after detecting the face, now we will be describing the rectangle shape for the face. So for that, create a for loop for. Now in this braces, we will be writing all the dimensions for the rectangle like x, y, w, h, length, breadth, height and width. Okay, so after the parameter, now in what? In face, we are actually we have detected the face, but now we have to define that face with a rectangle shape. So for that, we will be using the dot rectangle function. So here I am writing cv2 dot rectangle. Okay, rectangle. Now in this we have 4 parameters. The first one is the image that you have to detect the face image, this image that we have read it here. Okay, the second parameter is the RGB value. RGB value means the colored value. So here I am writing the x, y, and then the other parameters for the rectangle. We are basically defining the parameters of the rectangle, how it will look on the image. So we will be writing x plus w, y plus h. Okay, so after defining the parameters of the rectangle, now we will be look at the color of the rectangle. So here I am just taking the green color. So this is the code for green color. Okay, 0, 255, 0. Okay, so now after that the last parameter is the thickness of the rectangle. So I am giving 2. So now after defining the rectangle, now we will just show the image. So for displaying the image, cv2 dot imshow, in the parenthesis we will be writing detect. Any message you can write like detect images. Okay, and comma, which image? This image. So image. Okay, so after displaying the images, now we will be defining the wait key function. What does wait key does is we will define some intervals between the images. It's just a time period that what will be the intervals between the images. So cv2 dot wait key, and how many? I am taking 200 milliseconds. Sorry, 2000 milliseconds, and we will be writing cv2 dot destroy all windows. So destroy all windows will closes all the windows based on the wait for key parameter. So here I am writing the 2000 milliseconds, so it will destroy it for that. So here, okay, so I am running this code. So here you can see that all the faces have been detected.
The problem statement. So the problem statement is here. Your client is a large MNC and they have 9 broad verticals across the organization. So one of the problems your client is facing is around identifying the right people for promotion and prepare them in time. So it is only for manager position and below. So currently the process that they are following is, first one, they first identify a set of employees based on recommendations and past performance. Then the selected employees go through the separate training and evaluation program for each vertical. These programs are based on the required skill of each vertical. Then at the end of the program, based on various factors such as training performance, KPI completion, employees gets promotion. So talking about the KPI completion, so only employees with KPIs completed greater than 60% are considered. Now this is the actual problem statement. Now let us look at the scenario that is provided by the company. So the final promotions are only announced after the evaluation, and this leads to delay in transition to their new roles. Hence, the company needs your help in identifying the eligible candidates at a particular checkpoint so that they can expedite the entire promotion cycle and they can speed up the process actually. So the first thing is they have provided multiple attributes around employees' past and current performance along with demographics. Then they have provided multiple attributes around employees' past and current performance. Now the next and the second point is the task that we have is to predict whether a potential promote at checkpoint in the task set will be promoted or not after the evaluation process. Now this is what we have to do, and moving ahead, let's understand the data set and the parameters. So let me go to the training and the testing data set. Now this is our training set and this is our test set. So now let me go to the training set, and this is the employee ID. So we are not much concerned about the employee ID, so it will not actually help us in the prediction. This is the department section, including sales and marketing, operations, then technology, analytics, operations, sales and technology, again technology, then research and development, then there is finance, procurement, and so on. There is also a department called HR, and the next one is region. So this is region 7, region 22, region 19, and there are many regions. So region will actually not help us to predict the outcome of the model that we have to build. Then comes education. So education can be the factor for predicting the promotion. So the list of education that is provided over here is masters and above and bachelors. So also here the empty data is there, which means that there is no data provided over here. So we will deal with the missing values also. And then comes the gender. So the gender is male and female. After that comes the recruitment channel, that is sourcing and other. Then comes the number of trainings. So that is 1, 2, and we'll scroll down. It includes 3, the number of training that are provided to the individuals or the employee. Then the next thing is the age. So this is the age of the employee. Then comes the previous year rating. So this can be one of the most important factor in the promotion. So the previous year rating is 5, 3, 1, 3, and so on. And this position or this, so this is 3-star, 4-star, and this is empty. So it denotes that the employee is not at all having a rating. So it can be because the employee may be a fresher. So let's check out the length of service. So here the length of service is 1. So that is why the previous year rating is not shown over here. So we'll sort out this thing also for making the model more accurate. Then comes KPI metrics, that is key performance indicator. So it denotes and it indicates the metrics for the performance of the employee. So 0 over here denotes that the performance is not at all good for giving them promotion, and 1 indicates that the performance is decent enough to give the promotion. Then comes awards 1. So this is 0, 0, 0, and here it is 1. So award 1 is 1 over here for a particular employee whose ID is 77981. And now average training score. So this is the training score of an employee while pursuing a training for the company. Here it is 85, 73, starting from 49, 60, 50, and so on. So it can be a major factor for predicting the promotion for the employees, that is how well they perform in the training and what is their score in the training. Then comes is promoted. So 0 means that they are not promoted and 1 means that they are promoted. So in this data where the promoted thing is 1, so this is the average training score, and here this shows the KPI metrics, that is also 1. Then the next one is the length of service, that is 6 years, and so on. So these are the parameters and the data set on which we'll be working on for making an AI model to resolve the business problem. Now let me go to the training set. So this is the training set, and it consists of, let me go to this part. Okay, so this also consists of employee ID, then department, region, education, gender, recruitment, number of trainings, age, previous year rating, then comes length of service, KPI metrics, awards won, and then average training score. So these are the parameters over here. So we have divided the data set into train and test set so that we can train the model using the train set, and we can test the model using a separate data set, that is HR_test. Now the reason for using the test and the train data for the model is that we do not want our model to overfit the data. So in future it may get different sets of data and it may face issues in giving accurate results because the model is overfitting the data set that it is having. That is why we are using a separate data for training the model and a separate test data for testing the model. Now we have understood the data, that is trained data and the test data. Now let us move on to the steps that we'll see further. So the next step that we'll be going through is pre-processing and feature engineering. So in this we'll pre-process the data with using the different types of pre-processing. That is, we will manipulate the data, we will remove the null values and the missing values from the data set, and before that we'll use various and we will import various types of packages that are required for the implementation, and we'll see the info of the train and the test data set as well as the description such as the standard deviation, the mean and the average of the values. Then we'll perform feature engineering for the model and for the dataset values. Then we'll build the model using various algorithms that are used to build AI based applications, and we'll apply feature scaling so that all the values comes in the common slot and the prediction becomes more. And finally we'll evaluate the model that is created using various parameters and metrics of model evaluation, and then we'll visualize it using models visualization. So further, let's go to Google Colab for the implementation part. Now this is our Google Colab. So first thing you have to do is just go to this folder option, click on this upload session storage button and upload the training and the testing dataset. So I have already uploaded it, so I'll just show you.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now let's continue with the session.
So I'll scroll down and here is the data, that is train and test data that I'll be using. So whenever you open Google Colab, so the first thing you have to do is you have to load the dataset. Otherwise you cannot work with Google Colab and create algorithms and AI based applications. So also one thing more, if you load the dataset now, so it is for this instance on which you are working. If you will close the tab, then the dataset will be deleted. So again and again you have to load the dataset. Now I have written the code over here, the entire code. So I'll implement and I'll explain every code, what it is actually built for and how it is working. So first I'll import warnings and use this warnings.filter warnings ignore. So this is used to ignore the warnings that are displayed by the interface or by the Python library while implementing the program. So I'll run this and now you can see it has been successfully executed. Now the next thing is the scientific and data manipulation libraries. So I have imported pandas, I have imported numpy, then import math, gc, os and the sklearn package. So we use pandas basically for data analysis and data manipulation, and it provides various features for the analysis of data. Then comes NumPy, so we can work with multi-dimensional data and matrix arrays using the NumPy library. Then comes importing of maths that help us to implement various mathematical operations. After that, import GC for the garbage collection, and then importing OS so that the packages and libraries are imported so that the application which we are building using the various modules and libraries of Python, so it gets added according to the operating system. Then importing scikit-learn, that is sklearn. So scikit-learn basically help us to implement classification, regression, dimensionality reduction, and many other machine learning algorithms we can implement using the sklearn or scikit-learn library. So I'll run this, and now the installation of the scikit-learn is done. So I have already done. It may take a while for you to get this. So I'll run this pip install scikit-learn to install the scikit-learn library. So it will take a while and it will get loaded. So these are the basic steps that you need to implement before data pre-processing. So these libraries and packages are the first thing that you have to load and install or download for working further with the data pre-processing task or creating algorithms. Then comes more libraries. So in sklearn we have pre-processing, model selection, tree, ensemble, and metrics. So from sklearn library we import the packages for pre-processing and model selection, tree, ensemble, and metrics. So why we do that? Because we have to use label encoder, one hot encoder. We want to use min max scaler, normalizer, robust scaler. Then comes max absolute scaler, and then we used model selection thing for using k-fold, stratified k-fold, train test split, then cross validation score. After that comes the tree package, for which we have to use decision tree classifier, random forest classifier, and then voting classifier using the ensemble package of sklearn library. Then comes the metrics package of the scikit-learn library, using which we'll evaluate, or first we'll load F1 score, then confusion matrix and classification reports that help us to implement the functions for F1 score, calculating confusion matrix for accuracy, and the classification report. So we'll use this from sklearn.preprocessing, import standard scaler, min max scaler, normalizer, robust scaler, and for loading all these modules from the library we'll use these commands. So let me run this. So it shows that it is successfully executed. So before moving ahead, let me explain you the standard scaler, min max scaler, so all these, why we are actually using it. So starting with standard scaler, it actually removes the mean and scales each feature or variable to unit variance, and this operation is performed feature wise in an independent way. So standard scaler can be influenced by outliers, so the values lying beyond the common slot of area where the actual values are lying, so it can be influenced by the outliers, and it involves the estimation of the empirical mean and the standard deviation of each feature. So it scales it, so it helps the model to predict in a better way. Then comes min max scaler. So min max scaler rescales the data set such that all the feature values are in the same range from 0 to 1. So actually there are too many values and it can have different values from 1 to any of the value. So we need to rescale the value in a common slot such that we can create a plot out of it and gets a better visualization. So min max scaler helps in this way. After that comes the normalizer. So the normalizer rescales the vector for each samples to have unit norm independently of the distribution of the samples. Now then comes the robust scaler. So unlike all the other scalars, the centering and scaling statistics of this scalar are based on percentiles, and therefore they are not influenced by a few number of very large marginal outliers. then consequently the resulting range of the transformed feature values is larger than for the previous scalars. And one of the most important thing to note is that they are approximately similar, and for both features and for most of the transformed values, they actually lie in a range of -2 to 3. Now coming to max ABS scalar, so it differs from other scalars and such that the absolute values that are mapped, they are in the range of 0 to 1. So they are the absolute values, and on the positive data the scalar behaves similar to min max scalar, and therefore it can suffer from the presence of large outliers. Then comes the voting classifier. So the logic behind the voting classifier is creating a separate dedicated model and finding the accuracy for each one of them. So we actually create a single model that is trained by the other models and predicts the output based on their combined majority of voting for each output class. So that is the logic behind the voting classifier, and we'll use this voting classifier for our project. So I hope the importing of the libraries and packages is clear. Now we'll move ahead and we'll import class and we'll install the cat boost. So I'll click on it. So you have to use this command pip3 install cat boost, as we'll be using the boosting algorithms such as xgboost, lightgbm and cat boost for preparing our model. So it will just take a while to load, and I have already loaded this and I have downloaded the packages related to cat boost. That is why it is showing requirement already satisfied. Then I'll import the xgboost and use an attribute that is xgb for it. Then lightgbm and then cat boost. So I'll click on it and it is successfully executed. So why do we actually use XGBoost, LightGBM and CatBoost? So XGBoost is a scalable and accurate implementation of gradient boosting machines, and it has proven to push the limits of computing power for boosted trees that are used for implementing the algorithms for the sole purpose of checking the model's performance and improving the model's performance and the computational speed. So that is why we use XGBoost. So also XGBoost is used for supervised learning problems where we use the training data to predict a target variable. So that is why XGBoost is used for building the AI models. Then coming to LightGBM, that is a gradient boosting framework that uses tree-based algorithms, and it is designed to be distributed and efficient with the following advantages, that is faster training speed and higher efficiency. Also, it has support of parallel and GPU learning capable of handling large-scale data. So that is why LightGBM is used as a classifier. Then coming to cat boost algorithm, so it is an algorithm for gradient boosting on decision trees. So it is basically used for search, recommendation systems, personal assistant, self-driving cars, weather prediction, and many other search tasks. So one of the major benefit of using cat boost is it can handle missing values internally. Also, by default, cat boost uses one hot encoding for categorical features with a small amount of different values in most of the modes that we use. And so coming to one hot encoding, we use it for all the categorical features with a number of different values less than or equal to the given parameter value in a specific range. So we'll use all these algorithms for our AI project for building our model, and I hope you are clear with the algorithms that we are using. So let me run this and you can see it is being successfully executed. Now I'll run this. That is, from XGBoost we are importing XGBoost classifier. So it is also successfully loaded. Now comes the data visualization libraries. So we will use matplotlib, seaborn and plotly package for the data visualization. So I'll run this. Okay. Now comes the randomness of the data that is being selected. So we'll use np.random.seed. So it is actually used to save the state of a random function so that it can generate same random numbers on multiple execution of the code on the same machine, or it can be on different machine. So the seed value is the previous value number generated by the generator. So that is why we'll use this np.random.seed. After that, we have to set the location path from where we'll use the dataset. So we have already loaded the dataset, and you have to do it again and again for the Google Colab if you are using Google Colab. So now I have already imported OS. So it is just written over here from Google Colab import files, then train pd.read csv is used to load the dataset. I'll run this and let us see. Okay, so it is being successfully executed. Now we'll display the dataset of train and test. So we use this display function to display the values. So I'll run this and it will display the training values and the testing values. So let me scroll down. So the first one is training value and the second one is the test values. The second one are the test values. So this shows the index. Now employee ID, department, region, education, gender, recruitment channel, then number of trainings, age, previous year training, length of service, KPI metrics that is greater than 80, and awards 1, average training score, and is promoted. So as we have already discussed the training dataset, and the KPI metrics should be greater than 80% to get the promotion. So here it is. Now let us check out the test dataset. So again, these are the index, employee ID, department, region, education, and it will not have the is promoted column because this is the testing dataset. That is, these are the independent variables using which we have to predict whether the person has to be promoted or not. That is the variable is promoted. Now further, let me go to the exploratory data analysis that we have to perform. So for this, first we have to look into the information of the training set. So for this, we'll use train.info to display the information of the train data. So let me implement this. And now we get the training data. Along with it includes the non-null count and the data type. Also the count of the types of data type, that is float 64 is 1 time for the corresponding column, and it is previous year rating, and integer is 8 times and the object is 5 times. Also it shows the memory usage, that is over here it is 5.9 plus MB. So this shows the information related to train set, and then let me display the information related to the test data. So here it shows that there are 23,490 entries starting from 0 to 23489, and data columns total there are 13 columns, and non-null count along with data type and the count of data type over here, and the memory usage is 2.3 plus MB. So this is the information regarding the test and the training data. Then comes displaying the descriptive statistics of train data. So just talking about exploratory data analysis, so it is a part of the data pre-processing where we actually gather the information related to the data. So we check the info, we check the description of the data such as the average, the maximum and the minimum values, along with the mean or the standard deviation, the type of data, memory usage, and the non-null count, and many other factors. So we look into that in this data pre-processing step, or you can say the EDA, that is exploratory data analysis. So let me run this train.describe. So it shows more information related to the training dataset. So it shows the count, it shows the mean for all of these columns, then comes the minimum value, maximum value, and the interquartile range. Now let me check the description about the test data. So I'll run this, that is test.describe. Again, it shows the count, the mean, the standard deviation, minimum and the maximum value, and the IQR, that is interquartile range. So this shows us the description of the train and the test data.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
Now further we'll display the number of unique values and the actual values. So we have to first define a function, def for defining the function, that is display unique, and it will take the argument as data. So here we have passed the argument of train data. So display unique, we have called the function. Now what does this function do? So for column in data dot column, that access the columns present in the data set. So we have to print the number of unique values in the column, that is the column corresponding to the trained data set that we are accessing to. Then the columns are then using the str function data, then column dot n unique. It will fetch the unique values from the data set or from the column. Then the actual unique values in column. So again, now further to get the actual values, so here we use again the str function and then the sort values function that sorts the data in the ascending order, because the ascending is set true over here. So for getting the actual values, we have to use this sort underscore values function, and this na underscore position takes two strings, input last or first, to set the position of null values, and accessing this unique function gives the unique values from the data set. So it shows the number of unique values simply, and using the sort values function we can access the actual values in the column. So let me execute this, and now here we get the output. So number of unique values in employee ID are 54,808. So starting from 1 and it goes till this index. So these are the actual values, and then comes the number of values or unique values in department column, that are 9. But the actual unique values in the department column are analytics, finance, HR, legal, operation, procurement, R&D, sales and marketing, and technology. So the actual values are shown over here. So these are the actual values. So this is how we actually access the actual values using the sort underscore values, and we can keep descending also over here, but we have kept ascending order. So these are the actual and the unique values for all of the columns of the train data set. So we can check it for test, but we'll leave it for now. And now we'll move on to displaying how each feature is related to the target variable in a flow. So for this we will use a plot using the parallel categories diagram. So the parallel categories diagram actually it is also known as parallel sets, and it is a diagram, or you can say a visualization of multi-dimensional categorical data sets, and each variable in the data set is represented by the column of rectangles, where each rectangle corresponds to discrete value taken by that variable. So here we pass in the columns. So the columns are department, education, gender, previous year rating, KPI metrics, then recruitment channel, and is promoted, and color is based on the is promoted column. Then we use the continuous color scale. So using this sequential dot agrenil, so we plot the figure using multiple colors. So this figure dot show help us to show the figure. Now let me implement this and let us have a glance at the figure that we get. So it will just take a while to load. Till then you can just wait. Okay, this is the figure that we had. So this figure is very descriptive and it shows you the data. So let me show you how you can actually read this figure and how actually you can understand the various dependent or independent variables from this figure. So there are columns named department, then education, gender, previous year rating, KPI metrics, recruitment channel, is promoted. So is promoted is shown over here. So it consists of the value as 0 to 1. So hence its scale is from 0 to 1. And then comes the individual categories of the columns. So in department, there are multiple departments such as sales and marketing, operations. So this section is the operations one. So you can see when I have kept my pointer over here, so it shows the relation, actually the data relation from other columns such as education, gender, previous year rating, KPI metrics, recruitment channel, and is promoted. So the count it shows is 11,348. That is, there are 11,348 employees for the operations department. When I kept my mouse pointer for sales and marketing, it shows the count as 16,840. And then comes the count of this sales and marketing, and then technology. So the count is, let me click on this. So the count is, you can see over here. So this shows the count as 7138. Then comes analytics, that is 5352, R&D, which is the least, and then procurement, finance, HR, and legal. Now coming to education. So when I kept the pointer over here, so it shows the count for the masters and above degree as 14,925. So here the category is written over here. Then when I came to this bachelor's, it shows the count as 36,669. Then coming to below secondary, it is 2,409. And then the final one is the below secondary one, and this, so this last one is the below secondary one, that is 805. Now coming to gender, then the count is 16,312, and the count for the male employees is 38,496. Now previous year rating starting from 5. So the employee who are having the rating as 5 are 11,741. Then 3, rating of 3 is 18,618 employees are having a rating of 3. Then 1, it is 6,223. Then rating of 4 is of 9,877 employees. After that, the rating of 2 is 4,225. Now the KPI metrics greater than 80. So for 1, that is the metric, KPI metrics is greater than 80, the count is 19,291. And for the employees for whom the KPI metric is less than 80% are 35,517. Now again, the recruitment channel is sourcing, other, and referred. So for sourcing, it is, the count is 23,220. Then for others, the count is 30,446. Then for the referred one, it is 1142, that is the least. Now I'll come to the is underscore promoted column. So the count it gives is 50,140 people are not promoted, that is the value is 0. And the promoted people's count is 4,668. So you can see over here the structure of the figure. Now for the next one, we will have a heat map. So we will display the correlation between the features through heat map, and lighter color higher correlation, and if close to 1. So lighter color shows the high correlation. So for this we use sns.heatmap, and as we are making the heat map for the train dataset, so we'll use this train.corr for correlation, and this annotation or anot is true. So I'll run this and we'll get the heat map. So here are the employee ID. So these are the columns: employee ID, number of training, age, previous year rating, length of service, KPI metrics greater than 80%, awards won, and then average training score is promoted. And this scale shows the is promoted thing starting from 0 and 1. So the values are only 0 and 1. Now the x-axis of the figure, so it is not actually x-axis, but it is the other side of this figure. So it has again employee ID, number of trainings, age, and previous year rating, length of service, KPI metrics, then awards won, and average training score, and is promoted. So a heat map is a two-dimensional graphical representation of data where the individual values that are contained in a matrix are represented as colors. And the Seaborn library, we have imported it for this purpose, and the Seaborn Python package allows the creation of annotated heat maps, and which can be tweaked using the matplotlib tool as per the creator's requirement.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now let's continue with the session.
So we are creating this for the correlation, finding the correlation. So this color shows us the correlation between all these parameters that we are evaluating. So this is the heat map that shows the people who are promoted, or not the people who are promoted, but the correlation between these columns. Now let me go to the next part, which is finding the duplicate rows from the trained data if it is present. So we have to check for duplicate rows to remove them. So we will create a method that is remove duplicates that will have an argument of data. So in this we'll print before moving or before removing duplicates the number of rows, comma data.shape. We'll give the argument as data.shape. Then we have to implement the logic or the action, that is data.drop duplicates, to drop the duplicates, keep equal to first in place equal to true, and then again we have to print after removing duplicates the number of rows. So again the argument is data.shape. So actually this data.shape returns the data in the form of array, and then we'll return the check duplicates. And now I'll just implement this, run this, and now I'll call the remove underscore duplicate and give the data or the argument as train. And now I'll click on this. Further, after the successful execution of the code, we'll get this. Before removing duplicates, the number of rows are 54,808, and after removing the duplicates, the number of rows are again 54,808. Now it will return the checked duplicates. After that, we'll handle the missing values. So remember that still we are in the data pre-processing or the manipulation part. So we have to deal with the missing values. So missing values are present in the previous year rating and education columns in both train and the test data. So here I have just written for the reference why is data missing in column previous year rating. So data was not entered because those employees were fresher. So as I have already told you when we were discussing and when I explained you about the data set, so data was not entered because those employees were freshers, that is length of service is 1 is equal to 1, and they did not have the previous year rating. So the no data would have been there in the data source itself for these employees. So logically we are imputing with 0 as freshers with 1 year experience and may not have previous year rating at all. So filling the missing values in train and test data. So what we'll do is we'll use this train dataset and the test dataset, and in this bracket we'll give the column name, that is previous year rating. And what we'll do is, again, to access the previous year rating, so we are actually accessing the previous year rating, and then we'll use this dot fill na with 0, so it will fill those values with the 0. So the next thing is, we'll access the column of fresher for the train dataset, and then we'll use this previous year rating and apply function, and then we'll use this lambda. So here we'll put the condition, so if x is equal to 0, then the employee will be a fresher, otherwise the employee is an experienced professional. After that, we'll display the fresher column with the value counts, and again the previous year rating, length of service, and this fresher tag that we have used using the condition that is applied over here for marking the tag as a fresher. Again, we'll use this display function to display this previous year rating, length of service, then fresher for the first 25 values, and for this we'll use this head function. Now I'll run this, and here we get the output. So these are the columns, and they are replaced by the values as 0, 1, fresher. So this is the fresher column, and this is the fresher tag that we have displayed using the display function and putting the condition over here. So the experienced professionals are 50,684 and the freshers are 4,124, and the data type is integer again. So we have used the previous year rating, length of service, and the fresher column for displaying the data. Now again, we have displayed the data for previous year rating, length of service, and this tag I should have changed it to experienced. So okay, so I have put a condition over here, so let me go to that one. Okay, so here if x is equal to 0, then it will be a fresher, otherwise experienced. So that is why it is showing data over here for experienced as well as for fresher, and the length of service, previous year rating. So this is actually about the removal of the missing values and sorting out the missing values that were there in the dataset. So we actually saw some empty blocks in the dataset. So we filled in with the values as 0. So for that we used fill na and filled with 0. So this is done. Now next what we'll do is we'll display the missing values in the train and test data. So to display that, we'll use this display function, and this will give the text as train corresponding to the missing values in train set. So we'll use this train.isNull.sum. So isNull for counting the for getting the null values, and sum function to sum all those, and to display it we'll use this display function. Same for the test. So I'll run this. So for training set, so this is employee ID, department, region, education, gender, recruitment channel. So for all other columns, the null values, so there are no null values, there are 0 null values, but for education there are 2409 null values present. And for the test column, the employee ID, department, region, and all other columns are not having any null values. The count is, or the sum of those null values is 0. The count is 0. And for the education, it is 1034. So as the test dataset is less than the training dataset, so it is showing less. So we have counted the null values over here. So now after executing this, let us handle the null values. So for this we'll use ffill, bfill. So I have written this for reference, so you can read this. So talking about ffill, so this is forward fill, that fills the missing values with previous row value. And if previous row value is null, then it moves to the next element without filling. That is why we use ffill and bfill both. So what does bfill do is, so it is backward fill that fills the missing values with next row value, and if the next row value is null, so it moves to the next element without filling. So what actually happens is, for example, for just explaining you, if the system goes to 4th and 5th row and the 4th one is empty, then it iterates to the 5th row and fills the data of the 5th row into the 4th row. So this is actually the backward fill. And in forward fill, what happens is it fills the missing value with the previous row value. For example, if 4th row is having a data and 5th row is empty, the data is not present, then the value present in the 4th row will be added for the 5th row data. So we use both forward fill and the backward fill to fill in the data. Also, filling with mode and new category called others are most commonly used technique which didn't work here, so we are not using that. So we can assume that while collecting data relevant members, data were collected close to one another, so it is not too fluctuating, that means. So talking about the training, now we'll fill in the values for the education column. So here we have used this train, inside it we have given the argument inside the square brackets as education. Then we'll use this dot ffill for forward fill, and we give the argument in this way, that is access is equal to 0 for all of the train and the test data. And finally we display the data and we try to actually calculate the sum of all the null values that are present in the training data set and the test data set using the isNull and sum function. So I'll run this and let us see the output. So it will just take a while to load. So here we get the output for the train and the test data set. So employee ID, department, region, education, gender. So you can see over here, so we have implemented it on the education column by using the forward fill and backward fill. So the count has come down to 0 for the education column. Now after this we'll work on feature engineering. So based on the age distribution, most of the employees are in the range 20 to 40 who will be also waiting for a promotion, and so we have created 2 bins, 20 to 29, 29 to 39, and remaining 1 bin for 39 to 49. So we have used dist plot, so plot a univariate distribution for the observations. So I have written this for the reference so that you can refer it in future if you have any doubt and all. So you can see the description of this. Okay, so moving ahead, we'll use this sns.distplot and we'll give the train as the data and this age column, and after that we'll use this train, and inside this square brackets we'll give the age. We'll use this pd.cut and give in the argument as train and the age column. So the train data set along with the age column, or for the age column, and bins will be 20, 29, 39, 49, and labels that would be given to these bins are 20, 30, 40. Same for the test one. For age column, pd.cut, bins will be 20, 29, 39, 49, and the labels will be given as 20, 30, and 40. So let me run this, and now we'll get the plot like this. So feature engineering is nothing but extracting the feature or the properties from the dataset and the expertise and the knowledge that we have. So this is the plot that we have after plotting the age column. Now after this we'll split the train data into predictors and the target, that is independent and dependent variables. So this is the step that we have to do before creating our model. So here we'll split train into x underscore train, that is features, and y underscore train, that is target. So in X train, we'll select all of the columns, that is department, region, education, gender, recruitment channel, number of trainings, age, previous year rating, length of service, KPIs, metric that is greater than 80%, awards won, and average training score. And in this Y train, we'll select the is promoted column, that is the separate column that we have to predict using the test dataset. So we will add this in the Y train section, and then we'll convert the Y train into a frame using 2_frame, because it is a single parameter and the output is expected to be in data frame. So we'll use this to convert it to a frame. Now comes the X test. So we'll use this X_test, and inside it we'll give the argument or the number of columns, that is department, region, education, gender, till average training score. So now we have successfully splitted the train and the test data. So after running it, so it has no error, that is it has been successfully executed. Now as we have splitted our data set into train and test, now we'll perform the data encoding using the label encoding and the one-hot encoding. So what does it actually mean to perform these operations? So actually label encoding refers to the converting of the labels into numeric form, so that to convert it into the machine readable form, and the machine learning algorithms or the AI algorithms that we are using for building our AI based application can then decide in a better way on how those labels must be operated. And using one hot encoding allows the representation of categorical data to be more expressive, and many or the various machine learning algorithms cannot work with categorical data directly. So the categories must be converted into numbers. So this is required for both input and output variables that are categorical. So we use one hot encoding for that. So we'll define a function that is data encoding, and given the parameters or the arguments, that is encoding strategy, encoding data, and encoding columns. So let me go down and check where I have called this. Okay, encoding data encoding. So I'll check where I have called this function. So this is data encoding I've called over here, then encoding strategy, and then the data, then the columns that we have to give. Now I'll go back over here. Now what does this function do? So if encoding strategy is label encoding, then we have to print if label encoding, and the encoder we have to put in the label encoder because we are using label encoder. And then we will put a for loop over here. So for column in the encoding columns, we have to print column, then encoding data, and in this encoding data the column will be inserted, and then this function has to be executed. So encoder.fit transform, and then the argument must be given. So tuple encoding data, again we'll use the column as the argument. After that, if this is not true, then we put in elif condition where encoding strategy is equal to one hot encoding. So if this is the scenario, then we have to print elif one hot encoding, and then encoding data we'll use pd.get dummies for encoding data. So this pd is the instance of the pandas library, and this get dummies will give us the categorical values, the dummy categorical values. And after that comes the dtype list that we have to define for float 64, float 32, int 64, int 32 for the data type. So this is the data types list. Then encoding data as type we'll use, and then data types list, and then we'll access the data types. So after implementing if elif, these two lines of code will be implemented which shows the data type, and then return encoding data. So using these condition we'll implement the data encoding technique. So here for description I have added this quote and many points related to it. So let me read it for you. So applied one hot encoding, it will be applied to object categorical columns only. And it's most common to one hot encode these objects columns since they can't be plugged directly into most models. Then Pandas offers a convenient function called getDummies to get one hot encodings. So using this getDummies, we get a dummy variable or a dummy value for the categorical or for the encoded values. So get this using getDummies, and many machine learning algorithms cannot operate on labeled data directly. Then they require all the input variables and output variables to be numeric. This means that categorical data must be converted to a numerical form, and a one hot encoding can be applied to the integer representation. Finally, this is where the integer encoded variable is removed and a new binary variable is added for each unique integer value. So you can go through this description for the reference. So I'll run this. So it has been successfully executed and you will get the result in the next code when we'll implement it. So just for reference or example, I have added the data encoding for this color, that is red, blue, green, red, blue, green. And I have created this df as the data frame, and then pd.data frame. I have given the data over here columns as color. Then I'll print before one hot encoding and call the function as display df, and then I'll print after one hot encoding and display pd.getDummies. So for the first one, so we get the result as before one hot encoding, it is displaying the data frame, and in the second one we get the result after one hot encoding. So I'll run this in one go. So let me explain this one also. So encoding columns, encoding strategy. So I'll go in this code. So we have created a function data encoding, and the parameters are encoding strategy, encoding data, encoding columns. So over here are encoding columns, encoding strategy. So encoding strategy is label encoding, one hot encoding, and the encoding columns are region, age, department, education, gender and recruitment channel that we have to encode. So while implementing this, we have to just give in the index. So here I have called the data encoding function that we have defined earlier. So xtrain encode, xtest encode, and we have called data encoding and data encoding strategy. So index is 1 and the data is xtrain and encoding columns. So it will take the entire column, so all of the columns, and then the second one is encoding strategy xtest on xtest and encoding columns, so it will take all the columns. Then for displaying the encoded train and test features, we'll use the display function and we'll display the first few values using the head function. So xtrain encode, xtest encode. So let me run this, and the first one gives the color data frame, that is red, blue, green, red, blue, blue. So these are encoded in 0, 1, 2, 3, 4, 5. So we have performed one hot encoding, and after performing one hot encoding we get the following results, that is color blue, color green, color red. So these three are the colors, red, blue, green, and these are the indexes, and the encoding that is done is, so this is the data frame. So we have converted it into a data frame, that is why it is showing a data frame over here. So color blue, color green, color red. So this is the these are the encoded values for it. Now let me go up and let me check. So this was the color part, and then we defined the encoding strategy. Then we have called data encoding 2 times for train and test, and it is showing one hot encoding, one hot encoding. So it has performed one hot encoding. So why it has performed? Because the index that we have given over here is 1. So here it is 0, label encoding is 0, having an index of 0, and one hot encoding is at the index position 1. So one hot encoding will be performed. So for performing one hot encoding, first it will print LF one hot encoding that shows that it is performing this type of encoding, and then it has performed the one hot encoding using the pd.getDummies. So it is displayed over here. So these are the result for the encoded rows, the columns that are over here. So you can check it out, the encoded values. So we have encoded it for region, and then it shows various region and the values, then for gender, recruitment channel, and so on. After that, after the encoding has been performed, so our data is encoded, and now we have to perform scaling. So we have already discussed about the scaling types, that is robust scaler, standard scaler, min-max scaler, and max ABS scaler. So I have told you about these type of scalars. So we will directly create a function using this data underscore scaling, and we'll give the argument name as scaling strategy, scaling data, scaling columns, and we'll give in the condition as if scaling strategy is robust scaler, then the scaling data will be, and inside this square brackets we'll give the scaling columns that we need to scale, and then we'll use the robust scaler dot fit transform to scale the values using the robust scaler, and then the scaling data which we have used and we have passed in the argument, and the scaling columns that we need to scale. Same with the standard scaler. So we'll give in the condition as LF. So scaling strategy, if scaling strategy is equal to standard scaler, then we have to use this standard scaler dot fit transform, and again the scaling data along with the scaling columns, or you can say the corresponding scaling columns that we have to put in over here. After that, again LF scaling strategy is equal to min-max scaler. Now same with the min-max scaler and max ABS scaler. So scaling data, then scaling columns, then again using the fit underscore transform method and given in the parameter as scaling data with the corresponding scaling columns that we need to scale. And final else condition consists of the robust scaler. So if any other scaling sent by mistake, it still performs the robust scaler. So we'll use the same line of code that we used for robust scaler, that is scaling data, corresponding columns, and then robust scaler function dot fit underscore transform, and finally we'll return the scaling data. So I'll run this and let's check. Okay, so it has been successfully executed. Now the next one is where we will call the data scaling function or the method. So this is the data scaling method that we have created over here. So this is the description that I have given for reference. So let me read for you. So robust scaler is better in handling outliers. So standardization of a dataset is a common requirement for many machine learning estimators, and typically this is done by removing the mean and the scaling to unit variance, and the outliers can often influence the sample mean variance in a negative way. So in such cases, robust scaler, which uses the median and the interquartile range, often give better results. So here we have defined the scaling strategy. So that is robust scaler, standard scaler, min-max scaler, and max ABS scaler. Now we'll use this x train scale and x test scale as the variable or the instance, and we'll store the values after calling this method, that is data scaling. We'll pass the argument as scaling strategy, that will be 0 in the first one and 0 in the second one. So 0 indicates that it is calling the robust scaler. So we have created the scaling strategy and we can call any one of this. So we have called the robust scaler. Then here we have given the x train encode and then X train encode columns. So what it actually shows is we are scaling the encoded values of train and the test dataset that we have encoded in the previous steps. Okay, then we'll display this X train scaled value and first few values of it for the train and for the test. So it should be test over here. Now let me run this and let us see what we get as the output. So this is the number of training previous year, length of service, KPI, metrics, award won, average training, department. So now we have successfully scaled the values using the robust scaler. So what actually is robust scaler doing over here? So you already know. So it is handling the outliers and it is making the model more accurate and helping us to create such a model to give more precise results. So this is done. Now comes the most important step, that is creating baseline ML model for binary classification problem. So we will use some machine learning algorithms, and you can also say that AI algorithms. So we have already looked around it earlier, that is XGB classifier, then cat boost, light GBM. So here we will create a dictionary, that is key value pairs for ML model name, and then ML model functions with hyperparameters. So these are the hyperparameters. So we'll given the name as classifier, and at the 0th index we'll give the XGBoost. First will be cat boost, second will be light GBM. So using this XGB classifier, we'll define the hyperparameters, that is learning rate, N estimators, max depth, subsample, verbosity, scale, position weight, updater, base score. So the learning rate over here is 0.1. The number of estimators are 494. Maximum depth is 5. Subsample is 0.7, that is 70%. Then verbosity is 0. So what actually verbosity is? So verbosity in keyword it arguments, and it usually means that showing more wordy information for the task. So actually giving the more description. Then the scale position weight, that is 2.5. Updater is grow hist maker, then base score is 0.2. So we'll see the plot which will be plotted. Then it will be same for the cat boost classifier, learning rate, number of estimators, subsample, max depth. Then for light GBM, the importance type come in for extra. Then verbosity is -1. So you can see over here the verbosity is -1. Here it is 1 or 0. Sorry. So here it is 0. Here it is 1. So the more is the verbosity, the more wordy or the descriptive is the model, or you can see it is more adaptive and it shows the more information. So here it is -1, so it is low. Then maximum number of bin is 60, number of leaves 300, boosting type is Dart, learning rate is 0.15, number of estimators are again 494, max depth and other things are same as the cat boost and XGBoost.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now let's continue with the session.
Now after creating a dictionary, after creating baseline ML model for the binary classification, we'll print. So we have to use this list, then classifiers.keys and classifiers.values for it. So after implementing it, let us see what we get as the result. So XGBoost, cat boost, light GBM, and this is what we get. Now our model is created and there are so many parameters to evaluate it. So pace score, booster, column sample by level, and so many others. But we need to improve our model, as no model is perfect in AI or machine learning. So what we'll do is we have to improve the machine learning or the AI model. So as we have used this machine learning algorithms, so it is same for AI also. So I have written over here the ML model. So to improve the ML model with voting classifier, with model evaluation metric, we'll use this F1 and predict target for S promoted. So we'll evaluate the F1 score. So actually what voting classifier is, we have already discussed in the previous section while importing the libraries, modules and packages for the voting classifier. So we'll use the instance or the variable as voting model, and then we'll use the keyword that is reserved by the library or the package, that is voting classifier, and the estimators will given as the xg boost, and then the second argument will be then list classifiers dot value to fetch the values, and for 0th index is the 1 for xg boost, and the 1 or the first index is for cat boost, then light gbm. Then we have given over here as soft voting, and the weights are given over here 5, 5.2, 5, 5 and 5.2. So actually in soft voting, the output class is the prediction based on the average of the probability given to that class. And you can consider an example. Suppose you are given with some input for the 3 models and the prediction probability for class 1 and class 2. So if the probabilities are 0.1, 0.2, 0.3, and for the next one it is 0.2, 0.3, 0.4. So obviously the average of the second class is greater. So the winner is the second one. So this is the soft voting that we call in machine learning. So it is given over here. So then we'll use this voting model that we have created and use this fit method, and inside it we'll give the parameters as xtrain scale for the scaled values that we have created in the data engineering process, and we'll give in the y train for training the model. Then we'll evaluate the predictions of the voting using the voting model that we have just now created dot predict probability, and we'll give the x test scale for checking the performance of the model on the basis of test dataset. So we'll take the entire test dataset. So let me run this, and it will just take a while to get executed. So now get the output. So you can see over here, so the learning rate and the total time, remaining time. So you can see it is still executed. Now again it will take time, so let me tell you the next part that we'll implement. So next we'll work on the result, we'll see the result and try to improve the F1 score. So for this it is completely executed. We see the values. So it took a total of 10.4 seconds to predict the outcome or to learn the features of it. Then the next part that I was talking about is the result and the improving of F1 score. So for this we have to round off the probability results, and for this we'll simply use an instance as prediction, and we'll give in the round function, and before it we'll use the integer that converts it to the integer, and then we'll have a for loop. So for value in predictions of voting that we have just now implemented for the voting model or the voting classifier, so predictions of voting will be counted over here, and then we'll create a data frame table for this result, and we'll store it in the result promoted section. So we'll use this pd.data frame and we'll give in the employee ID and is promoted, and it will have the predictions and the test set of the employee ID. Then this thing you need not to take care of. These are again the classifiers, and then you have to print list classifiers keys over here. So this will be same as previously we have used the classifiers over here. So this is the same thing. Now let me implement it and let us see the results. So list of classifiers, so XGBoost, CatBoost and Light GBM. Now next we'll print result promoted. So I'll type in print, then result, and now I'll run this, and you can see employee ID and is promoted. So these are all the IDs of the employees who are being promoted. So here you can see that the ID number 5973, so employee corresponding to this ID has been promoted. So this is how we implement it and get the result using the round of probability. Now next we have used the classifiers, that is classifier 1, classifier 2, classifier 3 for XGBoost, then Light GBM and CatBoost. So we are fetching the values and the index as same. We have used 0, 1, 2, and then we have used the array from the NumPy library and given the index over here, and then finally use the voting classifiers, and we have given the estimators as XGBoost, CatBoost and then LGBM for classifier 1, classifier 2 and classifier 3 represented by CLF 1, 2 and 3. Then voting again is soft. Then we will predict the class probabilities for all the classifiers using the predict underscore prob function and giving in the argument as X, and using the classifiers for the XGBoost, CatBoost and Light GBM along with the voting classifier that we have built over here. So all this we are using for predicting the probability. Now to get the class probabilities for the first sample in the dataset, we'll create two classes and then we'll create a 2D array and put a for loop where we'll use the probus instance that we have used for predicting the probability for the model using various classifiers. So these two has been created, and now we'll plot what we have created or what model we have created. So we'll plot. So we'll use n equal to 4, that is number of groups, then ind instance for np.arrange, so arranging these groups, and these are the group positions, and width will be 0.35, that is bar width. Then we'll use figure and ax as the instance for the subplots. So we'll use the plotly package. So plt.subplots is the function that we have to use, and then bars for classifiers 1 to 3 and bars for voting classifiers. So for classifiers 1 to 3 we'll use the instance of p1 and p2 and use this ax.bar function where ax is the instance and bar is the function taking the parameter as ind, that is the group's position, np.hstack that takes the class probabilities that we have created, and the index -1 shows that it is taking all the values. Then the width is 0.35, then color h color, and same for the second one, that is p2, where we'll use the second class that we have created. And for the bars for voting classifier we'll use the p3 p4 instance, we'll create it, and ax.bar where bar is the function that we are using and ax is again the instance, and here the parameters are quite different. That is, ind is same, but here we are giving 0 0 0. So instead of hstacks, that is np.hstack, we just given the values as 000 because it is a voting classifier and we cannot use hstag in it for this scenario. So the color is quite different, and now we'll set the plot annotations using the axv line. So it takes the argument as the value 2.8, color equal to k, line style equal to dashed, and then ax dot set underscore x ticks with ind plus width. So it is a matplotlib function that takes when the values are true and a minor tick when the values are false. Then set the x tick labels for xgboost, catboost, light gbm voting classifier, and the rotation will be 40. And now we'll give the y limit, that is 0 to 1, plot title, that is class probabilities for sample 1 by different classifiers, then plt.legend that creates a legend for any plot, so for p1 and p2, and the values given over here is promoted no and is promoted yes, then location is upper right, then plt.tight layout that helps to automatically adjust the subplot parameters according to the padding. Then finally we'll use this plt.show to show the plot. Now let me run this. So this is the final step of building our AI model and optimizing it using various feature engineering processes, classifiers and encoders. So this is the class probabilities for sample 1 by different classifiers. So here the dark green color shows the people who are not promoted and the light green color shows the people who are being promoted. And this is the voting classifier and its average probabilities. So this is the visualization of the probabilities for the employees who are being promoted and who are not promoted, but the actual values we already saw using these classifiers over here. So there are 23,490 records of 2 columns consisting of employee ID as it is unique. So it shows the corresponding ID and the promotion status of the employees. So I'll just go up. So here we have created the model and we saw that the model took 10.4 seconds, and this is the learning of the model we have created. The model using the voting classifiers and XGBoost, CATBoost, Light GBM, gradient boosting or extreme gradient boosting instead of that. And after that we have the results and we worked on improving it. Then we get the result of promoted, and finally we have visualized using the plot our results. So this visualization of the data is just for our understanding, but how actually is the code implemented using the algorithms in real time is by integrating it using other softwares. So company will not use this code directly. So what they will do is they will create the model using the code that we have built, and then what they will do is they might have another application that shows the information of the employees and their various parameters such as age and other things that we saw. Let me go to that section where we have looked around the data. So employee ID, number of training, age, previous year rating. So they might have an application that show the data. So there they can add a feature that predicting the promotion, and whenever they click on that, so this code is added in the backend. So before it shows the prediction of the employees or before it shows the list of the employees, this code is being implemented and the results are shown on the interface. So this is how artificial intelligence or machine learning algorithms helps the company to resolve the issue for their various business problems. So here it is the status of the promotion, whether the employee has to be promoted or not. So it is not about this problem. There are many real life business problems that can be resolved using artificial intelligence and machine learning. So these algorithms and these methods are added in the pipeline of a static software or an application, and it gives the output and the result that is the best prediction according to the analysis using the algorithm along with using the data set that is being provided by the organization, and it makes that software or the application as AI based application. So this is how we implement various scenarios using artificial intelligence.
Okay guys, a quick info: if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
So a fraud by definition is an act of deception that is used illegally to deprive a person or an organization or entity of money, property, or legal rights. So if we talk about financial frauds, which are the most common type of frauds, so a typical organization loses around 5% of their yearly revenues to fraudulent cases. And according to an RTI report, there were around 2,480 cases of frauds in 18 public sector banks, which involved around 32,000 crores. And according to an RBI report, in 2017 and 18, a total of 911 credit card fraud cases were there, which amounts to around 65 crore rupees, which were illegally transferred from different bank accounts. So now let's discuss some of the types of frauds that we can encounter in our daily lives. So the most common types of frauds nowadays are online frauds, where a person's account may be hacked and all his money can be transferred to different accounts illegally. And the most common types of frauds nowadays are the credit card frauds, where stolen credit cards and credit card numbers are used to make illegal transactions. And then we have threats and theft of inventory when someone breaks into a bank or an ATM. And then we have other types of frauds where someone can steal your idea or your professional work. So now that we know what are frauds and what are the different types of frauds and how they can affect different organizations and how important it is to detect the frauds and save ourselves from heavy losses. So now we'll discuss some of the rule-based approaches or traditional approaches that are used for detecting frauds. So in the rule-based approaches, the algorithms are actually written by fraud analysts, and these are based on strict rules. So if there are any changes that have to be made for detecting a new type of fraud, so they are all done manually. So either by making those changes in the already existing algorithms or by creating new algorithms. So in this approach, whenever there's an increase in the number of customers and the data, the human effort also increases. So in conclusion, we can say that the rule-based approaches are time consuming and they are costly. So now let's discuss some of the drawbacks of the rule-based approaches. So one drawback of the rule-based approach is that it is more likely to have false positives. So this is a type of error condition where the output of a transaction, it depends upon the rules and the guidelines that we have made for the training algorithm. So if you have a fixed rule and a fixed threshold, and if a transaction is rejected where it should not be rejected, so it will generate a condition of high rates of false positives. So these false positive conditions actually result in losing a lot of genuine customers. So our rule-based approaches cannot recognize hidden patterns since all of the rules are mentioned by the fraud analyst, and it cannot also predict new types of frauds because it always abides the rules that are mentioned by the fraud analysts, and that leads us to a situation where it cannot respond to new situations which is not trained on or it is not explicitly programmed on. So now that brings us to our next topic, that is how we can use data science to solve these problems and use data science for fraud detection. So the modern alternative is to leverage the vast amounts of big data that is collected from different online transactions and model it in such a way that allows us to flag or predict fraud in the future transactions. So for these, different data science techniques such as machine learning and deep neural networks are the obvious solutions. So here I'm going to show you an example of how machine learning techniques can be used to identify fraud in financial transaction. So machine learning is a broad field. It has a large collection of algorithms and techniques that are used in classification, regression, clustering, or anomaly detection. So two main classes are supervised and unsupervised learning. So in supervised learning, it is used to predict either the values of a response variable, which is also called regression, or the labels of a set of predefined categories, which is also called classification tasks. So in supervised learning, the algorithms learn how to predict unknown samples based on the data of samples with known response variables and labels. So in fraud detection, we are technically dealing with the classification task. So for each sample, that is a transaction, the predefined labels tells us whether it is a fraud transaction or not. So however, there are two main problems while using supervised learning for fraud detection. So the first problem is data labeling. So in many cases, fraud is actually difficult to identify, and some cases will be obvious. Some cases will be easy to recognize with rule-based techniques, and they usually won't require complex models. So where it becomes interesting are the subtle cases. So they're hard to recognize as we don't usually know what to look for. So here we use the power of machine learning, but because fraud is something that is hard to detect, so our training data sets that is collected from the past transactions are probably not classified correctly in many of these cases. So this means that the predefined labels will be wrong and some of the transactions will be wrongly labeled. So in this case, our supervised machine learning algorithms won't be able to learn how to find these type of transactions or these type of frauds in the future transactions. And the next problem that we face is the unbalanced data. So an important characteristics of fraud data is that it is highly unbalanced. So this means that one class is much frequent than the other. So in a fraud detection example, less than 1% of the transaction will be fraudulent. So in most of the cases, you'll find that less than 1% of all the transactions are fraud transactions, and most of the supervised machine learning algorithms, they are actually very sensitive to unbalanced data. So we have to use different techniques to balance the data before we actually use the supervised machine learning algorithms to predict the fraud cases in the future. So the next class of problems that we can solve is using the unsupervised learning. So it does not require or predefined labels or response variables. So it is used to identify clusters or outliers or anomalies in the datasets. So in our fraud dataset, we don't trust the predicted labels to be 100% correct. So since there will be a lot of incorrect labels as well, but we can assume that the fraudulent transactions will be sufficiently different from the vast majority of regular transactions, so that our supervised learning algorithms will flag them as anomalies or outliers. So in supervised learning, we can use the dimensionality reduction, which is also called a type of dimensionality reduction is called principal component analysis. So in preparation for our machine learning analysis, dimensionality reduction techniques are very powerful tools, and they are used to identify hidden patterns in the data. And whenever we have high dimensions in the data, so it is better to use PCA so that we can reduce the number of features for machine learning while preserving the most important patterns of the data. And similar approaches can be used, such as clustering algorithms, and like k-means clustering can also be used to find the patterns in the data using number of clusters. So in this video, we are going to use the supervised machine learning model on our data set so that we can predict future fraud transactions. Now let's discuss some of the challenges that we'll face while building a machine learning model on our credit card dataset. So various challenges arise when building models for fraud detection. So the first challenge is the unbalanced data. So there are plenty of legitimate cases, but only a very few fraudulent cases. So for example, in a credit card transaction, typically less than 0.5% of the transactions are fraudulent. So it might cause an analytical technique to experience difficulties in creating an accurate model. And depending on the exact application, operational efficiency may be a key requirement. So the fraud detection system might only have a limited amount of time available to reach a decision. So in a credit card fraud detection setting, the decision time to let a transaction pass or not is typically less than 8 seconds. And also incorrect flagging. So when flagging a particular transaction, if the transaction is flagged as fraudulent for a good customer, so you risk losing this customer due to the harassment caused by flagging the transaction as fraudulent. So now let's discuss some of the techniques that we can use to solve the first type of challenge, that is unbalanced data. So here you will find that most of the cases in a data set, most of the transactions will be legitimate transactions and very less transactions will be fraudulent transactions. So if you train your classifier model on this, so your classifier will tend to favor the majority class, that is your legitimate transactions. So which results in large classification error over the fraud cases, since it has not learned much because of the less data available to it. So the classifiers actually learn better when it is trained on a balanced distribution rather than an unbalanced data. So now we'll discuss sampling methods to solve this unbalanced data problem. So we always perform the sampling methods on the training set, not on the test set. So we'll always divide our data set into two sets, that is our training and test sets. So we'll build our model on the training set, and before building the model we'll balance the training set so that our model learns on the training set, and then we'll use the original test set, which is the unbalanced test set, to predict whether a transaction is fraudulent or legitimate. So the first technique is called the random oversampling technique. So in this technique we oversample the minority class, which is our fraud cases. So we copy the cases that are already present in our fraudulent cases. So we'll just copy the same cases multiple times till we reach a particular threshold or the value of the cases that we want in our dataset. And the other technique that we can use is the random undersampling. So in this technique we undersample the majority class, which is our legitimate cases. So we remove some of the cases that are present in our dataset which are from the legitimate transactions. So we'll remove some of those cases, and then we'll downgrade some of those cases till we have a dataset that has an equal distribution or an almost equal distribution of both the fraudulent and the legitimate cases. Or we can do both, so either we can up sample or we can down sample. So now let's discuss some of the techniques that we can use to solve the first type of challenge, that is our unbalanced data. So you'll find that most of the data sets have most of the transactions as legitimate and very few transactions as fraudulent. So if you train your classifier model on this particular dataset, so our classifier will tend to favor the majority class, that is the legitimate cases. So which results in the large classification error over the fraud cases, since it has not learned much from the fraudulent data because the data that was available to it was very few. So now let's discuss some of the techniques that we can use to solve the first type of challenge, that is our unbalanced data. So you'll find that in most of the data sets or legitimate cases they are outnumbered. So now let's discuss some of the techniques that we can use to solve the first type of challenge, that is our unbalanced data.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now let's continue with the session.
So you'll find that in most of the data sets, most of the transactions are legitimate transactions, and there are very few transactions which are fraud transactions. So if you perform a classification model on top of this dataset, your classifier will tend to favor the majority class, that is all legitimate cases. So which means that it will show a huge classification error over the fraud cases. So classifiers actually learn better from a balanced distribution. So if you train or model on a balanced distribution, it is more likely that we have a less classification error for our fraud cases, and it will be easily available to us. So now let's discuss some of the techniques that we can use to solve the first type of challenge, that is our unbalanced data. So you'll find that in most of the data sets, most of the transactions are actually legitimate transactions and very less transactions are fraud transactions. So if you create your machine learning model on this type of data set, your classifier will tend to favor the majority class, which is your legitimate transactions, and which will result in large classification error over the fraud cases. So our classifiers or our machine learning models, they learn better from a balanced distribution where the balance of the two classes, that is legitimate and fraud, can be equal. So now let's discuss some of the methods that we can use to solve the first type of challenge, that is our unbalanced dataset. So you'll find that most of the datasets, they have large number of legitimate cases and very few fraudulent cases, since in credit card transactions less than 0.5% of the transactions are fraudulent. So our classifier or our machine learning model will tend to favor the majority class, that is our legitimate cases. So which means that it will show a large classification error over the fraud cases. We will not be able to identify which case is fraud or not. So our classifiers actually learn better from a balanced distribution instead of an unbalanced data. So now let us discuss different sampling methods used to balance an unbalanced dataset. So the first technique is called the random oversampling. So in random oversampling, we increase the number of fraud transactions in the dataset by creating duplicates of the already present fraud cases. And the next technique is called the random undersampling. So in random undersampling, we decrease the number of legitimate cases to get a balanced distribution. And also we can perform both random oversampling and random undersampling by increasing the number of fraud cases and decreasing the number of legitimate cases. So now this is how our dataset will look like after performing both the oversampling and the undersampling. But the problem with oversampling is that it is done by creating duplicates of the fraud cases that are already present in our dataset. So that means that we will be training our model using a lot of duplicate values which won't explain the variance in the data. And the problem with undersampling is that we end up throwing away a lot of useful data and information which is not preferred in general. So that brings us to our next sampling technique, which is called the synthetic minority oversampling technique, aka SMOT. So in this technique, we oversample the fraud cases by creating synthetic fraud cases. So if you look at this scatter plot at the right hand side, the green dots here represent the legitimate cases and the red dots here represent the fraud cases. So in SMOT, we find the k nearest neighbor of a fraud case, let's say x here, and let's take the value of k as 3, so we'll find the 3 nearest neighbors of x. And after choosing the nearest neighbors, we'll randomly choose one of the x's nearest neighbors, let's say y here, and then we add a synthetic sample using the following method. So we'll take the x and the y coordinate of both the points and find the x and the y coordinate of a synthetic point, which is given as follows. So the synthetic point will lie on the line that joins both x and y, and here the number 0.3, it is a random number between 0 and 1, so we can use different numbers between 0 and 1 so that we get different synthetic samples that are present on the line that joins x and y. And we can also repeat this step multiple times for each neighbor of x, which is a fraudulent case, to get a desired value of the fraud cases in our dataset, and hence we'll get a balanced dataset after all. So now let's go to RStudio to implement credit card fraud detection model using SMOT. So now let's build a fraud detection model in R. So first of all, we'll import the dataset that we are going to work on. So I've stored my dataset in this particular folder. So once I load this dataset using the read.csv function, and I'll store the dataset in credit underscore card data frame. So if I run this line, your dataset will be imported, and after importing the dataset, we'll look at how our dataset looks like. So after your dataset is imported, you can click on the dataset name in the variable explorer, and once you click on the name, you will find that our dataset contains 284807 entries, that is rows, and around 31 columns. So this dataset is about different transactions made by different credit card users, and the first column here you can see is the time. So this is the time stamp, and then we have columns from V1 to V28. So these columns are actually the reduced versions using the dimensionality reduction. So the actual dataset contains the actual columns which the dataset does not contain. So these are actually the reduced versions using the PCA, so that the confidentiality of the users is maintained. So these are different features that are extracted from the actual features using the dimensionality reduction. So after the 28th column or the 29th column, we have the amount column that represents the amount of transaction that was done using this particular credit card. And then the last column here you can see is the class column, which contains two values, that is 0 or 1. So 0 here represents that the transaction was a legitimate transaction, and 1 represents that the transaction was a fraud transaction. So after that, let's look at the structure of the dataset and see what are the different types of variables that we have in our dataset. So if you use the structure function and write the name of your dataset, that is credit card, so you'll see we have around 31 variables, that is columns, and most of the variables are numerical columns. And the last column here you can see is class, which is also an integer column, but in actual it is not an integer column, it is a categorical column. It has two categories, that is 0 and 1, and 0 here represents the legitimate transactions and 1 represents the fraud transactions. So first of all, we will convert our class column to a factor column, two levels, that is 0 and 1, so that we can work with our dataset later on. So we'll convert this to a factor column using the factor function, and I'll pass the name of the variable, that is credit card $class, and then we have two levels, that is 0 and 1, 0 for legitimate cases and 1 for fraud cases. So we'll again store it in the same variable, that is credit card $class. So once you run this function, and if you now look at the structure of the dataset, so you'll see now our class column is a factor column with two factors, that is 0 and 1. 0 here represents the legitimate transactions and 1 represents the fraud transactions. So now let's look at the summary of the dataset to display the summary statistics of different columns. So here you can see the last column is a class column. So here around 284315 entries are legitimate cases, that is 0, and only 492 entries are your fraud cases, that is 1. And then we have most of the columns are integer columns with mean of 0, and the first column is our timestamp. So now before moving ahead, now let's check whether there are any missing values in our dataset or not. So we'll use the is.na function to check whether there are any missing values in our dataset or not, and then the sum function will count the number of missing values if there are any. So once we run this function, we will see that we don't have any missing values in the dataset, so it is okay for us to continue and work with our dataset. So now we have to use the class column. So first of all, let's see how many fraudulent and legitimate transactions are actually there in our dataset. So we'll get the distribution of fraud and legitimate cases or legitimate transaction in the dataset. We'll use the table function, and inside the table function we'll write the variable that we want the distribution for. So our variables or the transactions are stored in class variable in our credit card dataset. So we'll use the table function to get the distribution of different transactions. So here, after running this command, here you can clearly see that 0 represents the legitimate transactions, and most of the transactions in this dataset are legitimate transactions. So there are around 284315 legitimate transactions and only 492 fraud transactions. And if you want to get the percentage of the transactions, you can use the prop table function, and then inside the prop table function you can write the table function which will get you the distributions, and the prop table function will get you the percentages of the distribution. So here you can see that 99% of the more than 99.82% of the transactions in this dataset are legitimate transactions, and only 0.001% transactions are fraud transactions. So clearly we can see this is an imbalanced dataset. So now let's also plot a pie chart to get the distributions of our legitimate and fraud cases in our dataset. So we'll firstly set the labels of our pie chart. So the labels are legit and fraud. So we'll create a vector that contains two strings, that is legit and fraud, and we'll store that in labels. And after that we'll paste or we'll concatenate the percentages of your fraudulent cases and legitimate cases with the respective labels. So if you pass two vectors in the paste function, so first we'll use the paste function to concatenate two strings. So first vector that we have passed is the labels, which contains two values, legit and fraud, and then we'll pass the round function. So this function will actually calculate the percentages of the distributions. So we'll calculate the percentages of the prop table that we have just seen above, which will display this particular result, and we'll multiply it by 100 to get the percentage, and then we'll round this percentage to 2 digits. So we'll only get 2 digits after the point. So we'll use the round function, which will contain our percentages up to 2 digits of decimal, and then we'll have the labels which contains your two strings, that is legit and fraud, and we'll paste it together and we'll store the result in labels. So if you run this command and I look at the labels right now, so now your labels actually look like this. We have a 99.83%. so here we have rounded the values up to 2 decimals using the round function here, and the fraud cases are 0.1% and legit cases are 99.83%. So clearly we can see there is an imbalance in our data set. So let's plot a pie chart first of all to get the distribution or display the distributions of our legitimate and fraud cases. So we use the default pie function from the default R package, and we want a pie chart for the different distributions or the different categories of the class variable in our credit card dataset, and we'll use the table function to get the different distributions of the categories, and our labels will be equal to these labels, and then the color of the labels will be according to the orange and the red. So the orange will represent the number of legitimate cases and the red represents the number of fraud cases. And then this is the title of our pie plot. So our title will be pie chart of credit card transactions. So let's run this command to get a pie plot. So this is our pie chart for our credit card transactions, and here you can see most of the color is orange. It means we have around 99.83% of the legitimate transactions and only 0.17% are fraud transactions. So now if you make a model on this particular data, so you will get most of the accuracy. So we'll first of all make a model that is no model. So even if you don't have any particular machine learning model, and if you predict that every single transaction in this data set is a legitimate transaction, so you can see what kind of accuracy we'll get. So first of all, we'll predict that all the transactions in this data set are legitimate transactions. So we'll store all predictions in predictions variable, and we'll repeat integer 0 equal to the number of rows that are present in our credit card dataset. So in our credit card dataset we have around 284807 rows. So we'll create a vector that will contain zeros 284807 times. So after creating a vector, we'll convert this vector to a factor variable with two levels, that is 0 and 1. Here 0 represents the legitimate transactions and 1 represents the fraud transactions. So we are predicting without using any model that all the transactions are legitimate transactions. So once you run this command, we'll factor out or we'll convert this particular vector to a factor with 2 levels, that is legitimate transactions and fraud transactions 0 and 1. So after that, we'll use the confusion matrix to get the accuracy for these particular predictions or that we have done without using any particular model. So we'll use the caret package. So if you have not installed this package, you can use the install.packages command and write the name of your package to install it. And then after installing the package, you can load the package using the library function. And once you run this command, your package will be loaded, and then you can use the confusion matrix function from the caret package to get the confusion matrix and the accuracy. And if you want to know more about this particular function, you can press F1 here, so it will take you to the documentation on the right hand side, and then you can know more about this particular function. So in this function, we'll firstly pass our predictions that we have stored in predictions variable as data, and then we have our reference variable which will contains the actual classes that we have predicted. So we have predicted the classes of the credit card dataset. We will pass our reference variable or the actual classes that we have predicted. So once we run this command, we'll get the confusion matrix for this particular model that we have built without using any machine learning model. So here you can clearly see that we have correctly classified all the samples that were all the transactions that were legitimate transactions, but we have not classified any of the transactions that was a fraudulent transaction. So still we get an accuracy of 99.83% because we have flagged every transaction as a legitimate transaction and we have not flagged all the fraud transactions as fraud transactions. So this will be your true positives and this will be your true negatives, which are the correctly classified values. So our true positives are total and our true negatives are 0. It means we have wrongly classified all the samples that were fraudulent transactions. Here your 0 represents legitimate transactions and 1 represents your fraud transactions. So out of all the fraud transactions, we have flagged all the transactions as legitimate transactions, which are false positives. So here you can clearly see that if you only check the accuracy of the model that we built, so we'll be wrong most of the times because here accuracy does not represent anything. Here our goal is to maximize the number of cases or maximize the true negative so that we can classify most of the fraud transactions as fraud transactions. So now let's move ahead and build a model. So before moving ahead, we will take a small subset of our data set so that it is computationally more faster, and later on, once you have built a model on the smaller subset that you can make, then you can make the model on the whole data set, which will take some time. So we'll take a smaller version of the data set so that we can compute it faster. So we'll use the dplyr package to get a small fraction of our whole dataset, that is credit card. So I'll load the dplyr package first of all. So after loading the dplyr package, I'll use the sample frac function to get the fraction of our dataset, which will be random fraction. So it will contain both zeros and ones, and I'll pass my credit card dataset using the forward pipe operator, which will pass my credit card dataset to the sample frac function, which will extract 0.1%, that is 10% of the samples or 10% of the rows that are present in our dataset. So right now our dataset contains 284807. So after extracting 10% of the rows, it will be 28,480 rows. And we'll store the result in our credit card data frame again. And we have used the set seed function. So if we run this particular code again, so we'll get the same sample again. And if you don't use the set seed function and you run this code again and again, so your sample will be different every time. So we'll run these two lines together and we'll get a sample that will be 10% of all the rows that are present in our actual data set. So now let's look at the data set. That is a fraction, that is a subset of our original data set. So we have around 28,481 rows and all the columns. So this is a 10% of data set, and then we'll make a model on this particular data, and after building a model later on, we can build the model on whole data set. So now let's see what is the distribution of classes that we have in this particular data. So right now we have around 28,437 transactions as legitimate transactions and only 44 transactions as illegitimate or fraud transactions. And now let's plot a scatter plot between the two columns, that is V1 and V2. So we'll plot a scatter plot between the columns V1 and V2, and we'll see what is the distribution of classes between these two variables. So we'll use the ggplot2 function to plot a scatter plot. So firstly I'll load the ggplot2 library, and after loading the ggplot2 library, I'll use the ggplot function to plot a scatter plot. So ggplot function is based on grammar of graphics, so it has different layers that we stack upon each other to build a final plot. So our first layer is our data layer, where we pass our data frame. So our data frame is our credit card data frame that we have just extracted from the whole data frame. And then we have our second layer as the statics layer. So in the statics layer, we have our variables that we want to plot on our scatter plot. So on the x-axis, we have our variable v1, and on the y-axis, we have our variable v2. And we want the color of the points of the scatter plot according to the different categories of the classes. So we'll have two categories in the classes, that is 0 and 1. So we'll have two different colors for each particular category. And then to plot a scatter plot, we'll add the third layer using the plus sign here. So our third layer is our geom layer. So in the geometry layer, we'll pass our function that we want to plot scatter plot for. So here if we want to plot a scatter plot, we'll pass geom underscore point. So it will plot a scatter plot for us. And then if you want to change the background of your plot, so we can use the theme function. So theme BW, that is black and white. So it will make the background of your plot as black and white. And then you can also change the color of the points. So to here, this will get you the basic plot that we want. So if you zoom in on this plot, you can see that this particular color represents our legitimate cases, and our blue color here represents our fraud cases. So if you want to change the background of this particular plot, so you can use the theme function, which will change the background to black and white. And if you want to change the color of these points to different colors, so we can use the scale color manual function, and inside of that function we can declare our values. So our values of the colors are dodger, blue, 2 and red. So now this color represents the 0, that is legitimate cases, and red represents the fraud cases. So now let's run the whole command and we'll get the final plot, black and white background, and these colors as the color of the points. So if you zoom in on this particular plot, you will find that now this particular color, dodger blue 2, represents our legitimate cases, and our red color represents our fraud cases. So here also clearly you can see that we have a comparatively huge number of legitimate cases and only a few fraud cases. So if you train your model on this particular data, our model will not be able to learn a lot because the number of fraud cases are very less. So we have to use different techniques to balance the dataset before we actually make or build a model on this particular data. So before balancing the dataset, we'll first of all create training and test sets. So we only use balancing on the training set to train the model, and we don't use balancing on the test set because that will be the original test set that will predict values for. So first of all, we'll create training and test sets, and then we'll balance the training set and train our model, and then evaluate the performance of the model using the test set. So now let's build our training and test sets for the fraud detection model. So we'll be using the CA2's library. So if you have not installed this library, you can use the install.packages and the name of the library to install it. And after installing this library, you can use the library function to load the library, and after loading the library, we can use the sample.split function to split our dataset into two sets, that is training and test sets. So in the sample.split function, if you want to know more about this function, you can press F1 here. So it will take you to the documentation on the right hand side. So now if you want to split your dataset into training and test sets, so here we'll pass our column that we want to split according to. So since we are going to predict whether a transaction is a fake transaction or a legitimate transaction, so that column is a class column that represents zeros and ones. So we'll use the class column to split our dataset into training and test sets. So I'll pass the column, my class column, from the credit card dataset, and now I'll mention the split ratio, which will represent how many rows I want in the training set and how many rows I want in the test set. So if you write split a ratio equals 0.8, so 80% of the rows that are present in your dataset will be in the train set, and 20% of the rows that are present in your dataset will be in the test set. So if you run this particular line, and we'll store the result in data sample. So once you run this line, and if you look at the data sample now, so it will contain true and false values. So here the true values will be 0.8. So 80% of the values here will be true, and 20% of the values here will be false. And these number of values will be equal to the number of rows that we have in our dataset. So now we'll use this particular object to split our dataset into two sets using the subset function. So we'll use a subset function on our credit card dataset, and we'll check wherever the sample value is true. We'll store all those rows in train data. So after running this line, our 80% of the rows from the credit card dataset will be in the train data, and wherever the data sample value is false, we'll store all those rows in the test data. So 20% of the rows in the credit card dataset will be in the test data. So now let's run all these lines together. So now we have successfully created our train data and test data. So now let's click on the train data in the variable explorer to see how many rows are there. So we have around 22,785 rows in our training data, that is 80% of the rows of the whole data set. And then if you look at the test data, so we have around 5696 rows in the test data and all the columns. So we'll train our model on the trained data after balancing this data, and then we'll test the performance of the model using confusion matrix on the test data. So now if you want to check the dimensions of your training and test data, you can use the dim function, so it will display the dimensions. So our training data contains 22,785 rows and our test data contains 5,696 rows and all the columns, that is 31 columns. So now before making a model, we have to balance our data set first. So we'll use different techniques. So the first technique that we're going to use is called the random oversampling, which means that we will increase the number of fraud cases in our data set. So we'll oversample the minority class. So right now, if you look at the distribution of the class variable, you can see around 22,750 transactions are legitimate transactions and only 35 transactions are fraud transactions. So now if you want to increase the number of fraud transactions, so we'll use this particular method. So first of all, we'll write how many will store or number of rows in our dataset or number of legitimate transactions in our dataset in n legit variable, and then we'll store the number of fraction or the amount of fraction that we want for our fraud cases. So if we want our fraud cases to be 50% of the whole dataset using the random oversampling, so we'll write 0.50 and we'll store the result in new fraction legit. So now this fraction will be 50%. So in our final data set, after performing the random oversampling, the 50% of the rows will be your legitimate transactions and 50% of the rows will be fraud transactions. Now if you want to calculate how many rows should be there in our data set to accumulate both of the legitimate and fraud transactions as 50%, so we'll divide the number of legitimate cases by the fraction, and it will tell us how many rows we want in our data set to balance our legitimate and fraud transactions as 50-50%. So after dividing the number of legitimate cases by the fraction, we'll get the number of rows that we want in our data set. So if you run this function, we have stored the number of rows in new and total. So if you click on new and total, so you'll find that we need around 45,500 rows in our data set, and out of these rows, 50% of the rows or 50% of the cases will be fraud cases and 50% of the cases will be legitimate cases. So now to perform random oversampling, we'll use a package called rows. So if you have not installed this package, you can install the package using install.packages function and then write the name of the package that you want to install. And after you have installed the package, you can use the library function to load the package so that you can use the functions that are included in this package. So in this package, you're going to use the open.sample function, which will help us to perform random oversampling. So if you want to know more about this function, you can press F1 here. So it will take you to the documentation of this function. So in this documentation, you can see the first argument that we want is our formula argument. So in the formula argument, we have to mention our variables that we want to oversample. So here our class variable is the variable that we want to oversample, and then we have used the dot, which means the rest of the variables are independent variables, and this tilde sign is used to separate our independent and dependent variables. So our class is our variable that we want to oversample or that we will predict later on, and we'll use all of the variables in our dataset except the class variable, which we can mention using the dot symbol here. And after the second argument is our data argument, so it will require the data that we want to oversample. So our data comes from trained data that we have just created above our training set. And the third argument here you can see is our method argument. So if you go to the documentation, you can see that we have three methods, that is over, under and both. So firstly we'll perform the oversampling of the minority samples. So we'll use method equals over, and then we have our n argument, which will be the number of rows in the new dataset after the oversampling is performed. So that is equal to the number of new and total, which is 45,500 rows. And then we'll also use the seed function so that if we run this code again, so we will be getting the same sample again or the same number of oversampled rows again and again. So let's run this function now to get our oversampling result. So after running this function, if you just click at the variable that has been created, so here you can see we have different attributes of this variable, that is oversampling result. So our data is actually stored in the data attribute. So if you want to reach the data attribute, you can use the oversampling data and then the data attribute, and we'll store the data set in oversample credit. So if you store the result in oversample credit, and now if you look at the distribution of the classes that we have after random oversampling, so you will find that we have 22,750 legitimate cases and 22,750 fraud cases. So now the distribution of our fraudulent and legitimate cases are equal using the random oversampling. So before moving ahead, let's plot this distribution using the same V1 and V2 columns of our oversampling result. So now if you click at the oversampling credit, so this is our oversampling credit. We have 45,500 rows. So let's plot a scatter plot between V1 and V2 and see what is the distribution of classes between these two variables.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now let's continue with the session.
So we'll use the ggplot function to plot a scatter plot again. So here now our data comes from oversampled credit here, and then we have the variables v1 on the x-axis and v2 on the y-axis, and the color of the points will be according to the categories of the class column, that is 0 and 1. And then we'll use the geom function. So if you want to plot a geom, so if you want to plot a scatter plot, we'll use the geom point function, and then the theme of our plot will be black and white using the theme function, and the color of the points will be dodger blue and red. So if you want to change the color, you can use this scale color manual function. So once you run this command, you will get a scatter plot between v1 and v2 that represents your oversampled data set that we have just created using the rows package. So now if you zoom in here, you will find that we have the blue color or the dodger blue color as class 0, which is the legitimate cases, and the red will be our fraud cases. So here you can see still our points do not represent a lot of points compared to the blue points. So the reason is that in our random oversampling we create duplicate points, so most of these points are overlapping on each other, because we in random oversampling will just create duplicate points that are already present in our dataset. So if you want to know whether there are points overlapping on each other or not, so we'll add some jitter to these points. So once we add some jitter to these points, so you'll see that there will be a lot of points in this on top of each other, because we have just created duplicate points using the random oversampling. So to add jitter to the points, we'll use the position argument of the geom point function. So if you set your position argument to position jitter, and inside the position jitter function we can mention our width of the jitter that we want. So if you write 0.1 here, so now if you run this function, you'll find that there will be a lot of points that are overplotted or stacked upon each other, because we have just created duplicate points using the random oversampling. So now here you can see the points. When you add some jitter, you will find there are a lot of points that are stacked up on top of each other, because we have just performed the duplicate values. We have just increased the number of duplicate values using the random oversampling. So now let's perform our random undersampling. So in random oversampling, we just train our model on duplicate values, which is not a good condition. So we'll see what is random undersampling. So in random undersampling, we'll reduce the number of legitimate cases. We'll keep the legitimate cases equal to the number of fraud cases. So let's first of all see the distribution of our credit card dataset. So we have this distribution. We have around 22,750 legitimate cases and only 35 fraud cases in our training set. So now if you want to set the number of legitimate cases equal to the number of fraud cases, so we'll use this method. So first of all, we'll store the number of fraud cases in n fraud, and then we'll calculate we'll store the fraction that we want for our fraud cases or our legitimate cases. So we want the number of fraud cases equal to 50% of the whole data. So we'll store that in n fraud, and then we want to calculate the number of rows that will be in our data set, so that our fraud cases and legitimate cases are equal in number. So we'll divide the number of fraud cases by the fraction that we want our fraud cases to be in, that is 0.5. So once we divide it, we'll get the total number of rows that we need in our dataset to satisfy this fraction. And once you run this particular command, so if you look at your new total, so now our dataset will contain 70 rows, and out of the 70 rows, 35 rows will be number of legitimate cases and 35 rows will be number of fraud cases. So now let's use the o1.sample to create that particular data. So we'll use the same o1.sample, and now instead of mentioning the method as over, we'll write method as under, and then all of the arguments are same. So you just have to change the method, and once you run this particular function or particular command, so now your undersampling result will be calculated. And now if you want to get to the data set that is stored in undersampling result, so we'll get the dataset attribute or the data attribute of the undersampling result, and we'll store that in undersampled credit. So once you run this line, you will have your dataset that is undersampled credit. And if you look at your dataset right now, so we have around 70 rows, and out of these 70 rows, 35 rows will have legitimate cases and 35 rows are fraud cases. So now let's plot scatter plot between same v1 and v2 to see how our distribution of the points look like and the distribution of the classes look like between these two variables v1 and v2. So if you plot it now, so you'll see that now we have equal number of legitimate cases and fraud cases. So in random oversampling, we decrease the number of legitimate cases to a certain ratio so that we have more, or we have an equal distribution of legitimate and fraud cases. But the problem here is that we end up losing a lot of data which is not preferred in a general case. So now we'll perform both the random oversampling and undersampling to see how our data actually looks like. So now we'll perform both random oversampling and undersampling. So now the number of rows that we want in our dataset will be equal to the number of rows that are present in our training set. So our new dataset will also contain the same number of rows, that is 22785. And now we want our fractions of the legitimate and fraud cases equally in our dataset. So out of the 22,785 rows, 50% of the rows will be fraud cases and 50% of the rows will be legitimate cases. So we're not going to increase or decrease anything. We're just going to resample our dataset in such a way that 50% of the rows will be fraud cases and 50% of the rows will be legitimate cases, using both random oversampling for increasing the number of fraud cases and random undersampling to decreasing the number of legitimate cases. So after storing our fraction in the fraction of fraud new variable, we'll use the same o1.sample. So now we have used the method as both. So here, if you want to perform both random oversampling and undersampling, you can use the method as both. And then the n argument here is the number of rows that we want in our new dataset, and then the p is your probability of fraction. So if the method is both here, so the probability will be default by 0.5. So 50% of the rows will be your legitimate cases and 50% of the rows will be fraud cases. And then we have used the seed function so that we get the same sample again and again if you run this code again. So now if you run this code and if you get to the dataset using the data attribute of the sampling result, and we'll store that dataset in sample credit. Now let's look at the dataset. So we have around 2785 rows, and out of the 22,785 rows, you can see around 11,430 rows are legitimate cases and 11,355 rows are fraud cases. So if you want to get the percentages of these rows, so you'll get around 50% of the data are legitimate cases or legitimate transactions, and 49.8% are fraud transactions. So now let's plot a scatter plot between v1 and v2 to see how our class distribution looks like. So I've already added some jitter so that we can see the overlapping of the points, because we have performed random oversampling and undersampling both. So we have reduced some number of legitimate cases and we have increased some number of fraud cases. So now they are in equal ratio, but the number of fraud cases are overlapping on each other because they are duplicates of each other, and the number of legitimate cases are scattered on whole of the plot. So now let's move ahead and use the third method that we use, which is called the SMOT, which is the synthetic minority oversampling technique, which will add the synthetic samples in our dataset without actually creating duplicates of the fraud cases. So to implement SMOT, we use this library called SMOT family. So if you have not installed this library, you can use the install.packages and the name of the library to install it first, and then after installing you can use the library function to load the library to use the functions that are contained in this library. So after loading the library, if you look at the class distribution, we have the same class distribution, that is 22,750 are legitimate cases in our trained data and 35 are the fraud cases in our trained data. So now we want to increase the number of legitimate cases, or we want to add synthetic samples of the fraud cases so that we have a balanced data set that we can use to train our model.
Okay guys, a quick info: if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
So we'll start by first of all setting the number of fraud and legitimate cases and the desired percentage of the legitimate cases that we want in our dataset. So our legitimate cases are represented by N0 here. So we have around 22,750 legitimate cases, and N1 are the fraud cases. So we have around 35 fraud transactions, and then R0 represents the ratio that we want in our dataset after the SMOT. So we want 60% of our rows should be legitimate cases and 40% of the rows will be fraud cases. So we'll add synthetic samples in such a way that after adding the synthetic samples, our data set has 60% of the legitimate cases and 40% of the fraud cases. So now to get the number of times that we have to perform smooth to get the desired number of ratio of the legitimate and fraud cases, so we'll use this mode function first of all from this mode family. And if you want to know more about this function, you can press F1 here, and you can see we have different arguments, that is x, which is our data that we want to apply smooth on. Then we have our target value, so the vector of the target class attribute corresponding to our dataset x. So our x will be our independent variables, and our target will be our dependent variable that we are going to predict later on, and k is the number of nearest neighbors we want during the sampling. And then we have our dupe size, so it will be the number of times we run our smooth, or number of times we want to run our smooth to add different synthetic samples. So if you want to get the number of the dupe size, which will actually tell us how many times we have to run smooth in order to get the desired percentage of all legitimate and fraud cases, so we'll use this formula. So this formula will help us to get the number of times we have to run smooth in order to get a percentage of synthetic cases, such that our final data frame contains 60% of the legitimate cases and 40% of the fraud cases. So using this formula, which contains both R0, N0 and N1, once you run this here, and before running this we have to run these three together, and after that if you run this, so if you now look at the number of times, so we'll get we have to run 432 times. So after running 432 times on the smooth, we'll get to a value of your variables in such a way, or value of the points in such a way that or 60% of the points will be flagged as legitimate transaction and 40% will be fraud transaction. So we'll use the smooth function first of all, and our x will be our training data. So if you look at your train data right now, so our train data first column is our time column. So we are not going to use this particular column because we are only going to use these features v1 and v2 up to v28. So we'll be removing this particular feature from our data, and then we'll also remove the last column, which is our target column, which is our class column, which is 31st column. So we'll remove these two columns, and our training data will be from amount till v1. So after declaring our training data, that is our x, now we'll declare the target. So our target is our class variable that we are going to predict either 0 or 1, and the number of neighbors that we want is 5, and then the dupe size is equal to the number of times here. So once we run this particular code, so we'll get our output as smooth output. And if you right now if you look at the smooth output, so it will have different attributes, and our data is stored in our data attribute here. So we'll get the data set, which is data frame from this particular attribute. So we'll use this attribute data, and we'll store the data set which we have created using the smooth method. So once we run this particular line, and if you now click at the credits mode, so we'll get the data set that has around 37,905 entries and around 30 columns. So we have removed the first column, and our last column is our class column. So in the class column, around 60% of the class values will be 0, that is legitimate cases, and 40% of the class values will be 1, which is fraud cases. So now let's change the name of all this variable to class with an uppercase C, so that we are according to all of the data types that we have in our, or all of the data frames that we have used till now. So we'll change the first of all the name of our last column, that is our 30th column, to class with an uppercase C using the call names function. So after changing the name of the class, so if you want to now get the percentage of the number of legitimate and fraud cases in our dataset, so we can use the prop table function, and then we'll pass a table function which will get the distribution of the categories present in the class variable. So now you can clearly see that we have around 60% of the legitimate cases and 40% of the fraud cases represented by 1. So now let's plot a scatter plot between v1 and v2 and compare the original dataset with the dataset that we have created using this mode. So this will be our original dataset, where our data comes from the training data, that is without smooth, and the rest of the code is same as above. So this will be our original scatter plot between v1 and v2 for the training data. So now let's plot a scatter plot for the v1 and v2 in the credits mode data after we have used the credit, or after we have used this mode method on our training data. So you have just have to change your credits mode, the data that you are passing to ggplot function. So once you run this function, you will see that we have added a lot of synthetic points, around 40% of the synthetic points using this mode method. So now if you look at this particular data, you can see the blue points represent class 0, which is the number of fraud legitimate cases, and the red points represent number of fraud cases, and you can see we have not only added points, but we have added synthetic points and not the duplicate points. So these are all the synthetic points that our smooth algorithm has added using this mode method. And now after creating this particular data, we'll train our model on this data, and then we'll evaluate the performance of the model on the original test data. So now after making the data set 60:60 and 40 ratio, so the 60% of the cases now are legitimate cases and 40% of the cases are fraud cases. So now let's build a decision tree on top of this data so that we can predict whether a transaction is fraudulent or legitimate. So we'll be using the rpart package to build classification and regression trees. And we'll use the rpart.plot package to plot the regression trees or the classification trees. So if you have not installed these two packages, you can install using the install.packages command and install the packages for rpart.plot. So once you have installed these packages, you can load it using the library function. And once you load these packages, now we'll use the rpart function to make our classification and regression tree. So if you press F1 here, you will get to the description of this particular or the documentation of this particular function. So the first argument here is a formula argument where we have to mention the independent and dependent variables. So now we are predicting the class variable. So our class is our independent or the dependent variable which we are going to predict, and we'll use all other variables except the class variable as independent variables. So these were, if you want to write all the variables, you can use a dot instead of writing every single name, and then we use tilde sign to separate our independent and dependent variables. And then we'll pass our data that we want to train our model on. So now our data that we'll train our model on is a credits mode data, which is our balanced data. So once we run this, we'll create a tree which will predict the class of any particular sample based on all other variables. So we'll store the tree in cart model variable. So after building a decision tree on this particular data, so now let's plot the decision tree using the rpart.plot function. So we just have to pass our model that we have built, that is our cart model, and then we have used extra equals 0. So once we plot this model, we'll get a decision tree. So if you don't want any extra information on the leaves, we write extra equals 0, and type equals 5 will change the display of this plots, the shapes that we have used in this plot. And tweak equals 1.2, it enlarges the text to 120%. So the text will be enlarged by 120%. So this is our decision tree that our model has built. So it will use only one column in our data set, that is V14, and it will use this column to classify different samples. So if the particular column's V14th value is greater than minus 2.6, so that sample will be classified, or that transaction will be classified as a legitimate transaction, and if it is less than minus 2.6, so that transaction will be classified as a fraud transaction. So now after building the decision tree, let's now predict values on top of the test set to see how many samples are correctly and incorrectly classified. So we'll use the predict function to predict the values on top of the test set. So we'll use the first method, that the first argument that our predict function takes is our model that we have built, that is our cart model. And if you want to know more about this function, you can press F1 here, so it will take you to this particular documentation. So we'll use the cart model, that is our machine learning ML model that we have declared above, and then the data that it wants to predict on is our test data, and then we want to predict classes. So it will predict whether a class is 0, that is legitimate case, or class 1, that is fraud transaction. So it will predict on top of the test data, and then we'll compare the predictions with the actual values of the test data that we already have with us, so that we can see what is the distribution of the correctly and incorrectly classified values. So we'll store all the predictions in predicted val variable. So once we have predicted val variable, if you look at how our predicted value variable looks like, so here you can see the first value is 4. If you go to your test data, so here you can also see the first row of the test data is the fourth row of our whole data set. And if you want to see what our model has predicted, so for this particular row, the class value is 0, and our model has also predicted 0. And for this the second row, the class value is 0, and our model has also predicted 0. So if you want to know how many predictions are correct and incorrect according to our model and the actual values, so we'll build a confusion matrix to see how many predictions are correct and incorrect. So let's build a confusion matrix using the caret package. So I'll load the caret package, and then I'll use the confusion matrix function where I'll pass the predicted values first and then our actual values that are present in our class variable in our test data. So once you run this, you will get the confusion matrix for this particular model. So you can see here our true positives are 5625 and our true negatives are 7. So out of 9 samples that we have in our test data, 7 samples or the 7 fraudulent cases were correctly classified by our model that we have built using the credits mode data. That is, after using this mode method, the data that we have built, if we build our model on top of that, so we'll get out of 9 cases that are present in our test data, out of 9 cases, 7 cases which are fraud cases are actually classified. So we'll be able to detect 7 cases out of 9 cases that are present in our test data. And here accuracy is insignificant, but still if you want to see the accuracy, our accuracy is around 98.98%. So now if you use the model, if you build the same model without using more data or on the original trained data, and let's see what is the classification rate or how many samples are incorrectly and correctly classified. So this is our decision tree without using the small data. So now our data is actually the trained data, and I've excluded the first column of my data, that is our time column. So we were only using the variables v1 to v28 and then the amount column, not the time column, and the rest of the code is same. So this is our formula which contain dependent variable, that is class, and independent variables, the rest of the variables that are present in our data set. So we'll use this particular function rpart to create a classification and regression tree, and we'll store the modeling card model, and after that we'll plot the card model. So this is our model, looks like this is a decision tree that our model will use to classify different samples based on the legitimate cases and the fraud cases. So now let's predict on top of the test set and see what is the classification or the misclassification rate. So we'll use the same predict method, and then we'll call the card. In the predict function we'll mention the first argument as our model, that is our card model, and then we are predicting on the test data. So here also I have excluded the first column. So if you want to exclude the first column of the test data, you can write this. So here it will include all the rows and it will not include the first column, that is our time column of the test data. This is our test data, how it looks like. So if you want to exclude this particular column, because we are not going to predict using this column, so you can write -1 here, and after that we have to write type equals class. So it will predict classes for each sample, so either it will be 0 or 1. So now we have predicted the classes of the test data using our model that was built on the original trained data without using smooth. Now let's look at the confusion matrix. So now if you now look at the confusion matrix, you can see that our true negatives is 6. So out of the 9 samples, we are only able to classify 6 samples if we use the data set that we have, that is our trained data, without using the smooth. So now let's compare these two models using the whole data. So now instead of predicting on the test data, we'll predict on whole of the data set, and that will show us how many samples will be correctly classified by a model that was built on smooth and by a model that was built on the original data, that is unbalanced data. So first let's build our model that was built on the credits mode. So this will be our model that we built on the credits mode. Now let's predict on the whole credit card data set that will contain all the values. So we'll exclude the first column, and then we'll predict the classes, and we'll store the predictions in predict val. And after storing the predictions, let's see the confusion matrix. So in this confusion matrix, out of the 44 samples that we had in our dataset, 40 fraud cases were correctly classified by using the smooth data, or the model that was built on this smooth data, because our true negatives is 1. So these are the samples that was the transactions that were actually fake transactions, 1, and our model has also predicted that these transactions are fake. So out of 44, 40 transactions were actually correctly classified. And now let's build the same model using the model that was built on the trained data or the original data without the balancing factor or this mode. And after creating this data that is built on the original data set, that is unbalanced, and now let's predict on the top of the whole data set. And now if you build the confusion matrix, so you will see that we have only 35 right now. So we have using this mode, we can easily detect 5 more samples than we can detect using the unbalanced dataset. So that is why using smooth is preferable, because it balances the dataset first and then it predicts. So you can easily see we are able to classify more fraud cases using the smooth, which is 40, instead of using the original dataset that we have, which is unbalanced.
And then coming to the comparison between artificial intelligence and machine learning, let's break it down into a couple of simple points. The first thing has to be definition. We've already looked at this, so let's quickly glance over it again. Well, basically, in the world of artificial intelligence, the intelligence part of it is actually defined when we talk about, the machines gaining knowledge and, the ability to actually learn something and pretty much apply what it has learned. This particular stored knowledge, that is where the word intelligence comes in. Coming to machine learning, again, machine learning basically involves the process very similar to artificial intelligence, where it's acquiring information, but then it's doing it in a very different way. There's something called repeated learning, where it actually learns on one particular concept again and again to master it and then understand what the concept actually is. Then coming to the second point, which is the technological aim of artificial intelligence and machine learning. Again, when it comes to AI, pretty much AI is concerned about, increasing chances of success in actually mimicking human intelligence. So it at a couple of stages, artificial intelligence is not concerned with how accurate it is, but it's a very different story when you come to machine learning, because when it comes to machine learning strives to increase the accuracy, and it would actually sideline the amount of success that it sees, because achieving accuracy in a mathematical model in terms of machine learning is actually a very good priority, and it is actually built for what it's supposed to do, and it does it very well. Coming to the third point, it is basically the goal of artificial intelligence and machine learning. When we talk about the goal of AI, it is to, again, as I've already told you, to simulate natural intelligence, to prove to humans that machines can be as good as humans, and this is done by solving complex problems and whatnot. Coming to machine learning, again, machine learning, the primary goal of machine learning is to actually learn from the data that it actually sees, understand what the data is, then perform certain tasks using the data. Since it does it repetitively, it understands it better and better every time it does it, and this increases the performance of that particular machine. And then the fourth point is how simpleton it actually is. Well, artificial intelligence, put in very simple terms, is basically that it is decision making on steroids, because to a computer what feels like a very complex convoluted entity, it is actually a very simple dumb machine which has been coded by the humankind, right? So artificial super intelligence claims to, if it has ever been founded, or if a machine chooses to start coding another machine, the decision making skills of an artificial intelligence entity will be equal to that of human intelligence or better than that as well. Coming to machine learning, again, machine learning basically allows a system or a computer to learn things from the data it sees, does it repetitively, as you already know it. And coming to decision making, again, as we already talked about it, artificial intelligence is actually concerned with finding the optimal solution to an existing problem, but machine learning is used to see if the problem is actually pretty much optimal to work on or not. So it'll actually try to see if the solution, whatever it's obtained, is actually optimal, it's not optimal, it'll work, it'll not work, and much more. So here's a very subtle difference that you can see on your screen right now when it comes to artificial intelligence and machine learning. And then number 6 on this list is the outcome. So artificial intelligence, again, leads to developing system which basically will mimic human activities in certain circumstances. But then at this point of time, it can mimic everything apart from emotions and much more. In fact, it can detect emotions. That is how good it is. But for it to mimic human level emotion is impossible at this point of time. But then let's not say it's impossible in the future as well, because we do not know what the future holds. And then coming to machine learning involves this entire procedure where you will be creating algorithms which learn on their own. And here's the best part about the comparison: machine learning will help achieve artificial intelligence at the end of the day. So the outcome of artificial intelligence is to equal human intelligence, guys. So this brings us to the 7th point, again, which is a very important point for all of you guys as learners. Because here's the average developer salary of an artificial intelligence developer and a machine learning engineer. An AI developer gets somewhere over 120,000 USD per year. And then an average salary of a machine learning engineer is over $100,000 per year as well. Well, this number is an average number for an associate to a junior or a middle intermediate level programmer. But do know that there are companies out there in the world which will actually pay 3 times, 4 times the number you see on your screen screens right now throughout the world, so they don't mind where you are, they don't mind what amount they're paying out. If you're actually good with the skills and you have the right certification when it comes to especially artificial intelligence, machine learning, and concepts of data science, guys. And then coming to my final thoughts about this particular comparison, well, if it has to be put into one sentence, then know this: artificial intelligence will lead to intelligence at the end of the day, or some sort of wisdom. But if you're talking about machine learning, again, it's all about acquiring knowledge, and this knowledge again is put into use when we talk about artificial intelligence in general. So to summarize the entire thing, guys, artificial intelligence will actually use all of the experience to acquire knowledge, to acquire skills, to learn it and understand how it has to apply all that knowledge. And machine learning will basically use all the experience it has from learning again and again and again to basically look for some pattern, understand what's going on there, to amplify the amount of knowledge it has gained, to see where it's like picking a needle in a haystack. So machine learning is where it's the process of picking the needle in a haystack. Where we're talking about artificial intelligence, it finds the fastest way, it finds the most important way where a human is not required to pick out that needle from the haystack, guys. So coming to when you have to use artificial intelligence, when to use machine learning, here is when you'll be using artificial intelligence. Artificial intelligence is required in situations where there is a requirement of precision, where there is a higher degree of precision is a very important requirement. And then you will use AI when you have faster decision making, logical decision handling, which does not require any human interference, guys. Because at the end of the day, emotions do come into place at a place of work, which might affect at the end of the day the work that the person is doing. But then if a machine does this, again, it cannot understand emotions. So your work will again remain very efficient because of the fact that it cannot have any emotional interference. And then coming to handling repetitive tasks, humans might get bored of doing the same thing again and again, but the machine does not. And then the next point is the reason why AI replaced a lot of jobs in the last year. It is that it can work 24/7, 365 days of the year without taking any single break, unless there's, of course, a breakdown in whatever it's doing. But then without a break, because humans again are very, very limited when it comes to working when you directly compare it to a machine, because machines can go years and years without a single break, but a human cannot, obviously, right? And then coming to risk analysis and risk taking, the machines can actually take a very good calculated decision based on so many things, so much mathematics, so much programming, and much more. Coming to machine learning is actually used where it can see the data and see a trend or a pattern that it can find. And another important reason is that there should be no human intervention here as well. The basic idea is to make the model self-sufficient enough so that it can understand the patterns and trends. And then, if there is a requirement for machine learning, then there'll definitely be some sort of requirement for continuous improvements, continuous learning, and hunting for more knowledge. So this brings us to the point which says that, improvement needed is actually linear. It does not have to be, learn, wait, forget, and no, it has to be learn, and keep going like that. That's what the point basically means. And then coming to the next point, it does not require any human intervention when it comes to adaptation as well. So humans take a lot of time to adapt, so let's say to a new climate, to a new technology they're learning on, everything in general, right? So humans need some time to go about doing that. Machines, well, if there is a requirement where you have to change certain programming language to something else, and nowadays there are tools which can do it automatically for you as well. And then industrial requirement are there, guys. So basically what we're trying to do is we're trying to perform predictive analytics in the world of manufacturing as well, like what product is doing good in what part of the world, why is this car selling so much more. So you have machines which can tell you all of this. You don't need any more humans to look at the numbers, plot graphs, and go about taking a judgment call, which might be a little inaccurate at the same time as well. So this brings us to the last section of this particular comparison: what companies use artificial intelligence and what companies use machine learning. Here's the list for artificial intelligence, guys. Everyone at Walmart Labs, we have KPMG, we have Microsoft, Genpact, Ericsson, Accenture, and millions of other companies, guys. So everyone in the top Fortune 500 company makes use of artificial intelligence in one or the other way. And then coming to machine learning, there's a lot of companies. Here again, there are thousands and thousands of companies which goes on to making use of machine learning on a daily basis. We have everyone from NetApp, we have General Electric, we have Google, Amazon. You can think about a lot, guys. Twitter, Facebook, again, Apple, Capgemini, IBM. And there are so many companies, I cannot fit all these guys in one particular slide, or in fact a couple of slides as well. So what do you guys think about this comparison? Do head to the comment section and do let me know.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
And then we need to understand why we require artificial intelligence. Guys, again, head to the comment section and let me know your top reasons of why you think we require artificial intelligence around us. I mean, human beings are the most intelligent species out there as of now. I mean, sure, that's debatable, but as of now, that's how it stands. Well, so why do we need artificial intelligence then? Well, let me tell you, humans are the most intelligent beings, but then there is only so much that we can do. For example, consider handling a huge amount of data, right? So in this world we live in, basically we live in a world which is a big data problem. So we have terabytes, we have hexabytes, we have petabytes worth of data coming in from each and every Fortune 500 firm, pretty much every single day, every single hour of every single day, in fact. So this data is growing exponentially, and then when the data is growing at this rate, you cannot expect a human being to be on the other side all the time to handle it. So this exponential growth of data is handled by machines very easily. And then when we talk about the variety of data as well, let's say you need to go on to merge some data, split some data, basically bifurcate some data. There are varieties of data. There's unstructured data, semi-structured data, structured data. So it might not be possible for one human or a team of human beings to basically go on to do this with the amount of data I just told you, right? So when you think about it practically, the variety of sources through which the data comes in is again unlimited almost. So having a machine on the other end of it to take the brutality of the variety of sources, the types of data, the amount of data is going to make life more efficient for the employer as well as the employee. And then we come to processing speed. Yes, again, I'm going to restate the same thing. Human beings might be the most intelligent beings out there, but then we do have machines which can be exponentially faster than humans when it comes to certain basic things, let it be mathematical calculations or anything as such. So this will provide unparalleled performance when we have to compare a human being's work directly to an artificial intelligent being's work. If we have to go on to directly juxtapose them. So this brings us to artificial intelligence developers. Who are these guys and what do they do? Well, you need to know this. Again, AI developers are basically computer science based people, and these people have to do a lot with coding, programming languages such as Python, languages such as R, and many other programming concepts. So why do they need all this programming? Well, this is basically to ensure that they can design, maintain, test, evaluate all the artificial intelligence solutions that certain organizations need. So let's say again, the AI technology which has gone into building Siri at Apple might be extremely different, is definitely very different than the technology which went into Tesla's autopilot, right? So these developers need to understand what the problem is, make sure they can formulate the problem and then formulate a solution for that problem as well, right? So designing a solution for an artificial intelligence requirement, and in fact maintaining that product after it's been designed and evaluating to make sure that it is performing right where it should, is again very important aspects of an artificial intelligence developer. And I have a quick question for you guys on that note. So I'm pretty sure most of you guys use social media, right? It might be Facebook, it might be Instagram, it might be Twitter, and it might be all the other fancy social media apps out there. Coming to Facebook, let's see how AI developers pretty much work out here, right? So AI developers are pretty much responsible again to handle about 350 million photos a day which has been uploaded to Facebook, and they do a lot with face detection and image recognition as well. So let's say you and your friends decided to go on a vacation. Let's say there were 10 people of you and you clicked about 300 pictures. Now imagine tagging 10 of these people in all the 60 pictures, right? So again, 600 tags you have to do manually, and this is going to take many hours if you have to do this. But then Facebook already would understand who the person that is in the picture, where the picture picture was clicked, and much more. That is what geotagging means, and location options too. So this is told to you very subtle. It says, hey, was the picture clicked here? Is this person that? I mean, it'll show you the name of the person, and it'll show you the location as well, and you might be like, yes. So at that point of time, you might not recognize and realize the power that's working behind it to get you all the details, right? Again, and another important thing is automatic friend suggestions, right? So let's say you added someone on any of their other applications. Now Facebook owns WhatsApp and Instagram. So let's say you're in touch with someone on WhatsApp where you've saved their number or something. Facebook will tell you, it'll give you a friend recommendation saying, hey, why don't you add that person on Facebook as well? So imagine all the processing that goes behind this particular thing. I mean, it's so subtle, as I mentioned on the first slide, that we don't even know it's there anymore. And then when you talk about Instagram, see, there are 95 million photos which get uploaded to Instagram, and handling that is definitely a task, right? And the best thing that Instagram is known for these days is customized advertisement. So you go to Amazon, you're searching for the latest mobile phone, or you're searching for a mobile cover, tempered glass, whatever it is. As soon as you come back to Instagram, it's going to show you one advertisement which is beautifully put together. You'll feel like clicking on the advertisement. Basically, that's how customized these advertisements are. And again, face detection and object recognition as well. So that plays a very important role in Instagram. Location recommendation systems, again, it'll just tell you where the photo was clicked, what time the photo was clicked, and much more. Friend recommendation, again. So let's say, again, you added someone on Facebook, or you guys just let's say there are two people who use Instagram. You guys have talked on another social media, but then you guys decided to meet for breakfast or dinner or whatever. And as soon as you come back to Instagram, it's going to give you a friend recommendation saying, why don't you add this person on Instagram? Again, how does this work? Artificial intelligence is at play, my dear viewers. And then coming to Twitter handles pretty much 6,000 tweets per second. Again, there has to be some form of pretty much a pipeline, a channel for the data to flow through in and out of the Twitter's storage area, where pretty much they need to understand, they need to work with this data, because it's not all about storing the data when it comes to Twitter, right? Because they perform sentiment analysis of every single tweet. They check if the tweet has a positive sentiment, a neutral sentiment, a negative sentiment, and what pretty much they can check to the depths of what person in which area liked or disliked this tweet on the face of the globe, basically. So this will add power to their organization. This will make sure that marketing can be done using Twitter, and in fact, at the end of the day, you're bringing more sessions to Twitter, and they are happy. Coming to outreach analytics and customized marketing, again, pretty much it'll tell you who your audience is, when they're watching your tweets, when they're reading it, and why as well, right? So coming to data analytics, again, you can pull out any number of statistics you want with respect to sentiment analysis of any tweet that's present on Twitter, guys. So think about it. We never knew a simple tweet can have this much of a complex circumstance in the back end when we talk about data and artificial intelligence, right? So this brings us to the most important aspect of this video, guys, which is the skills needed to become an AI developer. And let me tell you about 3 important skills that I think you should have. And the first one is all about mathematics and all about algorithms, guys. Because at the end of the day, you need to understand how numbers can in fact be used to achieve artificial intelligence. There is so much that you might not know, and to the intermediate level viewers, pretty much you will know how much of importance mathematics and statistics play a role. And then coming to algorithms, all the machine learning algorithms are again one step closer to making the machines intelligent. All concepts such as machine learning, deep learning, neural networks, all these work under the same umbrella of artificial intelligence. All of these terms that I told you, all of their goals is to achieve artificial intelligence at the end of the day. So having very good mathematical skills and being well versed with the top algorithms which works with, again, based on statistics, is very vital. And second of the 3 most important skills is probability and statistics, guys. Why did I mention statistics again? Well, it is that important. You need to understand all the concepts, everything from the basics of correlation all the way till how you can basically churn through data and make sure the data will give you insights that the naked eye might not tell you at all. So that is one of the reasons why statistics is extremely important. Coming to the world of probability, again, we need to sometimes understand that the values can be continuous, the values can be discrete. We need to find out what a possibility of occurrence of something is, right? So that again, pretty much a machine, an artificial intelligence algorithm of today will not give you 100% accuracy all the time. It'll give you an accuracy of 80, 90, 95, 98%. Again, this 98% is 9 on 10 probability, so it says that there are chances that it might fail 2 times out of 100 times. Again, probability, right? So this is a very important second skill to have. Coming to the third most important skill is having the knowledge of a programming language, guys, because again, there are languages like Python and R which form a very strong requirement when you have to learn about artificial intelligence and to help you become an AI developer. And you can either go on to learn Python, you can go on to learn R, but then beginners do prefer Python because R actually has a steep learning curve which some of the beginners might find difficult. But then do not worry, you can pick up either Python or R and you can be on your way to become an AI developer. And then coming to what R is majorly used for, well, R is actually used to do a lot of data plotting, a lot of statistics, and it involves a lot of bringing mathematics and programming together is what I want to tell you guys. And then in a just again, most of the companies which basically has open positions for AI developers has these roles always present. So you need R and or Python, you're going to need statistics, you're going to need to work with algorithms, machine learning, and so much more. And on that note, here is a step-by-step guide on how you can become an artificial intelligence developer. Let us begin with step 1. Step 1 is pretty much again you understanding data structures in detail. You might be wondering why you need the data structures, right? Again, if you understand how your data is stored, how your data is talking to the other entity that is present next to it, then you will understand how you can increase the performance of an algorithm by making it improve itself by drastically changing its understanding of its neighboring data. So understanding the right data structure, understanding when to use what data structure is extremely important, and this is step number 1. Guys, I urge you guys to pretty much whip out your pen and paper or make notes of these, as this will help you a lot in case if you guys are considering to becoming an AI developer. Coming to step number 2, again, as I mentioned, programming. So Python and R are the biggest names when it comes to a programming language to help achieve artificial intelligence, and programming knowledge is vital, guys. It is necessary. There is no work around this, and in fact, it is so much fun to work with, and I've been working on this for a couple of years and I absolutely love it. So, working on Python, working in R, there are libraries for machine learning, there is TensorFlow, there's scikit-learn, there's PyTorch for neural networks, there's CNTK, that's the Microsoft's cognitive toolkit, and there are much more. There is Staffy, pretty much, guys. If I have to go on to naming the frameworks, I can keep on going. So when you think about this, there are so many things out there that you need to know, and this already forms the step number 2. So what comes after this? Well, step 3 is understanding a little bit of mathematics, guys. You need to have some sort of clarity on how numbers can actually be used to drive a data driven entity into making it self-sustain, because at the end of the day, statistics will play an extremely vital role in making sure your machine understands what's going on in it and derive some sort of continuous or differential inferences based on that. And then this brings us to step number 4. Step number 4 is the most important part, ladies and gentlemen, because here again you will be finding a problem. This is how you have to go by with step number 4. Find a problem which needs a solution. Let's say it might be a new startup that your friend is starting, or you just spotted a common problem across your daily life. So find that problem and make sure that you can formulate the problem and understand what the actual problem is. Now find a solution to that problem, and after you found the solution to that problem in a general human way, try to see if you can get the machine to do it. If you can implement artificial intelligence to do it almost as good as you, if not better, then your job is done. But then you need to understand that at the end of it, you becoming an artificial intelligence developer. So telling the world about it is again very important as well. So there is this website called as Kaggle, where pretty much it's an amazing community where people pretty much come together, give out their problems, give out solutions. There are challenges that you can take place in, and basically it's like a GitHub for programmers. Again, GitHub is the same thing, but when we talk about it, Kaggle is a little different, and I'm sure you guys will know how when you go on to explore Kaggle, which is your step number 4. So coming to step number 5. Step number 5 involves you to understand a little bit of cloud computing, because again, in today's world, half of the organizations we see around us are already scaled to the clouds. So everything from Amazon Web Services, we have GCP, which is Google Cloud Platform, we have Microsoft Azure, and much more. So taking artificial intelligence and scaling it right up in the sky through the clouds is now booming. And as my dear viewers, I have to tell you that having a good certification which will train you on all of these concepts is extremely vital. Working on AWS, working on GCP or Azure or any of these, so having cloud computing knowledge and bringing it together with artificial intelligence are very vital. And coming to step number 6. Step number 6 is again an important aspect for an AI developer, because not only you'll have to work with one single computer at point of time, you'll have to work with multiple entities, multiple computers, because at the end of the day, you're going to use this to exponentially increase your computing power. And this is basically done to understand how you can gain some sort of systematic knowledge onto scaling this artificial intelligence entity that you're developing onto a modern infrastructure. This is very vital, guys. So to revisit all the steps, here's a recap. Your step 1 will begin by understanding data structures. Step 2 with a programming language and some libraries. Step 3 is mathematics and statistics. Step 4 is finding a problem, analyzing it, and solving it. Again, the next step involves scaling artificial intelligence to the clouds, and the last step is to understand how you can make use of artificial intelligence on multiple machines at the same time, which is basically distributed computing. And to basically strengthen everything that I've said, here are some of the sample job descriptions that we can check out. So here's a job description for an artificial intelligence developer from the Penn State University in the United States of America. Their requirement is this. They say proficiency in Python is needed, experience with machine learning library TensorFlow, Infinite Cafe is needed, and pretty much they say proficiency in mathematics is needed, as we discussed, linear algebra, multivariate calculus, and much more. Skill is required in JavaScript or R, as we discussed, data structures, and ability to communicate technical topics to the people who might be non-technical audiences. And then cloud computing, AWS, as I told you, right? So we discussed all the 6-7 points, and again, you can see just in one job description, we can see all those 6 points reflecting onto us, right? And then in fact, coming to a researcher's jobs, we just checked out the artificial intelligence developer role. Let's check out the artificial intelligence researcher's role. Again, this comes from the Massachusetts Institute of Technology. It's called Lincoln Laboratory. These guys as well, they require you to have experience in machine learning software, PyTorch, TensorFlow, MixNet, Scikit-learn, and much more. They would appreciate if you guys had experiences in working with large computer vision data sets, experience with big data, Hadoop, Spark, Elasticsearch, Cassandra. You'll be able to work in a multidisciplinary team environment. You have to have very good communication skills, oral skills, and sometimes you might have to travel as well. So guys, when we think about these two job descriptions of an AI developer and an AI researcher, again, when you come to think about it, we have validated all the points that we pretty much just discussed, right? And this brings us to the most important part of our live session, which is pretty much to tell you what the average salary is. So here is the average salary, guys. So pretty much again, when you think about it, the average salary of a junior AI developer is somewhere around $80,000 in the USA, 7 lakhs per annum in India, 45,000 pounds in the UK, and then a senior AI developer has somewhere around $115,000 in the US, 15 lakhs per annum in India, and 60,000 pounds in the UK, guys. So these are some of the very big numbers that you can see when we talk about AI developers, AI researchers, and then as I told you, this is a very lucrative career that you can pretty much jump onto, guys.
Okay guys, a quick info: if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. Let's continue with this session.
Coming to the first question on these top deep learning interview questions set, the first question is what are the differences between machine learning and deep learning? This is a very common question that's asked, and it is very important that you know the basic differences that lie between machine learning and deep learning. One very good commonality is that both of these are actually subsets of artificial intelligence, and deep learning itself is actually a part of machine learning. So when we talk about machine learning, we're making sure that we find a way where we're training machines with a lot of data. We give it some data and we hide some data from it, in fact, and we use the hidden data later, which we also call as the testing data, to make sure that the machine learns something, and to verify if it has actually learned from its experience. When it comes to deep learning, we try to find methodologies and ways where we can sort of trick the machine into making it think like a human being, making it use the human brain structure in terms of working. In the concepts of neural networks, the entire concept is named after neurons and the use of neurons as well, just because how very similar to how it works in the human brain. So this forms to be the basic difference between machine learning and deep learning. Moving on to the second question, it says, what is perceptron? Perceptron is a very important concept in deep learning because it actually matches what we see in an actual neuron in a human brain. So coming to how it works in deep learning, a perceptron actually receives inputs from a variety of entities, and then later it takes these entities, applies some transformations on it, what we call as functions. It applies functions on this, and then it becomes the output. So input, perceptron, applying function, output. That is how the order goes. So if you have to talk about when perceptron is mainly used, it is actually used when we go on to perform binary classification, where we use an input, we try to see if we can classify something based on the output. There's so many factors when we talk about the functions as well. There is weights, there is biases, and there's a lot of things in a neural network in deep learning that has a lot of impact. And in this system itself, perceptrons play a very important role to take an input and transform it and work on it to give you a valid output in the case of classifiers as well. Now, coming to question number 3, it states, how is deep learning better than machine learning? Both deep learning and machine learning are very powerful in their own ways. To solve most of the complex problem in a very simple way, machine learning has got it covered. But then when you talk about deep learning will overpower machine learning, especially when it comes to working with data that has huge number of dimensions. Think about an Excel sheet which has about, let's say, 100 columns with 35,000 entries each, something like that. So when there's a lot of data in your data set and the dimensions are very large, deep learning will be exponentially efficient at working with things than compared to machine learning. So if your data is large, then a deep learning model will work very efficiently to actually solve it, handle it, and it'll make it easier for you to program and work with it at the same time as well. So this is how deep learning is having the upper hand over machine learning in a very simple and a concise way. Now, moving on to the fourth question, it states, what are some of the most used applications of deep learning? Again, this is a very common question that can be asked in your deep learning interviews. So at least make sure you mention at least 3 or 4 fields, and in fact I've put up around 6 fields on the screen right now. Everything from sentiment analysis, mostly Twitter, and all of that. Then we have computer vision to analyze graphics. Then we have automatic text generation, we have object detection, we have NLP, natural language processing, and image recognition. There are more fields. You can name about 10 to 12 offhand if you have worked a little bit on deep learning, but then it doesn't really add a lot of value if you just list 10 to 12. So rather just tell 5 or 6 and just explain 1 or 2 lines about what each of them mean. That way the interviewer has an idea that you are concrete with respect to all the concepts there as well. Now with this we can come to question number 5 that states, what is the meaning of overfitting? Overfitting and underfitting are actually 2 very common issues that have to be dealt with whenever you're working with data sets and whenever you're working with deep learning. Overfitting, as the name suggests, is a scenario where you have a deep learning algorithm, and your deep learning algorithm is looking very hard into your data, and it is trying to hunt for meaning. It is trying to find some meaningful correlations in between the data in the data set. Now, in a way, what happens in overfitting is that it will start vigorously hunting for the data, and this makes it pick up noise, what we call as noise, rather than any sort of useful data. So with this noise, it hurts the efficiency, it hurts the detection capacity of the model. So rather than picking up any useful valid information, your model will start picking up noise, and that is not a good thing. So what happens is, at the end of the day, you'll have a very high variance in your data and a very low bias. This way, of course, you would already know that your model will be very, very inaccurate in terms of detection, and very inefficient at detecting new things, even if it has a good level of accuracy as well. So when you think about it, overfitting needs to be fixed, and underfitting is just the reverse of this. Anyway, coming on to the sixth question, it says, what are activation functions? Activation functions are very important entities in deep learning, because these are the actual functions that will take your input and make sure that you have something usable on it. So the transformations that happen, right, it is all because of the activation function. So what an activation function is basically is that it has the capability to decide if a neuron actually needs activation or not in that particular array, in that particular set of neurons, to see if there has to be anything modeled from that particular neuron in the chain in the neural network, or if it adds a value to the next set of neurons as well. So this is actually done by calculating the weighted sum of it and then taking the bias as well. So at the end of the day, whenever you're making use of an activation function, the model output will be non-linear. And if you have to talk about the types of activation functions as well, so there's rectified linear unit, or ReLU for short. You have softmax, sigmoid, linear, tanh, and many others as well. So it adds value that you answer it in a way where you tell what activation functions are, how they're calculated, what the output will look like, and what are the types of activation functions as well. With this, we come to the seventh question that states, what is Fourier transforms that is used in deep learning? Fourier transform is very, very vital to deep learning, because it is one of these packages that is used to manage and work with a lot of data when we work with deep learning. As you already know, in deep learning, we will be working with huge data sets. So we need methods and tools and techniques where we can process these in real time, and we can make sure that we can handle it and work with it easily and quickly as well. So Fourier transforms is one of these packages that will make sure that you have high efficiency whenever you're working with data. And with Fourier transforms, your model is now open to a lot of signals where you can have the data processed from multiple entities, and to just make sure that you're opening up a dimension when you're working with the data as well. So Fourier transforms are a very, very vital part of deep learning. Now with this, we can come to question number 8 that states, what are the steps involved in training a perceptron in deep learning? There are about 5 to 6 steps whenever we have to talk about the perceptron learning, or training a perceptron as it's also called as, and these are the 5 steps. Firstly, the first step is always to initialize all the thresholds and the weights of the network. Then of course, we'll be providing the actual inputs. The outputs are calculated based on a lot of things, and we have backpropagation, all the algorithms that run in the back end, and after which we'll have the steps where we'll be upgrading the weights in every single step. So after the weights are upgraded, then we'll again provide another set of inputs. We'll be calculating the weights again, and this goes on from the starting initial node all the way till the last node of the output neural network. And this is how simple it is to actually train a perceptron in deep learning. Now with this, we can move on to the 9th question that states, what is the use of the loss function? So whenever we talk about neural networks and deep learning, we need a methodology, we need a number, we need a numeric, where we have the ability to see if the model is working towards its goal or not, right? So the loss function is a measure of accuracy here as well, because we're trying to see if the neural network actually learned something useful from the data or not. And a loss function is a negative metric, where if the loss function's value is less, then it's good for the model. If the loss function value is high, it means that the model is not performing well. So at all times, it is very vital that you mention that the loss function has to be kept to a minimal extent. Now with this we can come to the 10th question that states, what are some of the deep learning frameworks or tools that you have used in the past? Now this is a very common question that's asked in the interviews because they want to find out, the interviewers want to find out about the experience that you have with all of these tools. So just make sure to mention of all the frameworks, tools and techniques that you might have used in your projects or your certification programs, or whatever it is that you have used, the methodologies that you have used to learn. Of course, there are many top deep learning frameworks out there. We have an entire video on that on the channel as well, so make sure to check that out after this video. Among the top deep learning frameworks, we have TensorFlow, we have Keras, we have PyTorch, we have Cafe2, we have CNTK, that's Microsoft's cognitive toolkit. Then we have MXNet, we have Theanon, we have many others. In fact, you can list about 12 to 15 very good top deep learning frameworks out there, but then just make sure to mention 3 or 4. But then if you of course used more than that, then do make sure you mention that as well. But then make sure that you are very honest about it, and do not I would suggest that you do not state a deep learning framework that you might have not used, as that might lead to you being asked questions on that, and you not being able to answer as well. So make sure to take care about that. Now with this we can come to the 11th question that states, what is the use of the swish function? So the swish function is nothing but an activation function, as we discussed a while ago. So it's something called as a self-gated activation function, and it is developed by the people at Google. So one thing to note about the swish function is that it is extremely popular because Google has put up a very good claim that it outperforms all of the other activation functions that exists today in terms of efficiency. So we discussed the different types of activation functions as well, right? Tanich, Relu and all of these. So then Google came about, they devised an algorithm, the activation function algorithm, and they have put up saying that this will outperform everything else that already exists. So that is one of the reasons why this particular activation function has seen so much limelight as well.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now let's continue with the session.
Now with this we can come to the 12th question that states, what are autoencoders? Autoencoders itself are artificial neural networks, and this is something which is very important that you know. And of course, they do not have any supervision, as they have the ability to automatically try and map inputs and to find out outputs and work with it on their own. So it's a very interesting concept to work with autoencoders, and these are very efficient as well. But then when we talk about autoencoders, it is very vital that we talk about two important things. One is the encoder and one is the decoder. These two are the very important entities that we have to discuss about. An encoder will make sure that the input is taken and it is converted into a format which is understood by the neural network, into an internal computation state, of course. And then we have the decoder, which does the exact opposite of this. It will take the computational state data and it will make sure to convert it back into the output. So encoders, even though the name only has encoders, there are two operations that's going on. One is the encoder operation and the other one is the decoder operation. Now with this we can check out the 13th question that states, what are the steps that have to be taken whenever you make use of a gradient descent algorithm. There are actually 5 to 6 steps that have to be discussed whenever we talk about initializing and making use of the gradient descent algorithm. The first step is always you have to initialize all the biases and weights for the network as well. And after you have initialized all the biases, you have to send the input data throughout the network, which forms to be, of course, the input layer, the first layer of your neural network. And then we'll actually calculate the loss function, right? So you'll have an expected value that you're expecting at that point of time, and there will be a value which is predicted by the model as well. So calculating the difference between this will give you the error of how far away the neural network is from the actual goal. Now after that you will actually change all the values in the neurons to make sure to find ways where you can minimize this loss function, this difference that we just found out in step 3. And after which, of course, this entire process is an iterative process. You'll be looping it and doing across multiple iterations to find out what biases, what weights and how best you can do to keep the loss function at its minimum. So these are some of the steps that have to be followed whenever you're working with gradient descent algorithm as well. So with this, we can come to the 14th question that states, differentiate between a single layer perceptron and a multi-layer perceptron. We already discussed that, if we're talking about a perceptron, in case if it's a single layer perceptron, it will not have the ability to classify non-linear data for us, but then a multi-layer perceptron completely can, classify non-linear data. And a single layer perceptron is a bit limited in one aspect where, the number of parameter that it takes in is very less when you compare to a multi-layer perceptron. And this in big deep learning models can have a very, very, disastrous effect as well for efficiency, for effective working and whatnot. So again, for the second point, I think multi-layer perceptron wins. And when you talk about the third difference, of course, a single layer perceptron has many things that it can do well. But if we are talking about efficiency when making use of large data, well, again, a multi-layer perceptron of course takes the higher end because it is extremely efficient to work with in the case of large data sets. Now with this, we can come to the next question that states, what is data normalization in deep learning? So data normalization is a very, very important step. It is actually a pre-processing step where we try to make sure, we can move around the data, rearrange the data, and we can make sure to refit and pack this data into one particular range. This is the entire process of normalization. Why we do this is to make sure that, if your data is in one particular range, it means that your network has the ability to learn very effectively and be very efficient as well. So, when you're performing steps like backpropagation, having a data in a very structured range, a specific range, will make sure that your network can learn that much faster as well. So these are one or two reasons why this pre-processing step that we take called as data normalization is very important. Now with this, we can come to the 16th question that states, what is forward propagation? So backward propagation is the scenario where, we work from the output layer to the input layer, and here in forward propagation, it is the exact reverse. We follow in the order of the neural network. So, we go from the input layers to the hidden layers and then the output layer. So, when you're talking about a complex neural network, there'll be more than one hidden layer. So for every hidden layer, the output of the activation function is actually calculated, and this is done until the next layer can actually be processed. The reason they call it forward propagation, as I just mentioned, is to make sure we work from the input and towards the output. And this is the exact opposite of the backward propagation algorithm as well. So to make sure that we use the output of the activation function and to calculate it for the next layers, forward propagation is very, very important. Now with this, we can check out the 17th question. Again, coming back to the very main important question, your interview could start with this question itself. What is backpropagation? So backpropagation, instead of talking about what, the first thing you have to always discuss is why backpropagation is even important, right? So it is to make sure that we keep the loss function or the cost function less, and to see how the values changes whenever we, work with a variety of biases, a variety of weights. Whenever we change all of these, even a slight change can have a very big impact on your model. To understand how these work, we require the backpropagation. It's called backpropagation, of course, because it starts from the output layer, works backwards towards the input layer direction. So how is backpropagation calculated? Well, it is very easily calculated whenever you work by understanding the gradient that is calculated at every single hidden layer itself. So it's as easy and straightforward as that. Now with this, we can check out the 18th question that states, what are hyperparameters in deep learning? So when you talk about hyperparameters, even though the term is very complex, they're nothing but variables that are actually used in deep learning to actually determine the structure of a neural network. So these variables are put into place to make sure that we have an easy way of understanding so many different factors and parameters in the deep learning model, be it the number of hidden layers that are present, or the learning rate of the model, and much more. So hyperparameters are very important variables that will give us a lot of insight into how the model or the neural network is functioning as well. So moving on to the next question, it states, how can hyperparameters be trained in neural networks? So training a hyperparameter is very important, and understanding how you can convey this to the interviewer is also very important, because these are long procedures and your ability to concisely answer it is very important. So, to train a hyperparameter, we'll require 4 very important components. It's the batch size, the number of epochs, and there's something called as the momentum, and there's a metric called as the learning rate. So what happens in batch size is that we'll take the input, we'll split it into batches. Batch size can be varied depending on however it is required based on the efficiency and a lot of other things. These batches can be cut into further sub batches as well, if that is the requirement. So instead of pushing all the input into a concurrent pipeline, we just make sure to dig it up into batches and then vary it across. Now, when you talk about epoch, an epoch is basically a denotion of how many times the training data is run through the neural networks where it can train. So the number of epochs is the number of iterations at which the neural network trains as well. So it's an iterative process. The number will depend on so many different factors. Doesn't mean that if you have a large number of epochs that your model will be very, very accurate with every single iteration. It will go up to a point, and then of course your model will work in fact in the opposite direction. Now, when you talk about momentum is actually put into place where we have an idea to check out what happens in the next consecutive steps. Whenever data is being moved around in a neural network, it is vital to understand what happens next, right? So, there is no point if your model is very inefficient where it's passing around data and not driving any momentum from it. So momentum is this particular track where we make sure we understand what's happening next as well. Now, coming to the last component, it's a very important component. It's the learning rate. Learning rate is what we are all after when you work with deep learning, because this is used as a very important parameter where we're trying to denote what is the time that's required to actually update all the parameters when your model learns and when your neural network is ready to take in certain inputs and give you meaningful outputs as well. So these, 4 form to be very, very vital, very important components in the world of deep learning whenever we go on to train hyperparameters. Now with this, we can come to the 20th question that states, what is the meaning of a dropout in deep learning? Now, dropout might seem like a very common term, but it is actually a technique in the world of deep learning. Dropouts are a very important technique, in fact, because these are used to avoid overfitting. Overfitting and underfitting are common problems, as we discussed a couple of questions ago. So to avoid overfitting, to make sure that your model doesn't hunt for noise, what we actually do is, we purposefully remove a bit of data which might not be useful for the model to learn as well. So if you have a dropout value to be very low, it will have a minimal effect on learning because you're not removing enough data and your model can still go towards overfitting. But then if you remove a lot of data, then what will happen is the model will not have enough data to learn. So it will underlearn and then cause inefficiency as well. So this value, right, this drop off value should be very, very vital, because if you have it too low, it will not have an impact. If you have it too high, then your model will not learn effectively anymore. So understanding this is a key concept. Now, coming on to the 21st question, it states, what are tensors? Tensors, you might have heard of these. These are another name of arrays, guys. So tensors are actually multi-dimensional arrays that are mostly used in deep learning, where we have to represent data across either one dimension or in fact multiple dimensions as well. So why can't we just call them arrays and not tensors, right? So tensors have the specialty of a name because they have been very famous. They have been very vital whenever we work with data of higher dimensions. So one very big advantage when we talk about tensors is that whenever we make use of it in any of the programming languages, right, the syntax is very readable. It's a very high level syntax. So what that does is it gives us a clear picture of tensors, even though if we do not have very high amount of training in terms of making use of tensors or its terminology. As soon as we look at the programs, we'll have a keen idea about what tensors are and what they might be doing in the program as well. So this is one very good advantage when it comes to working with these multidimensional arrays called as tensors. Now we can move on to the 22nd question that states, what is the meaning of model capacity in deep learning? Model capacity is again a very important metric that we have to discuss about, because model capacity deals with the capacity of the model to actually take in a variety of mapping functions. So how many mapping functions can your model handle? How many can it concurrently work with as well? One thing we drive out of this metric is that higher the model capacity, it literally means that there is a large amount of information that can be stored and worked with in the network. If the model capacity is low, as the name suggests, it means it cannot handle and effectively a large amount of information at a time as well. So model capacity is something which is very straightforward, but yet it forms to be a very important concept in deep learning. Now, with this, we can come to the 23rd question that states, what is the Boltzmann machine? Boltzmann machine sounds very complex, but it is actually a type of a neural network, that we call as an RNN, or a recurrent neural network, where we make use of binary decisions, biases, and to do a lot of functioning and working for us as well. So Boltzmann machines are, like as I mentioned, RNNs. They are hooked together to create something that we call as DBNs, or deep belief networks. So these deep belief networks are extremely sophisticated. They have multiple number of hidden layers, and they're put into place because we have complex problems that require effective solving. So the entire goal of deep learning, in fact, is that we have extremely complicated problems, and we need to find ways to make use of the power of computing to simplify that to a good extent for us, and a Boltzmann machine will do exactly that. Now, after understanding this, we need to check out what are the advantages of making use of one of the top deep learning frameworks out there called TensorFlow. So, of course, this could be a very important question in case if you work with TensorFlow, because understanding the advantages of it is very vital. So TensorFlow has many advantages, and to me the most important advantages where it will give you a lot of flexibility and platform independence whenever you're working with it. The platform independence is very vital because we all have multiple operating systems, multiple platforms that we work on, and of course, so it has the ability to power through and train on both CPU and your graphical processing unit as well. And with new technologies with GPUs, it just makes it very efficient to work with tensors too. And then when we talk about auto differentiation and the features it brings with it is again a huge impact. When we talk about threads and its ability to handle asynchronous computation, this is where TensorFlow wins over many other deep learning frameworks as well. The second most important advantage to me is that it's open source. It has a beautifully large community, so you don't have to pay for it, but then at the end of the day, there are so many things that are being added in terms of features, technologies, fixes, and so much more. And this entire community of open source is just a beautiful thing, and I'm sure you can relate to this if you work with TensorFlow as well. So with this, we come to the 25th question that states, what is a computational graph in deep learning? So a computational graph, as the name suggests, is a scenario, or is a graph itself, where we try to take inputs, arrange them into meaningful entities called as nodes, and later create a graph structure out of it. So these are done to simplify certain mathematical calculations as to visualize them better. So in terms of deep learning and in terms of backend functionality, it helps a lot whenever we're working with parallel processing, as it provides a huge performance boost over a single threaded performance in terms of making use of actual computational graphs, as your processing power is now 2, 3, 4, 5 or 10 times, 10 folds better than how it was before as well. So computational graphs are very important units when it comes to working with deep learning. Now, we can come to the 26th question that states, what are CNNs? CNNs and RNNs are very different types of neural networks. CNN stands for convolution neural network, while an RNN stands for recurrent neural networks. Now, coming to the talk of CNNs are mostly used to perform visual analysis, or working with a lot of images and classification as well. You can have multiple images of many channels as well. So when we talk about images and channels, mostly we talk about colored images and black and white images. Colored images will have like 3 channels, red, green and blue, RGB structure, and so much more as well, right? So a CNN has the ability to easily work with, classify, and give you meaningful outputs on all of these images and visual data. Now, if we talk about a little bit more about CNNs, the next question can be saying, what are the various layers that are present in a convolutional neural network? So when the talk is of this, understand that there are 4 important layers in a convolutional neural network. One is the convolution layer, we have the ReLU layer, or the activation function layer as it's also called. Then we have the pooling layer and the connectedness layer. So when we talk about the convolutional layer, this is where we apply things and entities called as filters across the main data to have them as parameters to teach and train the network. So after the convolution step is done, we'll use the activation function to squish it and bring it into a range range which is workable and understandable by the neural network. After the activation function is done, then there's something called as pooling. Pooling is where again we shrink the data to make sure we are not losing any of the existing data, and what happens after convolution is we lose certain data as well. So we do stuffing in the pooling layer as well to make sure that we add certain bits, dummy bits, to make sure that the size of the image is actually maintained after every single iteration. So with every iteration the image shrinks a little, and with padding we make sure that we are not letting it shrink out of context as well. And then when we're talking about the fourth important layer of the convolutional neural network, it's connectedness. Here we're just making sure that all of the activation functions are applied correctly by making use of the bias, and generally checking that the entire neural network is connected thoroughly and it's working as expected as well. So as the name suggests, this is a very important layer to verify the understanding of the neural network. So these are the four very, very important layers that you have to know about in this particular order itself. Whenever you're mentioning the working of it, the questions can be like, what is the working of a CNN, or what are the layers that are present as well. So this will develop as both of those questions. Now, when you talk about RNN, as I just mentioned, next question can be, what is an RNN in deep learning? So RNN, as I discussed, it stands for recurrent neural networks, and unlike CNNs, the working here is very different. The use of it is very different, because RNNs, or recurrent neural networks, are very, very efficient at working with a lot of string data, textual data, genome data, handwriting data, and much more. So if you have already worked with any basic use cases where you're performing, let's say, handwriting prediction or detection of handwritten letters or whatnot, then there's a good chance that you've made use of an RNN. RNN uses the technique called as backpropagation that we've already discussed for all its training requirements, and it is very, very effective at doing this as well. Just like how CNN is very effective for working with images, it shows similar girth whenever you're working with textual data as well. So this is again a very important aspect in deep learning. Now with this we can come to the 29th question that says, what is a vanishing gradient whenever you make use of recurrent neural networks? A vanishing gradient, to be honest, can be considered as a scenario, because we already saw in the last answer that RNNs make use of backpropagation, right? So if there is backpropagation, then there's the calculation of the gradients at every single step. And whenever we work with backpropagation, whenever we calculate gradients, they tend to get smaller and smaller as the data works backwards from the output layer to the input layer. So since the value becomes extremely smaller towards the end as we approach the input layer, it causes a problem. So this basically means that your model will learn very slowly, and it cannot be efficient. It will underlearn sometimes, and it will cause a lot of problems. So this is a scenario of occurrence where your gradient values are becoming very low, and that scenario is what we call as the vanishing gradient. Now, I hope this is clear. So with this we can move on to the 30th question, which states, what is exploding gradient descent in deep learning? Just like vanishing gradient, exploding gradients are another issue which work in a very different way, because here is a scenario where we're clumping up all of the gradients. Means what it does is it will create a large number of updates for all of the weights in the model whenever it's training. So your model weights are being updated constantly, more than required, and and we already know the working of gradient descent, right? So it's based on the condition to keep all of these updates small to make sure that your upgrades are controlled, and only then can your gradient descent have some meaningful impact on your deep learning model. So with this, we have to understand that whenever you control these updates that happen to the weights of the model, right, this will have a huge impact, in fact direct impact on the efficiency of the model as well. So this is another scenario, what we call as the exploding gradient descent, where we have large number of updates that happen to the weights, which make it very, very inefficient at the end of the day too. Now with this, we can move on to the 31st question. So the 31st question states, what is the use of LSTM? LSTM is again a very important type of recurring neural network that we use to perform a variety of operations whenever we work with textual data and string data, as I just mentioned a couple of slides ago. So it stands for long short-term memory, and the working of it is slightly different because it makes use of something called as feedback chains, where it gives the network the ability to perform like another general purpose computing entity as well. So when it comes to that, it is very efficient at working working with a lot of data, especially when we're talking about genome data and genomic sciences. LSTMs are very efficient at working with that as well. So again, just being a type of another RNN, it sort of trickles down to having all of the features and the general working of RNNs too. Now with this, we can come to the 32nd question that states, where are autoencoders used? So we checked out autoencoders before, but then there might be a follow-up question to that stating where they are actually used, right? So you have to understand that autoencoders again have a lot of usage in the real world. So whenever we talk about it, you can have about 10 to 15 uses that, of course, that you might know already. But then it is vital that you at least mention 3 or 4, very popular applications of it as well. So let's say in the real world, if you have a black and white image and you want to have it colored out to what it actually was in its real life, then adding color to black and white images are very important use cases. And if you have any other old images where you have to remove noise, autoencoders are used here too. And then when you talk about dimensionality reduction and feature removal or feature variation as well, autoencoders seem to be very popular. And in fact, more than popular, they're popular for a reason, that is because they're efficient at handling all of these tasks. So make sure you mention all of these real life applications which are very popularly used as well. So with this, we can come to the 33rd question that states, what are the type of autoencoders? So, there's actually 4 types of autoencoders that you have to mention. One is the deep autoencoders, we have convolutional autoencoders, we have sparse autoencoders, and of course, we have the contractive autoencoders as well. So you really don't have to explain when you're asked for the types, but then it might add value if you can just state 1 or 2 sentences about each. But then it is very important that you mention all the 4 types that exist for autoencoders as well. So moving on, we come to the 34th question that states, what is a restricted Boltzmann machine, or an RBM for short? An RBM is actually a graph, if you have to talk about it in general. It's a graphical based model that we make use of in deep learning today, and it does a lot of things and can do a lot of things efficiently as well. So when you have to talk about performing operations such as classifications, or let's say regression, dimensionality reduction, be it collaborative filtering, topic modeling, or all of these operations that need to be performed that require an algorithm to do it, an RBM can do it very effectively in today's world of deep learning, where it can make use of the computation power of today and work with it effectively as well. So an RBM is again a very, very important, I know there's a lot of efficient being used in the case of deep learning, but then of course an RBM is very tricky to work with at the same time, but then the output that it provides is worth the effort. Coming to the 35th question, it states, what are some of the limitations of deep learning? We've been talking about advantages for 34 questions now. So it is very vital that you know what some of the limitations or the disadvantages are. There are not many disadvantages, but then there are a few disadvantages as well. The first one is, whenever you expect very good, very accurate output, you need large amounts of data, and your network has to have the capability to work with large amounts of data effectively as well. So that is one disadvantage. To gathering all the data might not be the case in all the factors. And then when we talk about how complex it is to implement, for example, an RBM is pretty complex for a beginner to work with and to get it working efficiently as well. So in a couple of cases, not just RBMs, RBMs might be easy to you, but then there are many concepts where it can be a little convolutional, it can be a little confusing, and it can be a bit complex to work with as well. So that is one of the disadvantages. And just like any other deep learning concept, your main focus always will be to make sure that your models are very efficient. So you'll be hunting on keeping that loss function down, you'll be hunting on making sure that your goal parameter is being met, and it is being met in a way where your model is very accurate, it is not overfitting a lot, it is not underfitting a lot, and it is performing as it should at its best. So hunting for these can take a lot of time, and it is not as simple as it's put out as well. So in case if you have had first-hand experiences working with deep learning, you will know what I mean with this. Now, we can come to the 26th question that states, what are the varieties of gradient descent that are available, or what are the variants of gradient descent? There are actually 3 very important distinctions whenever we talk about gradient descent. One is the SGD, or the stochastic gradient descent, then we have the BGD, or the batch gradient descent, and then we have the mini batch gradient descent. And whenever the talk is about stochastic gradient descent, the first important thing is that we only make use of one training example, and we calculate gradients based upon that. We update all the parameters based upon this single entity, this single example that we have. But then this is not the case when we talk about batch gradient descent, because once we calculate a gradient for batch descent, as the name suggests, we'll take the entire data set and calculate the gradient for all of the entities that are present in that data set, and then of course we update all the parameters one after the other in every iteration as well. And mini batch is again very similar to batch gradient descent, but then the batches itself are broken down into digestible pieces or small sized chunks, or small sized batches as it's also called, and then work with it just like how if it was a stochastic gradient descent, where we again take a simple training example and we make sure that we calculate gradient, update all the parameters, and perform the same operations for different values across a variety of iteration as well. So these are some of the three important gradient descent, stochastic gradient descent, batch gradient descent, and mini batch gradient descent that you have to mention when you ask this question. So with this, we can check out the next question that states, why is mini batch gradient descent so popular? So why is mini batch so popular, right? So this is again a question that's asked a lot. In fact, it's a very frequent question if you talk about the previous question or a follow up to that as well. So one reason why it is popular is of course because it is very efficient when you directly compare it against stochastic gradient descent. And when we talk about avoiding the concept of local minima, mini batch gradient descent will help because we'll be approximating all of the gradient values for the entire data set, and this is done because we use a concept called as generalization rather than hunting for specific values every single time by doing this concept where we are finding the flat minima and working with it. So what this does is make sure that we can avoid the local minima, we can approximate the gradient for the entire data set by the process of generalization, and it can be done very easily as well. So it packs a punch without having much effort into it. So that's one advantage of mini batch gradient descent. Now with this, we can check out the 38th question that states, what are deep autoencoders, right? So we checked out regular autoencoders. So what are deep autoencoders? Deep autoencoders are actually an extension of the regular autoencoders that we just checked out before. So here the difference lies where, the first layer is actually responsible for what we call as the first order function of the input. And if you have a second layer, then the second layer will take care of what we call as second ordered functions. Third layer will have a third order function. Fourth layer will have fourth ordered functions, and so on. So it goes on like that. So when we talk about a deep autoencoder, it is basically a combination of making use of two or more symmetrical DBNs that we discussed, right? So DBN is a deep belief network. So here in an autoencoder, we combine two or more of these deep belief networks, where let's say the first 5 layers is considered as the shallow layers, which will take care of the encoding aspect of it, and the last 5 layers, or in fact all of the other layers, can handle the decoding part as well. We checked out that encoding and decoding are two very vital aspects of autoencoders, and this is where deep autoencoders shine, and how they are complementary to the regular autoencoder as well. So with this, we can come to the 39th question that states, why is the leaky ReLU function used in deep learning? So ReLU stands for rectified linear unit. So leaky ReLU is also called as LREL. In case if you're asked about LREL, make sure to understand that it is the same as leaky ReLU. So, we use leaky ReLU in a concept, let's say, where we have the input values, and if they, if the input values are all less than 0, right? So what we try to do is we allow the passage of, small sized negative values to the function, where we use it to actually manage the function, work with it, and then, to drive the activation based upon that as well. So whatever neurons require activation, if the values are less than 0, leaky ReLU is very popular there, which will allow the usage of small negative values and drive meaning out of that at the end of the day. So after understanding leaky ReLU, it becomes very vital that you check out some of the examples of supervised learning algorithms. So, this is a machine learning question, but then we've seen this has been asked a lot in deep learning interviews as well. So what are some of the examples of supervised learning algorithms in deep learning is the question. You have to understand that there are 3 main supervised learning algorithms in deep learning. One is ANN's artificial neural networks, then you have CNN and RNN, convolutional neural networks, and recurrent neural networks respectively. So you have to mention the 3 types or the 3 main supervised learning algorithms usages in the field of deep learning as well, and these will cover all of the subfields that come under them. CNN has a lot under it as well. RNN has a lot of types, as we just checked out in the previous set of questions, but then mentioning these 3 should be more than sufficient. Now, There can be a follow-up question to this stating, okay, what about unsupervised learning algorithms? Can you state examples of that in deep learning? Well, yes, there are three very main important unsupervised learning algorithms in deep learning. We've checked all of these out. One is the autoencoders, then we have the Boltzmann machine, and of course we have something called as self-organizing maps as well. So these three form to be very, very important unsupervised learning algorithms that find a lot of usage in the real world when we make use of deep learning and its concept too. Coming to the 42nd question, it states, can we initialize the weights of a network to start from 0? Can the weight be 0? The answer is very tricky. You might be, leaning to say no, but then understand that the answer is yes. It is actually possible to start with 0 initialization. But then, of course, it is not recommended to use, because setting it up to 0 will make sure that your neurons will be giving the same output and the same descent and the same gradients whenever we go on to make use of back propagation. So the learning is almost next to 0 or next to nothing here. What this means is that your network cannot learn at all if we start with 0, because there is no asymmetry, right? So each of the neurons have to be unique from each other, and they have to do a unique task that is assigned to them. So if everything is set to 0, then when we work with back propagation, there is no way to tell apart from one neuron to the other. So the learning rate is 0, as I just mentioned, and it really doesn't work. But then yes, it is of course possible where you can have 0 initialization done to the weights before working with the network as well. So after understanding this, it becomes very vital that you understand something called as same padding and valid padding in CNN. So you remember CNN is used for image classification as well, and padding is done as a part of working with images. So whenever we perform iterations, with every iteration the images are being shrunken in size. To make sure that they're not shrunken beyond usage, we do padding where we apply more dimension to the existing matrix, right? So there are two types of it. One is valid padding and we have same padding. Valid padding is where it is used where there is no requirement for padding actually. So the output matrix will have the dimension n minus f plus 1 multiplied with n minus f plus 1, which happens after the convolutional state. And with case of same padding, padding elements are common padding elements in fact are added across all of the output matrix as well. So same padding is a situation where we try to match the dimension of the input matrix as well, but then valid padding might not be matched because it can have its dimension on its own, which is calculated by the formula given there as well. So same padding will try to match all of the elements after padding to make sure that your output matrix will have the same dimension as the input matrix. So that is the basic difference that lies between valid padding and same padding. Now, it is very important that you might be asked this question, so make sure to concentrate on this as well. So what are some of the applications of transfer learning in the case of deep learning? Transfer learning is a very popular scenario where we take a large model, we train it with a huge data set, yes, of course, and then we make sure to use this model, which has learnt on very complex data, large amounts of data, to work on simpler data set. So what this does is its efficiency is boosted to a very high extent because it has actually trained on complex data, but it is now working on simple data. So this way it is very efficient, it is very accurate, and in fact transfer learning is being implemented in our daily lives very well as well. But then if you have to talk about the complex use cases of it, we have BERT, we have ResNet, we have GPT-2, we have VGG16, and many other popular examples of where transfer learning are made use of and how efficient and effective they are as well. But then understand the basic working of it. So you train your model on something very complex, but then you actually show simpler data to it at the end of the day where it can work with it effectively and be more efficient too. It's as simple as that. Now with this we can check out the 45th question that states how is the transformer architecture better than recurrent neural networks in deep learning? So, whenever we make use of something called as sequential programming, there are two important things you have to be concerned with. One is how much of processing power you're making use of at every single point of time. And so what is the difficulty that you're facing whenever you have to work with parallel execution, right? So sequential processing will raise these two red flags. And what this does is this actually gave away these two concerns were the primary reasons why we have something called as a transformer architecture now. So in a transformer architecture, we have something called as the attention mechanism. The attention mechanism will take all of the dependencies that are available and it will map in between each of the sentences whenever things have to be processed as well. So when we talk about concepts such as NLP, right, natural language processing. Here, since the data is mostly sequential, it'll of course bring up the two concerns as mentioned above. But then by making use of these attention mechanism, by mapping all of the dependencies, by making sure your model can recognize these entities faster and map it across to a dictionary faster, let's say, then transformer architecture is very effective, as you can think about it. So with this, we can check out the 46th question that says, what are the steps that are involved in working with an LSTM network, long short-term networks, as we discussed in a couple of questions before. So, whenever you're working with LSTM, there is three important steps that you have to think about. The first step is concerned with the network actually picking up all of the information, where it has to remember certain things, it has to identify what it has to not remember and what it has to process as well. So that is the first step, where your network has the capability to know what it has to remember and what it has to forget. And then when we come to step number two is where we actually update all of the cell state values, but then updating all of these will depend directly on the outputs of the step one, because depending on what information needs to be remembered or not, the cell state values are updated based on that. The third step, in fact, also depends on step number two, because here what we're trying to do is getting the network to calculate and analyze what is the current state, and which part of the current state should in fact make it to the output and which should not as well. So the most important step is step 3, but then without step 1 and step 2, it is very difficult to directly move on to 3, because you will need what is vital and what is not. Then you have to update the cell state values based on that, and lastly you have to make sure your network analyzes and calculates which part of the current state should make it to the output and which part should not as well. So these are the 3 steps that are very vital in the working of an LSTM network. Now we can come to the 47th question that states, what are the elements in TensorFlow that are programmable? So what are the programmable elements whenever you're working with TensorFlow as a deep learning framework? So the answer is very simple. It is very straightforward. In TensorFlow, all the users have the ability to program 3 main elements. One are the constants, one are variables, and one are placeholder entities. So these 3 entities are very important that you state out explicitly, because these are the entities that you can program explicitly, program manually, and work with them, depending on whatever model it is that you're working with as well. So after understanding this, we have to check out one more small concept called as bagging and boosting in deep learning. So the question can be, what is the meaning of bagging and what is the meaning of boosting in deep learning? So what happens in bagging is that, we actually take a data set, we split the data set, and we randomly shuffle around, move the data into multiple batches, or in fact we call it as bags, since the term bagging is used, and we use it to train the model as well. And then boosting is a different scenario where we take incorrect data points and we force the model to actually produce a wrong output. We give it a wrong input, we make sure it gives the wrong output. So this way the model has the capability to understand that, okay, this is wrong, and then it can retrain itself and increase accuracy as well. So this is a negative way of teaching the model, but then it works very, very well. If your model can understand what is wrong, that means that it knows what is right. So this way, making use of bagging, where we're splitting the data set, or making use of boosting, where we are giving it the wrong input and the wrong output derived from it to teach it better. Both of these are helping very effectively in the case of working with deep learning as well. Now with this, we can come to the 49th question that states, what are GANs or generative adversarial networks as well? So GANs are again very, very widely used. They are used to achieve this concept called as generative modeling in deep learning. What it is that it is an unsupervised task that basically is involved in a lot of pattern detection and pattern hunting in the data. So whenever we have an input data, we try to see if we can find out any patterns in it and make sense of it and convert it into a meaningful output. So GANs are very, very useful for this. So the generative part of it comes from the generator, where it is used to generate more than one example at a time, while we have another entity called as the discriminator. A discriminator will classify the examples which get generated by the generator. So the 2 entities, generator and discriminator, and it would add some value to your candidature if you actually mention these explicitly to the interviewer as well. So GANs are again they're very widely used, because whenever you think about it, everything is pattern detection in today's world, right? So GANs have a lot of implementation and a lot of requirement by us as well. Now with this, we come to the last question that states, have you earned any sort of certification to improve your learning and implementation process? Well, the answer to this is very important, because as you might already know, a certification program can give you a lot of advantages. Structured method of learning, a lot of use cases, real time projects, expert guidance, live classes, and to you this is fine, but then to the interviewer, what they are trying to understand from your certification program is, with the certification program, you are trying to show that you want to exceed in your career, that you want to build something, that you want to advance in your career. That is the first important point. The second important point is that, let's say if you're a fresher, if you learned it all on your own without having to learn it in college or something, that shows grit, that shows aspiration. And if you're a person who's moved from another programming language to come into the field of deep learning as well, that again shows very strong aspiration, that you are willing to put some time and effort, and that you've already put time, effort and money into learning all of these as well. And at the end of the day, that adds up to a concept where you're proving yourself to the interviewer that you are effective at what you do and you want to do this. So one very important thing that you have to know whenever you're talking about certification programs, right? So yes, you can list all the certification programs that you have had, but then what will add the most value is to tell the interviewer what you learned and how you used your learning to implement something new. See, because not just certification, any IT concept in the world, right? So we're trying to solve a complex problem using a simpler thing. So we're trying to make the complex problem very simple. So how have you taken a complex problem, how have you worked on it, and how have you simplified it by making use of your certification program is very important to the interviewer, and that is what you should talk about. Explain what you learned from it, explain how you learned and what you took away as well. And here is a small bonus for you guys. Apart from this, what would add a little more value is to make sure that you mention that that you're planning to use your learning in this particular way for that particular company that you're applying for, right? So you would have learned a lot of things. If you put it out in a way where you're telling the interviewer that, hey, I learned all of these and I think I can use it this way to help your company, that will impress the interviewer as well. So that is one very important way on how certifications will help you rapidly increase your career's dimensionality, basically. Well, with that, you have reached the end of this top deep learning interview questions. I take this opportunity to wish you all the best for all the interviews ahead. So you make sure to use this guide to understand how you can approach the questions effectively and how you can answer them precisely and with as much content and quality as possible.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below. So that's it guys, that's it for the live video. Thank you for attending it.